HTML Full Course. Welcome to HTML Engineering, the Extreme Guide. This is your definitive, production-grade HTML full course designed to transform how you interface with the web platform. Across this entire course, every single piece of markup, every structural element, and every data matrix will be authored directly inside a real, physical .html file using a professional code editor installed on your local computer. Fire up your local code editor, open a clean directory workspace, initialize a brand new .html file, and let us begin compiling raw code into live architectural masterworks. Furthermore, some detailed resources are available in description box. So let's begin. Chapter 0. The Philosophy Behind HTML. Section 0.1. The Art of Marking Up. Imagine you are holding a handwritten manuscript from hundreds of years ago. Before a book ever reached a printing press or a library shelf, it had to pass through the hands of an editor. The author provided the raw words, but the editor had a completely different job. They had to mark up the text. Using a pen, the editor would write specific symbols directly onto the page. These symbols did not change the story itself. Instead, they were instructions meant for the typesetter. They explained exactly how the text should be structured, organized, and broken down into meaningful blocks. This brings us to the absolute foundational law of the web, the separation of content from structure. The words are your data. The symbols are your metadata. To understand this, let us look at a raw piece of text before it has been marked up. Imagine seeing a solid block of text that reads, without any pauses, quote, "The original document is a mess. The first point is too long and the last is incomplete," end quote. To a computer or a traditional typesetter, that is just a continuous stream of data. It has no hierarchy, no emphasis, and no structure. Now, imagine the editor steps in to mark up that exact same text. They insert a symbol at the very beginning to indicate a fresh paragraph break. Then, right after the phrase, "too long," they inject a small star symbol, pointing the reader to a footnote at the bottom of the page. Finally, at the very end, they add 3 consecutive dots to show that the thought trails off. Long before computers, these physical symbols formed a universal language of editing. Traditional proofreaders used specialized symbols, like the pilcrow, to split text into paragraphs. They used the asterisk as a structural pointer to connect distant notes. They used the ellipsis to handle text omissions, the section sign to mark legal or thematic boundaries, and the caret to show exactly where missing text needed to be inserted. When you first look at HTML code, tags can feel cold, robotic, and foreign. But they are not. When you write HTML, you are not writing a programming language. You are simply practicing the digital evolution of a centuries-old human editing process. Section 0.2. What is a markup language? So, what exactly is a markup language? At its core, it is a formal system for labeling a document so that a computer can tell the difference between the words you want to show and the instructions on how to structure them. The secret to this is a concept called interleaving. This simply means weaving your structural instructions directly into the same stream of text as your raw words. Instead of keeping the text in one file and the layout rules in another, a markup language merges them together. It uses special characters like brackets, backslashes, or stars as a visual barrier, so the computer knows exactly when a word ends and when an instruction begins. To understand how this works, we can look at the family tree of markup languages. Over the decades, they have evolved into 3 distinct syntax styles. The first style is command-based. A great example of this is a language from the 1980s called LaTeX, which is still widely used in scientific publishing. Instead of tags, it uses a backslash to declare a command, followed by curly braces to hold the text. For instance, to create a section header and bold text, you would type \section, curly brace, introduction, close curly brace. Then \text, curly brace, bold, close curly brace. The second style is tag-based, which uses angle brackets. This family started with a massive, complex ancestor called SGML back in 1986. SGML was not a language you would use to write a standard document. It was a master toolkit used to create other languages. It introduced the bracket syntax we use today, like writing the word paragraph inside an open and close angle bracket right before your text. From SGML, 3 major tag-based languages were born: HTML, XML, and XHTML. HTML was created as a highly simplified version of SGML, designed specifically to link text documents across networks. It uses a predefined vocabulary of tags. You open an angle bracket, type a tag name like H1 or P, and close the bracket. To turn that instruction off, you repeat the tag, but add a /. XML came along later, looking identical to HTML but with one major twist. It has no predefined tags. You invent your own tags to transport and describe data, like creating an open bracket book tag, followed by a title tag. XML is completely ruthless. If you forget a single closing /, the computer will refuse to read the entire document. XHTML was a strict hybrid, where HTML was rewritten to follow those unforgiving rules of XML. In XHTML, every single tag had to be lowercase, all attributes had to have quotation marks, and empty elements like line breaks required a trailing / inside the bracket. Finally, the third style is lightweight markup, which uses plain text characters. The king of this style is Markdown, created in 2004. Markdown eliminates complex brackets and backslashes completely. Instead, it uses native keyboard symbols that you already use every day. To create a major heading, you simply type a hash symbol, followed by your text. To make a word stand out, you just wrap it in double asterisks. No matter which syntax style you look at, the computer processes them all the exact same way. It reads the raw characters one by one, in a continuous stream. The moment it hits a special character, like an angle bracket or a hash symbol, it switches into instruction mode. It isolates the command, groups the words that belong to it, and builds an internal tree structure. By understanding these different styles, you can see that HTML is not an isolated, quirky system. It is simply one specific branch of a massive linguistic family tree designed to give meaning to raw text. Section 0.3. The philosophy. Now that we know what a markup language is, we need to understand the golden rule of the modern web. It is a philosophy known as the separation of concerns. This rule dictates that a web page must be split into 3 completely isolated layers, and each layer must mind its own business. These 3 layers are structure, presentation, and behavior. The first layer is structure, and that belongs entirely to HTML. Think of HTML as the concrete foundation, the steel pillars, and the raw framing of a building. HTML only cares about what the content is, not what it looks like. It marks document boundaries, builds a hierarchy, and labels your text, telling the computer, this is a major heading, this is a navigation block, and this is a data table. The second layer is presentation, which is governed by CSS or cascading style sheets. This is the interior paint, the decorative trim, and the glass windows of our building. CSS takes your raw HTML structure and decides how it should look, handling colors, margins, fonts, layouts, and animations. The third layer is behavior, which belongs to JavaScript. This is the automated elevator, the plumbing valves, and the electrical switches. JavaScript adds logic, handles data, and allows the page to react dynamically when a user clicks a button or types into a field. Why does this clean separation matter so much to engineers? First, it makes a website incredibly easy to maintain. If you want to change the color scheme or the layout of 1,000 different pages on your website, you do not touch the HTML. You change a single CSS file, and the entire site updates instantly. Second, it ensures absolute accessibility. When a visually impaired user browses the web, their screen reader completely ignores the visual styling of CSS. It reads the raw HTML structure directly. If you blur the lines and hide your structure inside visual styling choices, the page becomes a confusing, broken mess for assistive technologies and search engine indexers. Third, it makes web pages fast. Browsers are built to parse your HTML structure separately from visual designs and programming logic. Separating these layers allows the browser to download and render text immediately, keeping the performance smooth and lag-free. When you see old code where people mixed these layers together, using visual HTML tags like font color equals red or center to force styling, or embedding inline JavaScript inside an element, it is a massive warning sign. It creates a brittle, messy codebase that easily breaks. As we dive into this course, remember this strict boundary. We are here to master the foundation. No styles, no programming logic, just pure, rock-solid structural HTML. Chapter 1. What is HTML? Section 1.1. From hypertext to the living standard. A short history. To truly understand HTML, we must first break down its name. Before it was a programming-like language, it was two entirely separate concepts that collided to change the world: hypertext and markup. Let us travel back to the late 1980s. In those early days of computing, digital documents were completely isolated silos. If you were reading a research paper on a computer and it referenced another document, you had to manually track down that second file on a separate system. It was slow and frustrating. Then came hypertext. Hypertext is simply text that contains digital connections or hyperlinks to other text. In 1989, a software engineer named Tim Berners-Lee had a brilliant realization. He figured out that if you combined hypertext with network protocols, you could link the entire world's information together. For the absolute first time, a user could click a link on a text document hosted on a server in Switzerland and instantly fetch a document hosted all the way in America. At this stage, however, the web was just raw, unstyled plain text. Hypertext solved the connection problem, but the documents lacked internal structure. A page was just a flat, endless stream of characters. To give it order, Berners-Lee took the concept of hypertext and married it to a document structural rule set. By inserting structural commands right into the text stream, he created hypertext markup language, or HTML. Now, a document wasn't just linked. It could have distinct headings, paragraphs, and lists. The very first version of HTML, released to the world in 1991, was incredibly simple. It contained just 18 basic tags. By the mid-1990s, the web exploded into the mainstream. Two massive tech companies, Netscape and Microsoft, went to war for control over how people browse the web. Instead of playing by the rules and sticking to a universal standard, they began inventing their own unique, proprietary HTML tags to lock users into their specific software. Netscape invented a tag to make text blink on and off, while Microsoft invented a tag to make text march across the screen. This fragmented the web entirely, forcing early developers to write multiple, completely different versions of the exact same web page just so it wouldn't break. To clean up this chaotic mess, an organization called the World Wide Web Consortium stepped in and tried to enforce absolute, ruthless strictness on web code. They created a hybrid language called XHTML. Under XHTML, if you made a tiny syntax error, like forgetting a single closing slash on a live web page, the browser parser would completely crash and display a fatal error screen instead of rendering the content. It was an engineering disaster for the messy, real-world web. Realizing the web needed a flexible, forgiving system that prioritized backward compatibility, a group of browser makers rebelled. They formed a new working group called the WHATWG and launched HTML5. Today, HTML has dropped generational version numbers entirely. There will never be an official announcement for an HTML6. Instead, it operates as a living standard. It is a single, continuously updated blueprint that evolves incrementally every single year, ensuring that code written today will work seamlessly far into the future, while keeping the ancient foundational web completely immortal. Section 1.2. Writing your first web page, the anatomy of tags. Now that we have looked at the history, let us look at what a basic, raw HTML file actually looks like. If you open a plain text editor and type out a few lines of code, you have created a functional web document. To understand how a computer reads your file, we must dissect the syntax of our tags and look at how they form structure. Let us start with the exact anatomy of a tag. A standard HTML tag is composed of specific structural characters that wrap around an element keyword to dictate its purpose. First, you have the left-angle bracket, which is the standard less than sign on your keyboard. This signals the browser parser to stop reading raw text and to switch immediately into instruction mode. Next comes the element character or token. This is the specific keyword that identifies the semantic type of the element. For example, the letter P stands for paragraph, while H1 stands for heading level 1. The characters inside the brackets indicate the tag's exact purpose. Finally, you have the right-angle bracket, which is the more than sign. This closes the tag definition and lets the text content begin. Most HTML tags work like an on-off switch for a structural container. The opening tag triggers the rule, and the closing tag turns it off. The closing tag is constructed identically to the opening tag, but it features a forward slash immediately after the less than symbol, which specifies the termination point of that element. Sometimes, tags need extra configuration data. This is where attributes come in. Attributes are always declared inside the opening tag, separated from the tag name by a single space. An attribute consists of two parts, an attribute name and an attribute value. Take the paragraph tag, for example. We can write open bracket P followed by a space, and then type the word lang followed by an equals sign, and the value, quote, ENUS, end quote, followed by a closing bracket. In this snippet, lang is the attribute name, specifying that we want to declare a human language property. The text inside the quotation marks, ENUS, is the attribute value, which tells the computer that the paragraph content is specifically written in United States English. When you start grouping multiple elements together on a page, they must follow a strict structural hierarchy, known as nesting. Think of nesting as a clean arrangement, where elements sit sequentially or entirely inside one another, building a clear box-within-a-box layout. When one element wraps around another, the outer container is the parent, and the inner element is the child. For example, a master HTML container can wrap around a body container, which then wraps around your visible headings and paragraphs. The absolute law of nesting is the stack order rule. Tags must close in the exact reverse order that they were opened. An inner child element must terminate completely before its outer parent element is allowed to terminate. If you open a paragraph tag and then open a strong tag for emphasis, you must close the strong tag first, and then close the paragraph tag. If you overlap them instead, writing the closing paragraph tag before the closing strong tag, the syntactic structure breaks, creating an invalid layout. Let us look at a practical code layout that uses these structures cleanly. Imagine a page that opens with an HTML tag containing our language attribute. Inside that, we open a body tag. Next, we write an H1 tag that says, quote, "This is the main heading," end quote, and we close the H1 tag. Below that, we open a paragraph tag, write, quote, "This text might be an introduction to the rest of the page," end quote, and we close the paragraph tag. Next, we establish a secondary structural tier by opening an H2 tag. We write, quote, "This is a subheading," end quote, and close the H2 tag. Finally, we open one more paragraph tag, write out our explanatory text, close the paragraph, and then close our major outer containers, the body tag, and the HTML tag. In this document, the H1 and H2 elements establish our informational hierarchy. H1 denotes the absolute primary title of the page section, while H2 denotes a secondary subheading tier to help the reader follow along. Now, here is a fascinating engineering quirk about how web browsers process this code. If you were to completely strip away the outer HTML and body wrappers from that file, leaving only the raw headings and paragraphs, and drag that file into a web browser, it would still render perfectly on your screen. This works because browser engines are built to be highly fault-tolerant. When the parser reads your text stream, it expects to see a standard structural layout. If it does not find those major wrappers, it does not throw an error or crash. Instead, the parser uses implicit node rules to instantly generate the missing HTML and body structures inside the computer's memory, automatically placing your text elements inside a valid container. You can witness this layout correction happen in real time on any desktop browser. If you click the page and select View Page Source, you will see the exact, raw, incomplete text file that you wrote. But if you select Inspect Element, you are looking at the live internal memory tree of the browser, known as the Document Object Model. There, you will see that the browser has automatically generated and wrapped your elements inside a perfectly structured HTML and body node architecture. Even though this safety net exists, professional engineers must never rely on the browser to guess document boundaries. Omitting your structural containers can cause severe rendering and processing errors the moment you try to add complex document definitions, metadata tracking, or styling rules. Master the syntax, respect the hierarchy, and always explicitly wrap your code. Section 1.3. The Execution Paradigm, Imperative versus Declarative. To truly understand how a web browser processes your source code, you must grasp a fundamental engineering concept. You need to differentiate between how standard programming languages execute instructions versus how HTML defines a document. This comes down to two contrasting styles of writing code, the imperative paradigm and the declarative paradigm. Let us break down the first style, which is imperative processing. Programming languages that you might already know or have heard of, like JavaScript, Python, or C++, operate on an imperative model. In this setup, you write explicit, sequential instructions that detail exactly how a machine must perform calculations or manipulate its data state. Imperative code relies heavily on step-by-step control flow. The computer executes your code linearly or jumps down conditional branching paths using commands like if and else. It can also run logical loops using instructions like for and while. Furthermore, imperative code requires manual state management. This means your program explicitly allocates memory to store dynamic variables, and those variables constantly change as the logic runs. You are writing an algorithmic recipe, telling the CPU exactly how to transform an input into a desired output. For example, if you wanted to create a heading using imperative JavaScript, you would have to write a line commanding the computer to create a new H1 element node in system memory. Then, you would write a separate line instructing it to set the text content of that node to say, quote, the main heading, end quote. Finally, you would write a third line commanding the machine to physically append that new node into the active document body. You have to spell out every single step of the process. Now let us contrast that with the second style, which is declarative definition. HTML operates strictly on this declarative model. In a declarative paradigm, you do not write algorithms, and you never instruct the browser engine on how to perform its underlying tasks. Instead, you simply describe what the final data structure should look like. Declarative code features no logic or flow control. HTML has absolutely no variables, no functions, no conditional branches, no loops, and no math operators. It also features structural permanence. The markup you write defines a fixed, static blueprint. It describes the exact nature of the content at a single coordinate in time. When you write declarative code, you utilize delegated execution. You declare the structural identity of the content, and then you completely outsource the complex layout mechanics, the text wrapping calculations, the pixel measurements, and the font paint physics to the browser's internal engine. To achieve the exact same heading goal in declarative HTML, you do not write a sequence of creation steps. You simply write an open bracket, H1, close bracket, followed by your text, and an opening bracket, /H1, closing bracket. You point directly to the data and state, quote, this is a heading, end quote. When an imperative program runs, a compiler or interpreter has to translate your logic paths into machine instructions for the CPU to execute. But when a declarative HTML document loads, the browser's rendering engine processes it entirely differently. First, the engine's parser reads your HTML string sequentially. It looks for syntax dividers, like the less than and greater than signs, to identify your explicit data states. Second, the engine does not execute or run your tags. It has no logic paths to follow. Instead, it uses your declared tags as a simple structural map to populate pre-existing data objects in computer memory, instantly assembling them into the live document object model tree. Third, once the structure is declared, the browser's built-in layout engines automatically handle the rest. They calculate exactly where every single character should sit on the screen, based on the current window width and system font defaults. As a web engineer, you do not need to manage the computational logic of rendering text. You simply declare the structural state of your data, step back, and allow the browser engine to automatically fulfill your description. Imperative languages tell the machine how to do it. Declarative HTML tells the machine what it is. Section 1.4. The skeletal structure of HTML. While browser parsing engines can often guess their way through isolated chunks of text due to their native fault tolerance mechanisms, any production-grade, standard-compliant web page requires a strict structural baseline. This foundational framework is the global layout skeleton, and it must wrap around all of your content. Every valid HTML document uses a standardized layout boilerplate to establish its operational zones. To visualize how this boilerplate is constructed, let us build it piece by piece, from the outside in. First, we establish the absolute boundaries of our document. To prevent structural errors and ensure everything aligns perfectly, a standard engineering workflow is to write your opening and closing tags together first, and then place your content inside them. Let us do that with the root HTML element. Write a pair of angle brackets, and inside them, put the word HTML to make your opening tag. Right next to it, write another pair of angle brackets, and inside them, put a / followed by the word HTML to make your closing tag. Now that you have placed your opening and closing tags together, create a space between them. Second, we place all of our structural document configuration data and text content inside these boundaries. Every single element you write from this point forward must live as stuff in between these two root tags. Now let us fill in that space to complete our full global boilerplate layout. On line 1, at the absolute first character coordinate of your file, write a less than sign, an exclamation point, the word DOCTYPE in all capital letters, a space, the word HTML in lowercase, and a greater than sign. This is your document type declaration. On line 2, write that opening root HTML tag we just discussed, but add a space, the word lang, an equals sign, and the letters EN inside quotation marks to set our language property to English. Next, inside our HTML boundaries, we create our configuration zone. Following our workflow, write the opening and closing head tags together first. Write a pair of angle brackets with head inside, and immediately follow it with a pair of angle brackets containing a / and head. Now, go inside that head container and put your metadata content. Write a pair of angle brackets inside them, put meta, followed by a space, the word charset, an equals sign, and the characters UTF-8 inside quotation marks. On the next line, write your opening and closing title tags together, and then put your page title text inside them. Right below that closed head tag, still inside our outer HTML boundaries, we create our visual stage. Write your opening and closing body tags together first. Put a pair of angle brackets with the word body inside, and right next to it, put a pair of angle brackets with a / and the word body. Now that the container is ready, we go inside this body section and place our structural text elements. For our heading, write your opening and closing H1 tags together and put your main heading text inside them. Below that, write your opening and closing P tags together and put your paragraph narrative text inside them. By always putting your opening and closing tags together first before adding content, you completely eliminate the risk of forgetting a closing tag and breaking your document structure. Let us break down exactly how the browser engine processes each of these distinct operational zones from our complete layout. The very first component is the document type declaration, which sits before the HTML root. It is important to know that this is not an HTML element. It is a null namespace processing instruction sent directly to the browser parser. The doc type acts as a mechanical switch. Writing this exact instruction forces the browser's rendering engine to parse the file using standards mode. If you omit this declaration, the browser engine drops into Quirks mode. In Quirks mode, the browser intentionally alters its internal layout algorithms to mimic the rendering bugs of late 1990s layout engines, completely changing how line heights, table widths, and element boxes are computed on the screen. The second component is the HTML tag itself, which acts as the outer boundary container for everything else. The root tag includes our language attribute, lang equals English. Browser engines, search engine indexers, and accessibility software read this string to manage text hyphenation, select localized typographical quote marks, and instruct text-to-speech screen readers exactly which phonetic dictionary to load. The third component is the head element, which establishes the metadata container. This zone functions as the configuration and data management center of your page. The browser engine reads this block in memory to set up environment states, process security protocols, and fetch external document assets. Elements placed inside this container, such as character sets or window titles, are strictly processed in system memory and are never painted onto the visible rendering canvas. The final component is the body element, which acts as the universal visual container for the document. The body element forms the root of your visible rendering context. Every heading, paragraph, table, interactive form, or embedded media asset that a user is intended to physically see must reside strictly inside this boundary block, so that the browser's layout engine can compute its dimensions and paint it onto the screen correctly. Section 1.6. Special Syntax. Welcome to Section 1.6, Special Syntax, Comments, Void Elements, and Raw Text. In this lesson, we are mastering the advanced structural mechanics of the browser's internal parsing engine to understand exactly how it handles non-rendering comments, standalone void layers, and protected raw text input perimeters. To build high-performance, enterprise-grade web applications, you must move past basic markup habits and understand that the browser reads your code stream using a strict finite state machine. As the parser tokenizes your file character by character, it dynamically alters its data processing laws based on the exact syntax states it encounters. Let us first examine document comments, written using the characters ampersand, less than, exclamation point, 2 dashes, and a greater than sign. A common engineering misconception is that comment blocks are simply ignored or deleted by the asset loader during network transport. In reality, when the lexical parser reads a valid comment sequence, it instantiates a true, independent comment node directly inside the live document object model memory graph. Because comments occupy active space within the DOM tree matrix, maintaining massive blocks of commented-out legacy code or heavy automated deployment metadata arrays will actively consume client RAM allocations. Visually, the rendering engine completely suppresses the display phase for comment nodes, assigning them exactly 0 pixels of structural space on the layout canvas. However, because these nodes stay locked in memory, they remain fully exposed to automated DOM inspection scripts, meaning you must never leave sensitive infrastructure details or security keys hidden inside your comment tracks. Second, let us master the absolute specification list of modern HTML void elements. Void elements are specialized standalone tags designed to represent immediate asset injections or explicit structural milestones on the page layout canvas. Under global development compliance standards, void elements have an internal content length of exactly 0, and are permanently banned from holding text fields or nested child nodes. The HTML Living Standard identifies an absolute list of exactly 14 conforming void tags: area, base, br, call, embed, hr, img, input, link, meta, param, source, track, and wbr. When the browser parser reads a void token, it registers the tag name, updates its internal configuration property values, and instantly closes the element context inside system memory. Let us completely shatter a massive validation myth regarding void tag assembly. Adding a trailing / before the closing bracket, such as writing out a graphic tag as less than img followed by a / and a greater than sign is a completely cosmetic presentational code choice that carries zero operational meaning in modern HTML5. The layout engine reads the trailing / and completely discards it as a character artifact or an attribute marker. The / exists purely as a visual habit left over from historical XHTML validation checks. Furthermore, attempting to force a separate closing tag onto a void element, such as writing a closing input or closing image block down the line, is a fatal structural syntax violation that breaks the parser, spawning broken ghost nodes inside your memory architecture. Third, let us perform a deep technical breakdown of the engine's specialized content parsing states, which protect script files and text data entry panels from layout distortion. The browser handles text stream data through 4 primary configurations: data mode, RAWTXT mode, RCDATA mode, and plaintext mode. Data mode is the default state, where the engine compiles standard tags and character references smoothly. However, the absolute microsecond the parser encounters a script or a style element opening bracket, it locks down its normal processing loop and switches instantly into RAWTXT mode. In this state, the engine treats every single character chunk as a flat literal text string, completely ignoring angle brackets and slashes to prevent programming code or presentation style metrics from breaking your document tree. Inside RAWTXT mode, character entity references are completely neutralized. Typing out the characters ampersand, L, T, and a semicolon will not render a less than glyph, but will print out literally as 4 distinct characters. The engine stays locked in this state until it matches a precise closing script or closing style tag token. Conversely, when the engine encounters a textarea text entry box or a title metadata block, it shifts its system environment into RCDATA mode, also known as escapable raw text. In RCDATA mode, the browser treats all nested angle brackets as flat literal plain text strings, which allows a user to type out or paste raw HTML tags inside a form area without the browser accidentally executing the markup code. However, unlike the script tag space, RCDATA mode actively processes character references. If you type the characters ampersand, a M, P, and a semicolon inside a textarea box, the engine computes the code block and instantly translates it into a single, clean visual ampersand symbol inside the form viewport. The state tracks this hybrid loop continuously until it scans the exact closing tag token sequence. Section 1.7. The Document Object Model Tree. Welcome to Section 1.7, the Document Object Model Tree. In this lesson, we are conducting a vital deep dive exploration into the hidden memory matrix of the browser layout engine to master exactly how flat text code strings compile into an active, multi-layered branching structure known as the DOM tree. To build high-performance, industrial-grade web applications, you must move past basic coding habits and realize that the browser never looks at your HTML markup as a simple flat document text file. Instead, the exact millisecond your code transfers over network lines, the browser's engine executes a highly sophisticated transformation pipeline. The system takes raw network bytes, decodes them into character matrices, tokenizes those packets into syntax boundaries, converts the boundaries into active memory objects called nodes, and links them into the finished document object model tree structure. The DOM tree is the definitive structural roadmap of your entire web page, held active inside the computer system memory, acting as the foundation for all layout display systems and scripting engines. Let us look directly at the shortcode example displayed on your screen to visualize exactly how these node families bind together in system memory. At the absolute foundation of our code sample, we have initialized a master main element node carrying a class configuration name of DOM tree architecture wrapper. In our DOM tree graph, this main element node stands as the top-level parent anchor for this entire block. Tucked cleanly inside the boundaries of this main container, we have nested a secondary section element node. Because this section tag sits directly inside the main wrapper, the browser maps it as a direct child node of the main element, while the main container is logged as its direct parent node. Now look inside the section node boundary, where the structural tree branches out even further. Here, we have nested two distinct elements, an H2 heading node displaying the text string structural node hierarchy chart, and a paragraph node containing our analytical text details. Because both the heading element and the paragraph element share the exact same parent section container and sit on the same horizontal layer of the markup architecture, the browser's parsing engine classifies them as sibling nodes. Simultaneously, the text characters inside those tags do not float freely. The parser wraps them into specialized text nodes nested cleanly within their respective element containers. If you look at the familial relationship from the very top, the heading and paragraph blocks are recognized as direct descendants of the root main element, while the main element serves as their ultimate ancestor node. Finally, we must emphasize a critical operational rule. You must never confuse your raw source code strings with this living memory graph. When you inspect a raw page source file, you are viewing a completely static text file that preserves every single coding mistake you make. Conversely, the DOM tree is a dynamic, auto-corrected memory model. If you drop a structural mistake into your source file, such as forgetting to close a tag boundary, the parser automatically fires its built-in fault tolerance loops to synthesize a closing node inside memory, completely masking your original syntax error inside the browser inspection tree. By masterfully managing your elements with a clear understanding of the live memory tree graph, you guarantee your code remains incredibly clean, performant, and structurally bulletproof across all environments. Chapter 2. The Text of HTML. Section 2.1. Headings and Paragraphs. Every text-based web page requires a clear, explicit structure so that browser parsing engines, search engine indexers, and assistive technologies can read and categorize data accurately. HTML achieves this by organizing plain text into block-level heading elements and paragraph elements. Let us look first at document headings. HTML provides exactly 6 tiers of headings to build a predictable informational layout. To construct a primary top-level heading, write a pair of angle brackets, and inside them, put H1. This forms your opening tag. Write out your heading text, and then close the element by writing a pair of angle brackets containing a / followed by H1. For lower subsections, you modify the token number sequentially, utilizing H2, H3, H4, H5, or H6. There are strict technical constraints you must follow when using headings. First, headings exist exclusively to establish a machine-readable document outline. They must never be implemented to alter visual font sizes or change text layout weights on the screen. If you require a heading to appear smaller or larger, that visual modification must be handled by an external stylus sheet, never by changing the tag tier. Second, you must always distribute headings in a strict mathematical sequence. Your page must begin with an H1 element to declare the primary subject of the document context. Any subsections directly underneath must transition sequentially to an H2 element. Skipping structural levels, such as jumping directly from an H1 element down to an H3 element, violates the technical specification. Doing so breaks the structural data map for screen readers, preventing users with visual impairments from navigating your text hierarchy efficiently. Next, let us look at how we isolate regular narrative text using the paragraph container. To implement this container, write a pair of angle brackets, and inside them, put the letter P. Input your block of sentences, and then terminate the boundary by writing a pair of angle brackets containing a / followed by P. The paragraph element follows specific layout rules. It is strictly categorized as a block-level element. When the browser parser encounters a block-level token, it automatically instructs the layout engine to allocate 100% of the horizontal width of the parent container to this specific block. The engine forces a line break immediately before the opening tag and immediately after the closing tag. The browser's built-in user agent stylesheet then automatically injects vertical spacing margins between adjacent paragraph nodes to ensure text groups remain separated. Finally, let us look at how to alter text flow without initializing a new heading or paragraph block. This is achieved using two specialized void elements, the line break and the thematic break. To execute a basic line break, write a pair of angle brackets, and inside them, put B. The BR element is a void element, meaning it cannot contain text content, and it does not use a closing tag. This element must only be implemented when a line wrap is an essential, permanent property of the text data itself, such as breaking up lines of poetic verse or formatting a physical postal address block. You must never use consecutive BR elements to force artificial vertical spacing between your paragraphs. Layout spacing must be handled strictly by structural element boundaries. To execute a thematic content break, write a pair of angle brackets, and inside them, put HR like the line break. The HR element is a void element that features no closing tag. Semantically, it denotes a complete macro shift or transition of context within a section of text. When the browser parser processes an HR element, it registers a thematic separation in the document outline, updating how assistive tools track separate content groups. By mastering these foundational blocks, you ensure your text remains perfectly structured and fully machine-readable. Let us combine these elements to look at a practical example of making a page fragment. Following our structural engineering workflow, we will always write our opening and closing tag pairs together first, and then place our content inside them. First, let us create our absolute primary title. Write a pair of angle brackets with H1 inside, and immediately follow it with a pair of angle brackets containing a / and H1. Now that the container boundaries are secure, go inside and put your text content, writing, quote, "Welcome to my history page," end quote. Directly below that heading, let us add our introductory paragraph. Write your opening and closing P tags together by putting a pair of angle brackets with P inside, followed immediately by a pair of angle brackets with a / and P inside. Move your cursor inside those text boundaries and write, quote, "This page documents major historical eras," end quote. Now, suppose we want to transition to a completely new subtopic on this page. We need to execute a thematic break to update our document outline. Right below your paragraph, write a pair of angle brackets, and inside them, put HR remember. Because this is a void element, it acts as a standalone marker, so you do not write a closing tag for it. Finally, let us establish our secondary subheading tier for the new content block. Write your opening and closing H2 tags together. Put a pair of angle brackets with H2 inside, and right next to it, put a pair of angle brackets with a / and H2. Go inside this freshly created container and write your subsection title, quote, "The Industrial Era," end quote. By assembling your text, lay out this way, structuring blocks sequentially, keeping your heading tiers in a strict mathematical sequence, and writing your tag pairs together before filling them, you create a perfectly formed, standard-compliant web page fragment. Section 2.2. Links the anchor element. Welcome to Section 2.2. Links. The anchor element. Hyperlinks are the defining structural feature of the World Wide Web, establishing the navigation mesh that allows users to fluidly traverse separate document paths. In HTML, these connections are initialized exclusively by the anchor element, which wraps around text characters or nested structural items to transform them into interactive nodes. Write a pair of angle brackets, and inside them, put the letter A to form your opening anchor tag. Right next to it, write another pair of angle brackets, and inside them, put a forward slash followed by the letter A to form your closing anchor tag. Now, let us configure the link destination by adding the required hypertext reference attribute inside the opening tag. Inside the opening bracket, right after the letter A, add a space. Type the letters href, followed by an equals sign and a pair of quotation marks. The destination address literal will be placed inside these quotes, and the interactive text will sit cleanly as stuff in between the opening and closing tags. Web architectures parse these paths using two targeting methodologies depending on where the file lives: relative links and absolute links. Relative links reference file assets located strictly inside the same project or local directory tree. They omit domain names completely, declaring a path relative to the current file. Inside your href quotation marks, you simply type the file name, like about.html. Absolute links point to resources hosted on completely separate external domains. This model requires the full target address string, meaning your href value must explicitly start with a network protocol tracker like http:// or https:// followed by the domain name. When organizing multi-page projects, you will look at three distinct directory traversal scenarios. In scenario 1, the target file is in the exact same directory folder. You only need to write the literal file name and its extension inside the quotes, like about.html. In scenario 2, the destination asset is nested down inside a subfolder. You declare the subfolder token name first, append a forward slash, and then type the target file name, such as pages/about.html. In scenario 3, the asset sits higher up in a parent folder. To jump out of your current folder, write .. inside the quotes. This double dot sequence instructs the parser to ascend exactly one parent directory boundary before looking for the file, allowing you to target paths like .. /blog/ post.html. Anchors can also perform internal document jumps to specific layout landmarks on the current page instead of loading a new file. First, go to your target element, like a heading, and assign it a unique identifier by writing the ID attribute set to contact inside its opening tag. Second, create an anchor link whose href value is set to #symbol contact. The #symbol explicitly marks it as a fragment identifier jump. You can also integrate non-web protocols using the anchor framework. To build an automated email trigger link, set the href property to the Mailto protocol scheme, directly followed by the destination email address, like mailto:/support@example.com. When clicked, it pauses browser execution to open the operating system's default email client pre-populated with that address. Furthermore, HTML parsing specs allow you to wrap the anchor tag around more than just simple string literals. You can encapsulate other clickable stuff. By writing your opening and closing anchor tags around entire structural layout divisions, headings, or nested content blocks, the parser maps those structural box boundaries into a singular interactive click zone. Now, let us examine advanced attributes for controlling browsing context and security. The target attribute specifies exactly where the linked document should open. Setting target equals _self, is the default state, loading the new asset in the current window frame. Setting target equals _blank, commands the engine to spawn a brand new window or tab context. When you use _blank, you must secure the link using the rel attribute, which declares the relationship between the pages. Historically, opening a new tab exposed the original window object via a memory hook. To isolate your execution threads, always add rel equals "nupener nor furrer" inside the opening tag, stopping malicious script inheritance across tabs. If you want to override inline rendering completely, add the download attribute. Instead of opening a resource like a PDF inside the viewport, this property forces the browser to intercept the stream and open its local file download management prompt. You can also provide resource prioritization hints. The reflang attribute declares the human language of the asset, while the type attribute specifies its formal media classification, allowing the network layer to inspect and optimize downloads early. For automated background metrics, the anchor node features a native tracking tool called the ping attribute. It accepts a space-separated list of fully qualified tracking server URLs. When a user triggers the link, the browser navigates to the destination href URL, while simultaneously firing an out-of-band, asynchronous HTTP post request to the listed tracking, addresses with a content type of text cross-ping. To govern how data paths are shared across domain transitions, use the referrer policy attribute. When navigating away from a page, the browser sends a header exposing the exact URL the user left. By configuring referrer policy to settings like no-referrer, you completely omit this metadata. Setting it to strict -origin- when -cross-origin ensures full path logs are shared internally within your domain, but only passes the base domain during external encrypted jumps, protecting user navigation history. Finally, we must address the JavaScript :void0 anti-pattern. A major architectural error is putting a JavaScript pseudo-protocol inside the href attribute to stop a link from navigating. The browser's internal parser registers an anchor with an href attribute as a formal navigation landmark and pushes it to accessibility trees with a link role assignment. If it runs a script switch instead of navigating documents, it breaks user expectations and ruins keyboard focus routines for assistive devices. The browser is forced to halt standard processing to compile a string script inside a location field. If an element exists solely to execute script logic, it must be built as an interactive form control, not an anchor link framework. Keep your document anchors clean, map them to real structural resources, and always secure your target boundaries. Section 2.3. Semantic versus visual-only text elements. Welcome to Section 2.3, Semantic versus visual-only text elements. To maintain strict structural integrity and clean accessibility trees, HTML classifies its text-level elements into two entirely different functional groups. The critical technical difference lies in exactly which layer of the browser's rendering engine they mutate. Semantic elements alter your internal metadata blueprint and the accessibility tree layout, whereas visual-only elements strictly alter the pixel paint operations of the graphical rasterizer. Let us break down our first major comparison: structural importance versus layout bolding, which is the strong element versus the B element. Following our engineering workflow, you should always write your opening and closing tags together first before adding text. To declare high importance, write a pair of angle brackets with the word strong inside to make your opening tag, and follow it immediately with a pair of angle brackets containing a / and the word strong to make your closing tag. Now, step inside those boundaries and add your content. While the browser's default user agent stylesheet paints this text with a bold typeface, its real job happens in memory. The strong element instructs the parser that the enclosed text carries high importance or urgency relative to the surrounding paragraph. When an assistive text-to-speech screen reader hits this node, it actively changes its vocal synthesis parameters, increasing auditory stress metrics like volume or pitch inflection. Search engine spiders also prioritize these character strings during indexing passes. Now, contrast this with the visual-only B element. Write your opening and closing B tags together by putting the letter B inside your first pair of angle brackets and a / followed by B inside the second pair. When you place text inside the B element, it commands the layout engine to apply a bold font weight parameter during the paint phase, but it communicates absolutely zero data value or priority shifts to the accessibility tree. A screen reader will read text wrapped in a B tag with the exact same vocal inflection and priority level as the surrounding plain text. It captures visual attention, but adds no metadata weight. Our second comparison is document revision tracking versus visual strikethrough, which is the del and ins elements versus the s element. Managing text modifications across historical document updates requires specialized tracking metadata that visual elements cannot replicate. To show that text has been formally removed from the document record, write your opening and closing del tags together first. Inside the opening tag, after the word del, add a space and configure the core metadata attributes. Type the word site, followed by an equals sign, and a URL string inside quotation marks pointing directly to the technical change log or ticket system authorizing the edit. Next, add a space, type the word datatime, followed by an equals sign, and an unambiguous machine-parsable ISO 860 timestamp inside quotation marks to document exactly when the revision occurred. To complement this, you use the ins element to mark text that has been formally inserted into the archive, configuration coded with its own matching site and datatime attributes. Now look at the visual-only alternative, the S element. Write your opening and closing S tags together and put text inside. This element simply instructs the rendering engine to pass a straight line-through vector path directly across the characters. It visually indicates that a text string is no longer accurate or relevant, such as an old, outdated price on a product catalog, but it carries 0 database modification history, 0 revision metrics, and does not register as a formal document edit in memory. Our third comparison is grammatical emphasis versus alternate prose voices, which is the M element versus the I element. To encode true linguistic emphasis that fundamentally alters the meaning of a sentence, write your opening and closing M tags together and place your targeted word inside. The M element changes the semantic metadata of the text, causing speech synthesis engines to immediately change their inflection parameters to place phonetic emphasis on that specific word token. To capture an alternate voice or technical prose variant without adding emphasis, use the I element. Write your opening and closing I tags together. The I element isolates distinct blocks of text that represent an alternate mood, tone, or linguistic classification, such as a foreign idiom, a taxonomic species classification, a ship's name, or an internal thought stream. The browser's default user agent stylesheet automatically paints this node using an italic layout font style, but it applies no vocal stress, no inflection modifications, and no structural importance within the accessibility ecosystem. By mastering the mechanical boundary lines between these text elements, you stop treating HTML as a visual layout tool. You explicitly separate your structural data metadata from your presentation layers, ensuring your files are clean, accessible, and perfectly parsed by every machine that reads them. Section 2.4. Lists. Welcome to Section 2.4, Lists. HTML provides specialized structural models designed to organize sequential or hierarchical data collections into clean block-level groupings. These models are split into linear itemized lists and associative key-value descriptive pairs. Let us look first at linear sequences, which are unordered lists and ordered lists. When organizing data items, the parsing engine categorizes them based on whether the structural sequence of the items changes the semantic meaning of your content. An unordered list is used when altering the sequence order does not change the core value or message of the data. To construct this element following our engineering workflow, write your opening and closing tag pairs together first. Write a pair of angle brackets, and inside them, put the letters UL to form your opening root tag. Right next to it, write another pair of angle brackets, and inside them, put a / followed by UL to form your closing root tag. Create a space in between them. When rendered, the browser's default stylesheet prefixes each item block inside this container with a filled bullet glyph. An ordered list is implemented when you are defining a procedural sequence, where the exact order of elements establishes a programmatic hierarchy or step-by-step logic. Write your opening and closing ordered list tags together by putting the letters OL inside your first pair of angle brackets, and a / followed by OL inside the second pair. The browser's default rule set automatically tracks, counts, and stamps sequential digits before each item block placed inside. To define an individual item block within either of these list structures, you use the list item element. Write your opening and closing list item tags together by putting the letters I inside a pair of angle brackets, followed by a pair of angle brackets with a / and L, I inside. Under the HTML specification, there is a strict parent-child constraint. An li tag cannot exist in isolation. It must reside strictly as a direct child node inside an unordered root UL container or an ordered root OL container. You can modify the index tracking states inside an ordered sequence using 3 specialized attributes declared inside the opening OL tag. The first is the start attribute. Add a space after the letters OL, type the word start, followed by an equals sign, and a signed integer value inside quotation marks. For example, setting start equals "5" forces the layout engine to compute the initial row index to 5 instead of 1. The second is the reversed attribute. This is a standalone Boolean attribute, meaning you simply type the word reversed inside the opening tag. This instructs the layout engine to count backwards from the calculated maximum sequence value instead of incrementing forwards. The third is the type attribute, which configures the typographic rendering scheme of your numbering indices. Type the word type, an equals sign, and one of 5 character values inside quotation marks. Using the number 1 sets decimal numerals. Using a lowercase sets lowercase alphabetical sequences. Using an uppercase A sets uppercase alphabetical sequences. Using a lowercase I sets lowercase Roman numerals. And using an uppercase I sets uppercase Roman numerals. Now let us look at our second major list model, description lists. To organize metadata pairings, structural specifications, or glossary vocabularies, HTML provides an associative model that maps definitions using specialized child keys instead of standard list items. To construct this framework, write your opening and closing description list root tags together first. Put the letters D, L inside your first pair of angle brackets, and a / followed by DL inside the second pair. This establishes the absolute parent boundary block for your metadata pairing tree. Inside this container, you will place pairs of terms and details. To define a term, keyword, or configuration variable acting as a lookup key, write your opening and closing description term tags together. Put the letters DT inside a pair of angle brackets, followed by a / and DT inside the next pair. Directly below that, to enclose the data values, definitions, or procedural blocks bound to that key, write your opening and closing description details tags together. Put the letters D inside a pair of angle brackets, followed by a / and DD inside the next pair. Under specification rules, a single term key can possess multiple description details blocks, and multiple term keys can point to a single description details block. Finally, let us master structural nesting and tree validation rules. Building multi-tier list structures requires strict adherence to element relationship constraints to prevent parsing failures in the active document object model tree. The absolute law of nesting states that a list root container, like a UL or an OL tag, can only possess list item I elements as its immediate child boundaries. You can never nest a secondary list root directly between the boundaries of a primary list root. Instead, to create a nested subsection layout, the inner list structure must live completely inside an individual LI container block. To build a nested sequence cleanly, write your outer ordered list root tag pair. Inside that, write an LI tag pair containing your first step text. Below that, write a second LI tag pair and type your second step text. While still inside that second LI container, directly below its text content, initialize a brand new opening and closing unordered list tag pair. Inside this inner UL container, place your nested LI tag pairs to declare your substeps. Close your inner UL container, and only then close your outer second LI container. By keeping your structures cleanly grouped, and always writing your tag pairs together before filling them, you ensure your hierarchical lists compile perfectly into a flawless data tree graph. Section 2.5. Walkthrough of Advanced Semantic Text and Media Components. Welcome to Section 2.5, Walkthrough of Advanced Semantic Text and Media Components. While standard text containers organize general content paragraphs, highly specified informational nodes, bridge the gap between raw human language and machine parsable data. These advanced semantic components provide precise structural context for quotes, abbreviations, database values, international text flow configurations, and self-contained media blocks. Let us walk through these essential elements piece by piece, continuing our strict engineering workflow of initializing our opening and closing tag pairs together before populating them with content. First, let us examine the layout architecture for handling quotations and source citations. HTML separates these into three distinct elements depending on whether you are marking a title, an inline quote, or an independent text block. To reference the literal title of a creative work, such as a book, a research paper, or a technical specification sheet, you use the citation element. Write a pair of angle brackets, and inside them, put the letters CIT to form your opening tag. Right next to it, write another pair of angle brackets, and inside them, put a / followed by CIT to form your closing tag. Step inside and place your text. Remember, this element must strictly contain only the title of the work itself, never the name of the author or the publishing platform. By default, the browser engine paints this text string using an italic layout font style. To encapsulate a short, inline quotation segment within a running sentence, use the inline quotation element. Write your opening and closing tags together by putting the single letter Q inside your first pair of angle brackets, and a / followed by Q inside the second pair. When placing text inside, you must never manually type quotation mark characters into your source file. The browser's parsing engine reads the root language attribute of your document and automatically generates the correct, localized typographical quotation, glyphs around your text. To isolate a large, independent, block-level section of text cloned from an external resource, use the block quotation element. Write your opening and closing tags together. Put the word block quote inside a pair of angle brackets, followed immediately by a pair of angle brackets with a / and the word block quote. To make this block valid in your metadata tree, you must configure its citation source attribute inside the opening tag. Inside that opening bracket, after the word block quote, add a space. Type the letters href wait, excuse me, type the letters CIT, followed by an equals sign, and a fully qualified source URL inside quotation marks. This structural reference is processed silently by automated search indexers and remains completely invisible to users on the visual painted canvas. Second, let us walk through elements used for textual clarification and structural landmarks, definitions, abbreviations, and contact channels. To mark the absolute defining instance of a new term within a paragraph, use the definition element. Write your opening and closing tags together by putting the letters DFN inside your first pair of angle brackets and a / followed by DFN inside the second pair. The surrounding narrative paragraph block must contain the actual explicit definition string, explaining the term wrapped inside this container. To mark an acronym or text abbreviation, use the abbreviation element. Write your opening and closing tags together. Put the letters ABBR inside a pair of angle brackets, and follow it with a pair of angle brackets containing a / and a BBR. This container relies entirely on the configuration of the global title attribute. Inside the opening tag, after the letters ABBR, add a space, type the word title, an equals sign, and a pair of quotation marks. Inside these quotes, you must type out the exact, full expanded plain text description of the short-form acronym. When a user hovers their cursor over this element on the page, the layout engine spawns a native tooltip panel displaying this expansion text. To establish a specialized semantic landmark that houses contact channels for an author, use the address element. Write your opening and closing tags together by putting the word address inside a pair of angle brackets, followed by a pair of angle brackets with a / and the word address inside. This container must exclusively house contact links, digital mail links, phone number integers, or physical location routes. It must never contain general calendar dates or random biographical text. If placed directly inside the document body root, it applies globally to the entire web page owner. Third, let us look at machine parsing intersect elements, which translate human text into exact database data blocks. To link a human-readable text description with a clean tracking token for background scripts, use the data element. Write your opening and closing tags together. Put the word data inside a pair of angle brackets, followed by a /, and the word data inside the next pair. This element mandates the implementation of the value attribute. Inside the opening tag, after the word data, add a space, type the word value, an equals sign, and a pair of quotation marks. Inside these quotes, you place your raw backend database keys or inventory product serial strings, leaving the visual canvas clean for human readers. To convert variable human calendar phrases, like, quote, next Tuesday afternoon, end quote, into absolute data objects, use the time element. Write your opening and closing tags together by putting the word time inside a pair of angle brackets, followed by a /, and the word time inside the next pair. This element relies entirely on the configuration of the data time attribute. Inside the opening tag, after the word time, add a space, type the letters D, a TIME, an equals sign, and a pair of quotation marks. Inside these quotes, you must write out the date using the strict formatting rules of the ISO 8601 calendar system, which tracks exact years, months, days, and hours separated by standard markers. Fourth, let us look at bidirectional processing elements for managing languages that render in conflicting screen directions, such as mixing left-to-right English with right-to-left Arabic or Hebrew. When pulling dynamic, user-generated string content from an external database where the language direction is completely unknown, you must wrap it in a bidirectional isolation element to protect your layout. Write your opening and closing tags together. Put the letters BD, I inside a pair of angle brackets, and follow it with a / and BDI inside the next pair. The BDI element acts as an absolute structural wall in memory. It completely insulates its enclosed characters from the text direction parameters of the surrounding paragraphs, stopping external language data from flipping or corrupting your layout order. If you need to force a hard-coded text direction reversal onto a specific string, use the bidirectional override element. Write your opening and closing tags together by putting the letters BDO inside a pair of angle brackets, followed by a / and BDO inside the next pair. This element requires you to explicitly set its direction rule. Inside the opening tag, after the letters BDO, add a space, type the letters DIR, an equals sign, and a pair of quotation marks. To force characters to render starting from the right side of the screen, type the letters RTL inside the quotes. To force them to start from the left, type LTR. Alternatively, you can apply the automated direction switch to any element opening tag as a local attribute. Simply add a space inside the tag, type the letters D, IR, an equals sign, and the word auto inside quotation marks. This instructs the browser's engine to perform a rapid first byte analysis on the text stream, automatically switching the rendering direction to match the primary language properties it detects. Fifth and finally, let us examine self-contained media containers used for charts, code blocks, or diagrams. To group a reference component that connects to your narrative but can be safely moved away into a sidebar or appendix without breaking the meaning of your document outline, use the figure element. Write your opening and closing tags together. Put the word figure inside a pair of angle brackets, followed by a / and the word figure inside the next pair. To bind an explicit text explanation or descriptive title directly to this media block, use the media caption element. Write your opening and closing tags together. Put the letters FIGCAPTION inside a pair of angle brackets, followed by a / and FIGCAPTION inside the next pair. To maintain strict document tree validation, this caption element must live inside your figure container block as either its absolute first child node or its absolute last child node. You are never allowed to insert more than one caption element inside a single figure block. By mastering these advanced structural hooks and configuration attributes, you transform plain text streams into highly specified, machine parsable, and globally accessible data trees. Section 2.5. Code, Performatted, and Computer Output Elements. Add-on 2.5, Spoken Video Script, Verified Workflow and Plain Text Edition. Welcome to Add-on 2.5, Code, Performatted, and Computer Output Elements. In this lesson, we are unlocking a powerful suite of native text-level elements engineered to handle advanced typography, technical system data streams, and complex phonetic character annotations completely natively inside our document trees. Up to this point in our course, we have focused on standard paragraphs and headings that format everyday language. However, when you are building technical documentation, displaying programming tutorials, or writing out complex scientific formulas, regular prose layouts fall completely short. A standard paragraph will automatically compress consecutive spaces, hide tabs, and discard literal line breaks down to a single whitespace block. Furthermore, assistive technologies require explicit semantic boundaries to differentiate between standard sentences, raw program files, manual keyboard inputs, and system terminal displays. HTML completely resolves these layout boundaries by providing specialized containers that preserve text geometries and announce structural meanings perfectly to the browser engine, without needing presentation layer alterations. Let us analyze the operational mechanics of our first major category, the computer output and ingestion subsystem. This framework relies on 5 distinct inline structures: code, pre, KBD, SAMP, and var. The code element wraps short syntax loops, rendering them inline using a clean monospace font mask while mapping the text as an explicit programming code fragment to screen readers. The pre-element, short for performatted text, functions as a block-level container that commands the browser engine to preserve every single tab, indent, space, and line return exactly as you type it in the source repository. When you need to display an entire multi-line script file, you combine these rules by nesting a clean code element straight inside a master pre-container. To track system interactions, we deploy the KBD and SAMP elements. The KBD element flags explicit manual keyboard key sequences or voice triggers, while the SAMP element maps sample output text returned by a terminal command or a server routine. To represent a user typing a command into a system terminal console, advanced development setups nest the KBD tag directly inside the SAMP container. To complete this technical space, we implement the var element, which isolates variables inside programmatic statements or mathematical expressions, rendering them with a clean italicized typographic adjustment that signals its variable status directly to automated parsing scripts. Beyond computer outputs, HTML builds a highly specialized set of markers to manage contextual document emphasis and structural baseline shifts. The mark element highlights text runs based on immediate user activity relevance, such as highlighting search match phrases across an article tree. It is a critical semantic tool that explicitly announces matching priorities to visually impaired users, meaning it must never be used just to paint decorative visual colors. The small element downgrades text priority, mapping text runs as disclaimers, side comments, or copyright lines. The U element handles unarticulated annotations, completely shedding its legacy identity as a visual underline tag to serve as an explicit marker to flag technical spelling mistakes or grammatical defects directly within the markup tree. To handle advanced alignment mechanics, we implement the sub, sup, and WBR elements. The sub and sup elements handle subscript and superscript layouts, shifting characters safely below or above the document text baseline to format chemical symbols like H2O or exponential equations like E=mc² natively. The WBR tag represents a word break opportunity. It is a conforming standalone void element that marks a safe layout break position where the rendering engine can drop an ultra-long URL link to a new line on narrow mobile viewports, eliminating container overflow bugs completely. Finally, we master the advanced multi-tier Ruby subsystem, which handles specialized East Asian typography layouts like furigana or pinyin. This system utilizes a 3-part tag structure containing the Ruby, RT, and RP elements, The master Ruby container groups the base character ideograph with its annotations. The RT element houses the tiny phonetic pronunciation character that floats directly above the base canvas word. The RP element acts as a brilliant structural fallback wrapper that places standard parentheses around the Ruby text. If a legacy device or specialized browser lacks the layout physics to display Ruby annotations above text, it automatically drops the layout rules and renders the parentheses inline, keeping the text readable across all legacy computing environments. Section 2.6. Character Escaping and Entities. Welcome to Section 2.6, Character Escaping and Entities. In this lesson, we are conducting a deep architectural exploration into the browser's internal tokenization mechanics to master exactly how to print literal punctuation symbols safely without breaking our core HTML code trees. To understand why character escaping is a non-negotiable requirement for industrial-grade web development, we must look at what occurs inside the browser rendering engine's finite state machine. As the engine consumes your HTML text stream byte by byte, it relies on specific characters as immediate switches to alter its parsing behavior. Look at our state machine transition diagram on screen. You can see exactly how the default data state branches outward into unique compilation, loops the exact moment specialized characters are scanned. The 5 reserved characters and reference systems. The HTML parsing engine monitors 5 specific reserved characters that instantly change its reading state. The less than sign forces an immediate transition from standard data collection straight into a tag open state, where the engine expects the following characters to be a valid element token like P or div. The greater than sign terminates an open tag configuration bracket, signaling to the parser that it should seal the current node properties and return to collecting raw body data. The ampersand shifts the tokenizer instantly into a character reference lookup loop, signaling that a specialized text sequence follows. Finally, double and single quotes mark the explicit boundaries of attribute values. Dropping a raw quote inside a value string breaks the boundary wall prematurely, causing the remaining text to parse as illegal, broken attributes. To render these symbols as visual text glyphs, we employ 3 character reference systems. First, named character entities provide human-readable, case-sensitive text shortcuts. They must always begin with an ampersand and terminate with a semicolon. We write ampersand LT semicolon for the less than sign, ampersand GT semicolon for the greater than sign, ampersand a MP semicolon for a literal ampersand, ampersand QUOT semicolon for double quotes, and ampersand a POS semicolon for a single quote apostrophe. Second, decimal numeric references map directly to the Unicode database using standard base 10 numbers. They bypass text names entirely by using the prefix ampersand followed by a hashtag, such as ampersand hashtag 60 semicolon, to resolve the less than sign. Third, hexadecimal numeric references target base 16 Unicode addresses using the prefix ampersand, hashtag, and a lowercase letter x. We write ampersand hashtag x3c semicolon for the less than sign, or ampersand hashtag x, a 9 semicolon for the global copyright protection symbol. Contextual processing rules. The necessity of escaping shifts dynamically based on the document zone the parser is reading. In normal body text, escaping less than signs and ampersands is completely mandatory to prevent tag opening errors and reference failures. Inside attribute values, escaping ampersands remains mandatory, while quotes must be escaped conditionally. If your master attribute value string is wrapped in double quotes, any inner double quotes must be written as the double quote entity to prevent breaking the container string wall. When the parser enters specialized zones like raw text, mode inside script, or style elements, all character references are completely neutralized, meaning typing out an entity will print out literally as 5 individual text characters. However, when the engine hits an escapable raw text zone like a textaria form box or a title metadata block, it ignores tag tokens, but actively processes character references, transforming entity codes safely into clean visual glyphs inside the user viewport canvas. Textual breakdown of production code cases. Let us analyze our first textual code implementation, which demonstrates how to safely escape reserved syntax tokens within normal body text blocks. Instead of an executed code block, visualize a standard paragraph container. We open the paragraph tag normally. Inside the text body, we write out the text. Verify that array indicator alpha, followed immediately by two consecutive named ampersand entities, written as ampersand a MP semicolon, ampersand a MP semicolon. We continue the sentence text, and indicator beta are evaluated, ensuring that total structural block constraints remain, followed by the named less than entity, written as ampersand LT semicolon. We finish the text string with the words maximum parameters and smoothly lock down the layout by writing the standard closing paragraph tag. In this structure, if we had left the logical double ampersands and the mathematical less than sign raw, the parser would drop its text collection loops, assume a tag was opening, and corrupt the DOM tree. By replacing them with their explicit named text entities, the tokenizer passes the characters cleanly into system memory as flat visual text characters, without misinterpreting them as code operations. Let us look at our second textual code implementation, showcasing how to safely handle quote boundaries inside interactive attribute configurations. Visualize an interactive, standalone input void element tag. We open the single bracket and write the element name input. We add a space and set its operational type attribute equals double quote text double quote. We add a space and map its tracking handle ID equals double quote syntax field double quote. Now, we add a space and declare our explicit value property. We write value equals double quote, and inside these master double quotes, we type the text string. Declaring an explicit, followed immediately by the named double quote entity ampersand QUOT semicolon. We write the character's ID, follow it right next to it with another ampersand QUOT semicolon, and finish the value string text by typing token parameter. We then seal the entire value attribute with a final master double quote and close the single element bracket block. Here, because the value attribute is wrapped in standard double quotation marks, dropping raw double quotes around the word ID would instantly break the attribute open, cutting off the value string and spawning a major parsing defect. By converting those inner quotes into the explicit text entity ampersand QUOT semicolon, we keep the outer attribute string perfectly secure while instructing the viewport to render beautiful literal quotation marks around the word ID on the final page layout. By mastering these explicit character escaping ecosystems and managing your code contexts with this highly disciplined approach, you deliver an industrial-grade, error-free markup architecture that executes perfectly across all modern browsing environments. Chapter 3. Sectioning and Semantic Structure. Section 3.1. The sectioning elements, IDs, and classes. While text elements organize words inside a paragraph, semantic sectioning elements provide massive data wrappers that divide your entire document into clear, machine-readable operational zones. These structural elements act as explicit landmarks within the browser's accessibility tree, allowing screen reader devices and search crawlers to index and jump directly to specific content regions. When you transition from writing simple single-page web forms to architecting massive enterprise-scale software configurations with hundreds of developers handling millions of lines of code, standard document format boundaries become your primary defense against code-base degradation. In huge projects, improper formatting creates structural chaos, commonly known as division soup, where every layout container is an unmarked, generic box. This makes files completely unreadable to peer engineers who inherit your repository files. By executing a strict semantic baseline paired with identifiers and classifications, you build a clean architectural map that enables massive engineering teams to move fast, locate layout files instantly, and scale applications safely. Before we walk through these structural containers, let us introduce two powerful global configuration tools that allow professional programmers to identify, group, and track any block within a vast project repository. The unique identifier attribute, known as ID, and the classification group attribute, known as class. Following our structural engineering workflow, you should always write your bracket pairs together first, and then declare these configuration properties directly inside the first pair of brackets. Let us look first at the unique identifier attribute. The letters ID stand for identifier. It is used to give a single, specific element a completely unique name within your document tree. The absolute rule of engagement here is that an ID name can only be used exactly once per page layer. No two elements on the exact same page can ever share the same ID name. In massive projects, developers use unique IDs as strict, high-priority targets. To apply a unique identifier, go inside the first pair of angle brackets of an element, right after the element name, add a space, write the letters ID, an equals sign, and your unique name string inside a pair of quotation marks. Now, let us integrate these attributes as we build our core semantic sectioning landmarks piece by piece, continuing our rule of setting up our brackets together first before adding our text content inside. This structural discipline is exactly what keeps massive systems clean. First, to wrap the dominant, unique content of your web page, we establish the main core. Write a pair of angle brackets, and inside them, put the word main. Right next to it, write another pair of angle brackets, and inside them, put a / followed by the word main. Now, create a space for your content in between them. Let us give it a unique identifier so that automated system deployment checks can track it instantly. Go inside that first pair of angle brackets, right after the word main, add a space, and write ID, an equals sign, and the word core inside quotation marks. Every single document layer must feature exactly one visible main element, and it must completely omit data repeated across other pages, like global navigation links or copyright footers. Second, to group your primary clusters of hyperlink paths, we use the navigation landmark. Write a pair of angle brackets, and inside them, put the letters NAV right next to it. Write another pair of angle brackets, and inside them, put a / followed by NAV. Let us categorize this navigation block under a shared group layout. Inside that first pair of angle brackets, after NAV, add a space, and write class, an equals sign, and the words primary -menu inside quotation marks. This landmark is reserved exclusively for major navigation blocks, such as your main site headers or an extensive table of contents index list. Third, to establish introductory or concluding zones, HTML provides header and footer elements. Both can live multiple times across a single document tree. To build an introductory zone, write a pair of angle brackets, and inside them, put the word header. Right next to it, write another pair of angle brackets, and inside them, put a / followed by the word header. If this is the global site header at the very top of a massive app, go inside that first pair of angle brackets, after the word header, add a space, and write ID, an equals sign, and the words main -header inside quotation marks. To build a concluding metadata zone, write a pair of angle brackets, and inside them, put the word footer. Right next to it, write another pair of angle brackets, and inside them, put a / followed by the word footer. To classify this block under a shared category, go inside that first pair of angle brackets, after the word footer, add a space, and write class, an equals sign, and the words document -footer inside quotation marks. When placed at the root of your document, these elements act globally. When nested inside a specific article or section, their scope narrows completely, acting strictly as the header or footer metadata block for that individual node. Fourth, to organize related streams of data that lack a more specific semantic tag, we use the section element. Write a pair of angle brackets, and inside them, put the word section. Right next to it, write another pair of angle brackets, and inside them, put a / followed by the word section. To configure this block cleanly with an identifier, go inside that first pair of angle brackets, after the word section, add a space, and write ID, an equals sign, and the words chapter -1 inside quotation marks. Remember this absolute rule. A section element must never be used as a generic empty box for visual styling. To be structurally valid within the document tree, a section node must always feature an explicit heading anchor inside its boundaries to define its theme to the parser. Fifth, to encapsulate a completely self-contained, independent composition designed to be logically reusable or detachable from the main document outline, we use the article element. Write a pair of angle brackets, and inside them, put the word article. Right next to it, write another pair of angle brackets, and inside them, put a forward slash followed by the word article. Let us classify this block as a modular item. Go inside that first pair of angle brackets, after the word article, add a space, and write class, an equals sign, and the words journal-entry inside quotation marks. This container maps perfectly to independent database objects, such as distinct blog posts, newspaper articles, or isolated user comment block. Sixth, to isolate content that is only tangentially related to the main narrative stream surrounding it, we use the aside element. Write a pair of angle brackets, and inside them, put the word aside. Right next to it, write another pair of angle brackets, and inside them, put a forward slash followed by the word aside. To identify this block uniquely, go inside that first pair of angle brackets, after the word aside, add a space, and write ID, an equals sign, and the words quick-facts inside quotation marks. When nested inside an article node, it functions as an internal callout box or glossary definition list. When positioned outside article boundaries at the root level, it functions as a global sidebar housing site advertisements or related resource recommendations. Seventh, to lock a multi-tier heading sequence together within the document tree without creating unwanted extra nested levels or subsections in the page structure, we use the heading group element. Write a pair of angle brackets, and inside them, put the letters HGROUP right next to it. Write another pair of angle brackets, and inside them, put a forward slash followed by HGROUP. This container wraps a main heading tag alongside secondary taglines or subheadings, keeping them cleanly unified in system memory. Eighth and finally, to mark the explicit search, filtering, or discovery zone of your document context, we use the search element. Write a pair of angle brackets and inside them, put the word search. Right next to it, write another pair of angle brackets and inside them, put a forward slash followed by the word search. To classify this landmark zone, go inside that first pair of angle brackets, after the word search, add a space, and write class, an equals sign, and the words utility-lookup inside quotation marks. This container must explicitly encapsulate your input elements and search form structures used to query your local databases or site indexes. By anchoring your immense systems with these explicit architectural landmarks, you completely eliminate structure tracking failures. When a new developer handles your code 2 years from now, they will not be searching through thousands of unmarked, nested boxes. They will look straight at the semantic framework, map the classes instantly, and run automated script updates with absolute structural confidence. Section 3.2. The document outline in reality. Welcome to Section 3.2, the document outline in reality. In this lesson, we are going to look under the hood of the browser's parsing engine to understand how a web page builds its internal layout hierarchy. This structural framework is exposed to search engines and assistive technologies as a document outline tree. When HTML5 was introduced, it attempted to completely automate how this outline was calculated. However, a massive gap emerged between the theoretical specification and the real-world execution of browser engines. Let us walk through exactly how this processing mechanics works in production environments. First, let us look at the rise and fall of the theoretical outline algorithm. To fully master document architecture, you need to understand why a heavily advertised feature of modern HTML completely failed to achieve operational deployment. The original HTML5 specification creators introduced an automated compilation mechanism known as the HTML5 outline algorithm. Their vision was to make web components completely modular. The specification declared that sectioning containers such as the section element, the article element, the nav element, and the aside element would create an isolated local scoping barrier in the browser's memory. Under this theoretical vision, a programmer could write a primary H1 element inside a newly nested section container, and the browser's parsing engine would automatically lower its structural importance based entirely on its nesting depth in the tree. For example, if you wrote an H1 element inside a section block that lived inside an article block, the browser was supposed to dynamically treat that heading as an H3 in the final document outline. This was intended to eliminate the need for developers to manually track numeric heading levels from H2 through H6. However, browser software developers and assistive screen reader vendors completely bypassed implementing this automated algorithm. First, tracking and continuously remapping dynamic node depths in system memory every time an element was added, moved, or deleted introduced a severe processing drag to the rendering pipeline. Second, activating this algorithm retroactively would have broken the structural layouts of millions of legacy websites that already used sectioning elements incorrectly without headings. Third, screen reader software rejected the algorithm because their users relied on strict, unchanging numeric heading commands to navigate web page context safely. As a result of this universal industry rejection, the automated outline algorithm was completely removed from the official HTML Living Standard specification. Second, let us examine the persistence of the implicit heading outline. Because that automated algorithm does not exist in real-world web browsers, your document outline is determined entirely and exclusively by the literal numeric value of your heading tags, from H1 through H6. The parsing engine reads your heading tokens sequentially as they appear in the character data stream to construct an implicit tree hierarchy. Sectioning wrappers like section or article create highly valuable landmark zones in the accessibility tree, but they exert absolutely zero structural control over the heading levels themselves. If you drop an H1 tag inside 5 layers of section blocks, the browser DOM tree still registers that text as a top-level primary page anchor, which breaks your semantic data structure. Third, let us master parsing constraints and architectural best practices. To ensure your document compiles into a clean, professional data tree, you must enforce strict engineering rules within your repositories. The first rule is the strict single H1 constraint. A standard-compliant web page layout must feature exactly one single H1 element per document layer. The H1 node serves as the absolute root title anchor for the entire page context. Initializing multiple H1 nodes splits the primary entry point of your structure, which fragments the data map for search indexers and breaks screen reader navigation loops. The second rule is the sequential tiers rule. Heading elements must progress in a strict, unskipped mathematical order. Skipping heading levels such as dropping from an H2 directly down to an H4 because you want a smaller default font size on the screen is a serious parsing error. It creates a broken, unnamed node vacancy in the document outline tree. If a subsection requires a smaller visual display on the interface, that presentation change must be handled completely by style rules, while your HTML tag remains tightly locked to its correct sequential numeric tier. Let us do a complete spoken walkthrough of a prototypical, perfectly compliant outline architecture fragment, applying our engineering workflow of initializing our opening and closing tag pairs together before populating them. Imagine our structure beginning inside our main stage core. First, let us establish our absolute global page title. Write a pair of angle brackets, and inside them, put the letters H1 to make your opening tag. Right next to it, write a pair of angle brackets with a / and H1 inside to close it. Step inside these boundaries and write your title text, quote, main system dashboard, end quote. Directly below that primary title, let us open a standalone thematic block. Write your opening and closing section tags together. Put a pair of angle brackets with the word section inside, and right next to it, put a pair of angle brackets with a / and the word section. Let us give it a unique name by adding a space inside the opening tag, followed by ID, an equals sign, and the words hardware-metrics inside quotation marks. Now, we must immediately anchor this section with its correct sequential heading tier. Since our main title was an H1, this section requires an H2. Inside your section boundaries, write your opening and closing H2 tags together by putting H2 inside your first pair of angle brackets, and a forward slash followed by H2 inside the second pair. Go inside this container and type your primary chapter text, quote, 1.0, hardware telemetry, end quote. Directly below this heading, open and close a P tag pair and input your narrative prose text block. Next, suppose we want to place an independent, reusable subcomponent inside this hardware section. Directly below your paragraph, write your opening and closing article tags together. To organize our hierarchy perfectly, this subcomponent needs an H3 heading anchor. Inside your article boundaries, write your opening and closing H3 tags together. Put H3 inside a pair of angle brackets, and follow it with a pair of angle brackets containing a forward slash and H3. Step inside this inner container and type your subsection title, quote, 1.1, Central Processing Unit, end quote. Below this H3, open and close a P tag pair to house your granular data report text. Finally, let us add a second parallel subcomponent inside the same section block. Directly below your closed article tag, write a brand new opening and closing article tag pair. Since this block sits at the exact same hierarchical level as our processing unit, it also requires an H3 heading anchor. Write your opening and closing H3 tags together inside this second article. Step inside and type your parallel title text, quote, 1.2, Core Memory Arrays, end quote. Below it, open and close your P tag pair to input your final memory log prose. By executing your document structure this way, locking your landmarks to the correct sequential tiers, avoiding the myth of automated rescoping, and keeping your tag pairs securely unified, you build a flawless, machine-readable outline map that navigates perfectly across every system on the web. Section 3.3. Putting it together. Welcome to Section 3.3, Putting it together. In this lesson, we will execute a complete spoken walkthrough of an enterprise-grade production scaffolding blueprint. When you transition from writing simple single-page web forms to architecting massive software applications with multi-team workflows, maintaining a strict structural hierarchy is your absolute primary defense against codebase degradation. It ensures that professional programmers can locate layout zones instantly, avoid structural bugs, and scale systems safely without drowning in unmarked container boxes. Let us walk through how these advanced landmarks, unique identifiers, and component classifications interlock cleanly in memory, without using a single raw code block, spelling out every single element from top to bottom so you can visualize the entire framework perfectly. Imagine our file data stream starting at the absolute top of a massive repository file on line 1. We write our less than sign, an exclamation point, the word DOCTYPE in all capital letters, a space, the word HTML in lowercase, and a greater than sign to force the browser engine into its strict standards mode rendering pipeline. On line 2, we initialize our root layer by writing a less than sign, the letters HTML, a space, the word LNG, an equals sign, and the language token string quote en unquote inside quotation marks, followed by a greater than sign. Directly below, we create our non-visual configuration zone by opening and closing our head tag pair together. And inside those boundaries, we place our character encoding meta tag set to UTF-8 and our descriptive page title tag container. At the absolute top of our visible stage, we establish our global site header area, which acts as a master banner for the entire website application. We open our header tag and set its attributes by adding a space after the word header, typing the letters ID, an equals sign, and the unique name string quote main hyphen header unquote inside quotation marks. Next, we add a space, write the word CLSS, an equals sign, and the classification group string quote site hyphen banner unquote inside quotation marks, before closing the opening angle bracket with a greater than sign. Right next to it, we write our closing header tag with a forward slash. Inside this global header zone, we place our absolute primary page title by opening and closing our H1 tag pair together, filling it with the text content quote global systems command unquote. Directly below that primary title, Still inside our global header, we add our major site navigation matrix. We open our nav tag and configure its properties by adding a space, setting its ID attribute to global-nav, and setting its CLOSS attribute to navigation-matrix. Inside this nav container, you would write out your sequential unordered list and anchor link paths to route users across different application network directories before closing your nav tag and closing your global header block completely. Right below that closed global header block, we add our discovery landmark zone to handle search functions. We open our search tag, add a space, and set its ID attribute to registry-search, and its CLOSS attribute to utility-lookup. Then we write our closing search tag right next to it. Inside this search landmark, we wrap an interactive form element containing an input tag with its type set to search, a name attribute set to query, a placeholder attribute set to enter component ID, and an explicit human-readable label container with the CLOSS set to form-label to ensure accessibility subsystems can map the lookup field cleanly. Now, we initialize our dominant content core stage, where the completely unique data assets of this individual web page reside. Below the closed search tag, we open our main tag, add a space, and configure its attributes by setting its ID to primary-stage, and its CLOSS to content-core, and we follow it with our closing main tag pair, creating a large operational zone inside. Every single piece of structural text or media unique to this specific URL must live as content in between these two main tags. Let us add our first regional thematic block inside our main stage core to display our analytics data. We open our section tag, add a space, and set its unique identifier ID attribute to system-metrics, and its classification CLOSS attribute to dashboard-region, followed by its closing section tag pair. To ensure this region compiles as a valid, named node inside the document outline for peer programmers and indexing crawlers, we must immediately anchor it with a heading. Inside your section boundaries, we open and close an H2 tag pair together, populating it with our primary chapter text string 1.0, real-time system metrics. Directly below this heading, we open and close a paragraph p tag pair configured with its CLOSS, set to region-description to house our section overview narrative prose text. Suppose we want to place a modular, reusable data component inside this metrics section to isolate a specific cluster report. Directly below our description paragraph, we establish an independent composition container by opening our article tag, adding a space, and setting its unique ID to node-alpha-report, and its component CLOSS to journal-entry component-card, followed by its closing article tag pair. To give this individual component its own self-contained metadata layout, we open and close a secondary inner header tag pair right inside the article boundaries, using a CLOSS attribute set to component-header. Inside this component-level header, we write our heading tag by opening and closing an H3 tag pair together, typing our sequential subsection title 1.1, cluster node alpha telemetry log, and right underneath it, we place a small paragraph container holding our author metadata text with the CLOSS attribute set to author-metadata. Below this inner header block, we write our main article prose by opening and closing a standard p-tag pair configured with the CLOSS attribute set to component-prose, filling it with text describing our core, parsing engine memory state and buffer allocations. Finally, we finish the article block by opening and closing a secondary component-level footer tag pair with its CLOSS set to component-footer, which wraps an inner paragraph securely housing our machine-readable revision timestamp strings configured with the CLOSS set to revision-timestamp. To add a parallel component instance for a second cluster node right below it, an engineer simply duplicates this entire self-contained article structure, changing its unique ID attribute to node-beta-report, and updating the H3 heading text to read 1.2, cluster node beta telemetry log. Right below these closed article components, we reach the end of our first regional block, so we verify that our primary section tag is securely closed. Now, let us add a second thematic block inside our main stage core to map out our network configurations. We open a brand new section tag pair, adding a space inside the opening brackets to set its ID attribute to quote network hyphen topology unquote, and its CLOSS attribute to quote dashboard hyphen region unquote. We anchor it immediately by opening and closing an H2 tag pair together, containing our second major chapter text quote 2.0, global network topology maps unquote, followed by a brief descriptive paragraph box with the CLOSS attribute set to quote region hyphen description unquote. Inside this second section, we want to isolate a distinct block of text that is only tangentially related to the topology map. We open our aside tag, add a space, and set its unique identifier ID to quote security hyphen notice unquote and its CLOSS group to quote sidebar hyphen notice callout hyphen box unquote, followed by its closing aside tag pair. Inside this isolated aside block, we write our opening and closing H4 tags together to type our warning title text quote cross-origin security protocol warning unquote. And directly below it, we open and close a p-tag pair with the CLOSS set to quote notice hyphen pros unquote to input our detailed security protocol notice pros. Now we close our second regional section tag completely. We are now back out in the root of our main stage container, so we write our closing main tag, which completely locks down our unique content core layer. Finally, at the absolute bottom of our visible stage, right below the closed main tag, and right before the final closing body tag, we establish our global site footer area to wrap our licensing information. We open our footer tag, add a space, and configure its properties by setting its unique ID to quote global hyphen footer unquote, and its CLOSS to quote document hyphen footer unquote, followed immediately by its closing footer tag pair. Inside this global footer, we open and close a final paragraph p-tag pair with its CLOSS set to quote copyright hyphen statement unquote, and we write out our corporate copyright assertions and technical specification standard compliance text. Below this footer sits your final closing body tag, and directly below that sits your final closing HTML root tag that we initialized at the very beginning of our file. Let us analyze the critical architectural concept of multi-tiered nested scopes and reusable elements that we just visualized in our blueprint walkthrough. A major source of structural confusion for junior developers on massive enterprise development teams is the valid reuse of structural layout tags like header and footer multiple times across a single document tree. If you visualize a structural map of a multi-tiered document tree, you can see global headers and footers sitting at the absolute root boundaries of the page, contrasted against component-scoped headers and footers nested deeply inside individual article cards. The absolute law of web document engineering is that the semantic meaning of these elements changes completely based on where they reside in your tree architecture hierarchy. When positioned as direct, top-level children of the root body element, the header and footer tags operate as global landmarks representing the macro website banner and site-wide footer. However, when nested inside an article or section container block, their scope narrows entirely. They no longer represent global parameters. Instead, they act strictly as internal metadata targets for that specific component container instance. In our blueprint walkthrough, each article card contained its own internal header to wrap its subtitle, and its own internal footer to wrap its unique log timestamps. This scoping rule allows software engineering teams to construct highly modular, self-contained data cards that can be cleanly pulled from database tables and injected across completely different application views without breaking the page layout or corrupting the global document outline. To wrap up this lesson, let us look at common structural architectural failures that occur when coordinating massive repositories across parallel engineering teams, where visual-driven element choices frequently introduce critical structural bugs. Professional developers actively audit their files to eliminate 3 specific failures. The first failure type is division soup, which occurs when programmers overwrap every single content area inside unmarked, generic box divisions instead of using semantic tags. This choice completely hides your layout from the browser's internal accessibility subsystems, turning your web page into a flat, non-navigable wall of plain text for assistive devices. The fix is to implement explicit landmarks like main, nav, search, and aside so the browser can map out clear structural entry points cleanly. The second failure type is unanchored thematic sections, which happens when developers organize content streams inside a section container but completely omit a heading tag. This forces the browser's outline parser to register an anonymous, unnamed subtier inside the structural map, which degrades your search engine indexing quality. The fix is absolute. Every single section element block must feature an internal heading from H2 through H6 to declare its explicit theme to the parsing engine. The third failure type is structural nesting violations, which occurs when engineers break the outside-in data flow of a document, such as nesting a global main content container inside a component article block, or placing a site-wide header inside an aside callout box. The fix is to maintain a strict, disciplined nesting hierarchy where the body wraps your global site blocks, the main stage wraps your regional sections, and your sections host your modular article and aside components. By enforcing this extreme level of formatting discipline across your files, you ensure your application remains clean, searchable, and fully optimized for every developer who interacts with your codebase.
Chapter 4. Section 4.1. Welcome to Chapter 4, Section 4.1, Basic Table Elements. In this lesson, we are shifting our focus from sequential paragraphs and structural section landmarks to examine the foundational architecture of the HTML data table. HTML tables are highly specialized data structures explicitly designed to organize multidimensional information into a strict two-dimensional grid coordinate space. The browser's layout engine processes table frameworks sequentially by reading horizontal rows from top to bottom, distributing internal data cells precisely along a vertical and horizontal grid axis. Let us walk through the fundamental building blocks of an architectural grid, applying our strict engineering workflow of initializing our opening and closing tag pairs together before populating them with content, ensuring our data matrices remain completely stable, valid, and readable to every system that compiles them. A functional data grid relies on a tightly bound parent-child nesting framework composed of 4 core structural elements. First, to establish the primary containment matrix root block for your tabular layout, we use the table element. Write a less than sign, the word table, and a greater than sign to form your opening root tag, and immediately follow it with a less than sign, a /, the word table, and a greater than sign to close it, creating a large space in between them. This root container creates a specialized formatting context that forces all enclosed row and cell tracks to conform to synchronized horizontal and vertical tracks. Second, to define a distinct horizontal row track inside your table matrix, we use the table row element. Inside the empty space of your table container, write a less than sign, the letters tr, and a greater than sign, followed right next to it by a less than sign, a /, the letters tr, and a greater than sign. Under the HTML specification, a table row cannot exist in isolation, it must sit strictly as a direct child node of a table root or a semantic table section block. Third, to create a standard structural data cell container that holds your actual raw information, we use the table data element. Inside your horizontal row track boundaries, write a less than sign, the letters td, and a greater than sign, followed immediately by a less than sign, a /, the letters td, and a greater than sign. The table data cell acts as the fundamental coordinate building block of the grid, holding text literals, links, or nested elements. Fourth, to declare a specialized header cell container that represents metadata labels for an entire row or column track, we implement the table header element. Write your opening and closing tags together by putting the letters th inside a pair of angle brackets, followed right next to it by a less than sign, a /, the letters th, and a greater than sign. The browser engine processes table header character strings with distinct significance, pushing them directly to accessibility trees as descriptive label targets so assistive devices can announce them when a user traverses column tracks. By default, user agent stylesheets render these table header character strings with a bold weight property and a centered layout position on the screen canvas. Imagine a structural diagram of this basic table DOM architecture showing the table root element wrapping around multiple table rows, which in turn contain tightly nested arrays of table header cells and table data cells mapping out an identical grid relationship map. By default, every individual data cell occupies exactly one unit coordinate square in the grid matrix layout. To build sophisticated user interfaces or adapt a layout to complex multi-tier reporting sheets, professional developers implement specialized coordinate spanning attributes declared directly inside the opening tag of a table data TD or table header TH node. The first configuration property is column spanning, known as COLSPAN. Go inside the first pair of angle brackets of your data cell, add a space after the element letters, type the word COLSPAN, an equals sign, and a positive integer value enclosed inside a pair of quotation marks. For example, setting column span equals "3" stretches that individual cell horizontally to the right side of the viewport, forcing it to consume its own layout track plus 2 adjacent column slots. The second configuration property is row spanning, known as ROWSPAN. Inside the opening bracket of your target cell, add a space, type the word ROWSPAN, an equals sign, and a positive integer token inside quotation marks. Declaring row span equals "2" instructs the layout engine to merge that individual cell vertically downwards, reserving its spatial grid coordinates across subsequent row parsing passes. Imagine a visual grid coordinate map demonstrating these cell spans where a single column span block stretches wide across multiple vertical tracks, while an adjacent row span block extends down across horizontal rows, creating an asymmetric data layout. Let us establish a critical grid deficit warning for your engineering workflow. If your cell span integer calculations are configured incorrectly, such as declaring a column span of 4 inside a data matrix that only possesses 3 functional column tracks, the browser layout engine will be forced to push its tracking boundaries outward, creating unaligned cells and breaking your visual layout symmetry. Always compute your spanning values precisely to match your target matrix tracks. To provide a clear, explicit descriptive label or programmatic title for your entire data table, HTML provides the caption element. Write a less than sign, the word CAPTION, and a greater than sign to form your opening tag, and follow it instantly with a less than sign, a forward slash, the word CAPTION, and a greater than sign to close it. To maintain strict validation compliance inside the document object model tree, the caption node must be positioned as the absolute first child tag placed directly underneath your opening table root tag, and you are only permitted to implement one single caption element per table block. The browser's accessibility tree parses this caption element instantly when a user navigates to a table landmark, giving immediate context to the data matrix before assistive text-to-speech hardware begins reading the individual row tracks. Let us do a complete spoken walkthrough of a structurally compliant data table blueprint, spelling out every element from top to bottom so you can visualize the entire grid structure perfectly. We begin by opening our master matrix container, writing less than table greater than. Directly below, on the very first nested layer, we establish our programmatic title by opening and closing our caption tag pair together, filling it with the text content "quarterly microprocessor delivery metrics." Right below the closed caption tag, we initialize our first horizontal track by opening and closing a table row tr tag pair together. Inside this first row, we place our header metadata labels. Open and close your first th tag pair, writing the column name "component model." Directly below, open and close a second th tag pair, writing "region code." Directly below that, open and close a third th tag pair, writing "units dispatched." We have now populated our 3 category column headers, so we close our first tr row block. Below the closed first row, we open a brand new tr tag pair to handle our first set of numeric data values. Inside the second row track, we want our first cell to span down across multiple rows. Open your TD tag, add a space, write ROWSPAN equals sign, and the number 2 inside quotation marks, then write your closing greater than sign. Follow it immediately with a less than sign, a / TD, and a greater than sign to seal the tag pair, and write your item name "alpha processing unit" inside. Directly below this spanning cell, still inside our second row track, open and close a normal TD tag pair containing the region code text US-East. Directly below that, open and close another standard TD tag pair containing the dispatched unit count string 14,500. We have now filled the available slots for this track, so we close our second TR row block. Below that, we open a third TR horizontal track tag pair. Because our first processing unit cell spanned down into this level, the first column slot is already filled in memory, so the browser engine automatically maps our next tags to the second column track. Inside this third row, open and close a standard TD tag pair containing the second region code text EU-West, and right below it, open and close another TD tag pair containing the unit count string 12,200, then close your third TR row block. Finally, let us build a summary row at the bottom of our grid. Open a fourth TR horizontal track tag pair together. Inside this row, we want a single summary cell to stretch across our first two columns. Open your TD tag, add a space, write COLSPAN equals sign, and the number 2 inside quotation marks, then close the bracket. Follow it with your closing TD tag, and place your summary text "total dispatched volume" inside. Directly below this wide cell, open and close a final, single TD tag pair containing the total calculated sum string 26,700. Now, close your fourth TR row block completely, and finish the entire data matrix layout by writing your final closing table tag with a /. By structuring your tabular frameworks using this strict structural coordinate logic, keeping your rows tightly nested, computing your cell spans accurately, and defining your captions at the absolute top, you create an intensely organized, robust data matrix that parses beautifully across every system on the web. Section 4.2. Welcome to Section 4.2, Structuring Tables Semantically. In this lesson, we are going to look under the hood of enterprise-level data mapping to transform our basic two-dimensional grids into highly organized, machine-readable data architectures. When you coordinate massive repositories, a flat series of unstructured rows fails to provide enough architectural meaning. Without clear semantic boundaries, browser layout engines and assistive devices cannot distinguish between category labels, core data matrices, and summary calculations. Let us walk through how we implement specialized section wrappers and explicit tracking attributes to build a robust database report framework, continuing our strict engineering workflow of initializing our tag pairs together before populating them with content. First, let us look at structural grid groupings, which divide our data table into 3 independent structural zones mimicking database report frameworks: the table head, the table body, and the table footer. Imagine a structural chart displaying these 3 blocks clearly stacked on top of each other. To isolate your primary category header label tracks, we use the table head element. Write a less than sign, the letters THEAD, and a greater than sign to open the container, and immediately follow it with a less than sign, a /, the letters THEAD, and a greater than sign to close it. This element must sit at the absolute top of your table layer, and you can only implement one single THEAD block per table structure. Next, to wrap the core informational dataset of your report, we use the table body element. Write your opening and closing tags together by putting the letters TBODY inside a pair of angle brackets, followed right next to it by a less than sign, a / TBODY, and a greater than sign. Unlike the header, a single table can host multiple sequential body containers, allowing programmers to split massive datasets into separate thematic rows without breaking the uniform column tracks. Finally, to group calculated totals or final disclosures, we implement the table footer element. Write your opening and closing tags together by putting the letters TFOOT inside a pair of angle brackets, followed by a less than sign, a / TFOOT, and a greater than sign to close it. Implementing these explicit zones grants massive performance advantages. When a browser's print engine processes a table spanning multiple physical sheets of paper, it automatically duplicates the THEAD row at the top and the TFOOT row at the bottom of every single printed page. Furthermore, web browsers can use these blocks to pin headers and footers to the screen visually, letting users scroll through millions of data rows inside the body core while keeping the tracking labels securely fixed to the viewport edges. Second, let us walk through column track architecture tools. Because HTML tables are written row by row, targeting a vertical column for bulk attribute updates used to be incredibly difficult. The column group framework fixes this by mapping out vertical tracks before any rows are even parsed. To build this boundary, go to the absolute top of your table matrix, directly underneath your caption tag, and open and close your column group tag pair together by writing the letters COLGROUP inside your angle brackets. Inside this container, we nest individual column references using the void element tag COL. Write a less than sign, the letter COL, and a greater than sign. Because this is a void element, it acts as a standalone marker with no closing tag. Each sequential COL tag you write maps directly to a vertical column track starting from the left edge of your grid. To target multiple adjacent columns simultaneously without writing repetitive tags, you implement the span attribute inside the opening bracket. Add a space after the letter COL, write the word SPAN, an equals sign, and a positive integer enclosed in quotation marks, like span equals "2", which instantly commands the engine to apply your structural classifications across the next 2 consecutive vertical data tracks. Third, let us look at the header association field known as the scope attribute. This is a critical configuration property declared exclusively inside the opening bracket of a table header th tag, telling the accessibility engine exactly which direction a header cell governs. Imagine a directional matrix graph showing horizontal and vertical vectors pointing out from a header cell to target cells. To bind a category header directly to every single data cell located straight underneath it, add a space inside your opening th bracket, write the word SCOPE, an equals sign, and the token string "COL" inside quotation marks to declare a column scope. To bind a header cell to all data cells located straight to its right, write scope, an equals sign, and the token string "ROW" inside quotation marks to declare a row scope. For advanced multi-span blocks, you can also pass the token string "COLGROUP" to bind an entire vertical column group, or "ROWGROUP" to bind all horizontal rows enclosed within a specific body segment wrapper. Fourth and finally, let us master asymmetric header binding matrices using unique identifier ID tokens and the headers attribute. Standard scope paths work perfectly for uniform layouts, but when an enterprise application demands irregular, multi-tiered data tables with complex nested categories, simple directional vectors break down completely. To map these complex data paths with absolute precision, developers build hard-coded metadata cross-references. Imagine a complex multi-header grid diagram displaying lines linking explicit identifiers directly to data coordinates. Let us walk through this execution pipeline step by step. Step 1. Go to every individual category header th cell across your multi-tiered layout, add a space inside the opening bracket, and assign a completely unique text string to its ID attribute, like ID equals "h1" or ID equals "h2". Step 2. Move down into the table body data cells, open your standard TD tag, add a space, and write the word HEADERS, followed by an equals sign, and a pair of quotation marks. Step 3. Inside these quotation marks, write a space-separated array containing the exact ID tokens of every single header label that governs that individual data value. For example, if a numeric cell is controlled by a data center location header, a telemetry type header, and a specific node row header, you will write headers equals "h datacenter space h telemetry space r node". This explicit cross-reference forces a permanent semantic connection in memory, ensuring that no matter how asymmetric or warped your grid layout becomes, every data cell perfectly identifies its parent categories across every assistive device and automated indexing system on the web. By enforcing this absolute level of semantic discipline across your tabular repositories, you turn raw visual grids into flawlessly organized data networks. Section 4.3. Welcome to Section 4.3, When to Use Tables. In this lesson, we will establish a core architectural principle of professional web engineering, which is the absolute segregation of structural data grids from visual presentation layers. The HTML table element possesses a single, highly specified engineering purpose: organizing and presenting multidimensional relational data. Abusing this framework for any other visual layout operation severely damages your document's accessibility tree, ruins your page outline, and introduces critical responsive bugs to your application. Let us walk through how to identify valid tabular structures and why legacy visual design hacks must be completely avoided in modern development workflows. Let us look first at valid relational data use cases. Imagine a visual diagram of a compliant data table matrix showing clear horizontal and vertical coordinate axes intersecting directly at a single data node. This illustration shows the exact condition under which an HTML table is structurally justified. The layout is necessary if and only if the underlying information is two-dimensional and relational. This means the dataset requires a reader, whether human or machine, to scan a horizontal row header and a vertical column header simultaneously to interpret the explicit meaning of a single cell intersection. Prototypical engineering scenarios include tabular numeric matrices like financial spreadsheets and quarterly balance sheets, system log registries tracking real-time server uptime metrics or error logs, comparative product feature grids, and structural timetables or project milestone charts. If your content demands a multi-axis cross-reference to be fully understood, it belongs inside a table container. Now, contrast this with the legacy visual layout anti-pattern. Imagine a comparative layout diagram displaying a legacy HTML table layout architecture anti-pattern side by side with a modern semantic layout structure. The left side of this visualization displays a classic industry mistake from the early history of the web, before advanced styling rules existed. Developers routinely weaponized table tags to force standard text, sidebars, images, and menus into visual columns on the screen. Entire websites were wrapped inside complex networks of deeply nested table, TR, and TD elements, using completely blank, empty cells purely to hack margins and padding into the visual viewport. The right side of the diagram shows the modern semantic blueprint, where structural landmark zones like header, main, aside, and section handle the layout, completely isolating presentation from data. Using tables as visual positioning tools is a severe structural violation. If a layout area does not represent an explicit coordinate database matrix, implementing a table framework introduces massive liabilities to your software stack. Let us analyze the severe technical consequences that occur when an engineer exploits layout tables for non-tabular page structures. the document immediately degrades across 4 critical engineering vectors. The first vector is accessibility tree destruction. When a browser parses a table tag, it registers a formal data grid landmark in memory. When a text-to-speech screen reader navigates into a table used for layout, it announces to a visually impaired user that they are entering a data grid. The device will loudly voice total row counts, column counts, and precise cell grid coordinates, stating things like row 3, column 1, navigation link, instead of cleanly reading the narrative prose stream. This completely disorients the user and breaks layout comprehension. The second vector is reading order inversion. Screen readers parse table cells strictly by row order, processing from left to right, and then top to bottom. If a layout table places a sidebar navigation menu in a left cell and the main article text in a right cell, the assistive device will force the user to listen to dozens of repetitive navigation links before ever reaching the actual page content, with no semantic way to skip the layout blocks. The third vector is document outline and SEO degradation. Search engine crawlers evaluate web documents based on their semantic purity. Wrapping banners, sidebars, and footers inside data tables completely flattens the structural outline of your document tree, preventing automated indexing daemons from separating primary content from secondary menus, which heavily reduces your search ranking weight. The fourth vector is responsive viewport truncation bugs. HTML data tables are fundamentally rigid structures. The browser's layout engine computes column tracks based on the maximum width of the text data cells. When a table-based page layout is rendered on a small mobile device viewport, the table cannot break or stack vertically like a standard semantic paragraph box. This triggers permanent horizontal scrolling bugs, element overlapping failures, and unreadable text truncation on mobile browsers. To ensure your applications remain completely stable and professional, let us master the primary engineering rule of thumb known as the linearization test. To determine with absolute certainty whether your content requires a table structure, strip away all structural containers and read the raw text token sequentially from top to bottom as a single, uniform line of text. If the information remains entirely comprehensible and retains its true logical meaning without the presence of a visual grid axis, you must never implement a table element. If the data can be written using a standard hierarchical layout, select semantic blocks like headings, lists, sections, and paragraphs. Reserve table models exclusively for datasets that rely on horizontal and vertical coordinate tracks to be understood. Presentational layouts belong completely inside external style configuration files, leaving your HTML markup structurally clean, fully accessible, and highly optimized for every system on the web. Chapter 5. Forms. Section 5.1. The form element. Welcome to Chapter 5, Section 5.1, the form element. In this lesson, we are stepping into the interactive engine of web architecture to master the foundational gateway of user-to-server communication. The FORM element defines an explicit structural data harvesting boundary within the document object model. Rather than just wrapping text or rendering layout shapes, the form acts as a master orchestrator. Its primary engineering purpose is to gather the fluctuating internal states of all its nested interactive controls, like text inputs, drop-down selections, and checkbox switches, and serialize those variables into structured key-value datasets. It then establishes a secure network transport pipeline to fire that payload data across HTTP channels directly to backend database handlers. To help visualize this entire mechanism, imagine a comprehensive lifecycle diagram showing a user typing information into an interface browser layout, clicking a submission button, and watching the form engine pack those key-value variables into an encoded request package that travels across the web to an external server architecture, which processes the file and fires back an updated data response. Following our structural engineering workflow to guarantee project stability, we always write our opening and closing tag pairs together in memory before we ever declare their routing configuration parameters. To initialize this element, write a less than sign, the letters FORM, and a greater than sign to form your opening tag container. Right next to it, write a less than sign, a forward slash, the letters FORM, and a greater than sign to seal your closing tag boundary. Create a large open space in between them where your user control input elements will live. Now, let us go inside the opening tag right after the letters FORM, add a space, and systematically configure the vital attributes required to guide our dataset across network pathways. The absolute primary routing property is the action attribute. Type the letters ACTION, followed by an equals sign, and a pair of quotation marks. The string value you place inside these quotes acts as the endpoint router, specifying the fully qualified URL path or local file directory pointing to the server-side script or API gate responsible for consuming your payload data. Let us establish an essential fallback behavior check for your debugging workflow. If you leave the action field completely empty or omit it from your markup, the browser engine defaults to submitting the harvested payload back to the exact same URL origin address currently hosting the web page layout. Directly following your action parameter, add a space to configure the protocol switch known as the method attribute. Type the letters METHOD, an equals sign, and a pair of quotation marks. The choice you declare inside these quotes determines the explicit transport methodology used to deliver your data variables to the target web server, and it is restricted to two core options, GT or POST. If you set your method attribute to the lowercase letters GT, the browser engine executes its data delivery loop by transforming your compiled key value inputs into an unencrypted query string, which it appends directly onto the end of your action URL path following a literal question mark character. This produces data pathways that display variables openly in the browser's address bar. Because GET transmissions leave variables exposed in browser history logs, they are fundamentally unsafe for sensitive inputs. Furthermore, GET requests are constrained by rigid browser length thresholds, typically capping your entire dataset at 2048 total characters. To override these deficits, professional developers switch to the lowercase letters POST inside the method field. When a user executes a POST submission loop, the browser engine completely isolates the dataset from your address links, packaging the serialized key value matrix directly within the hidden message body payload of the HTTP request. The POST configuration features no data size limits, making it strictly mandatory for security checkpoints, database write operations, user creation records, and file uploads. Our third critical configuration attribute is the media encoding standard, known as the ENCTYPE attribute. Add a space inside your opening form bracket, and type the letters ENCTYPE, followed by an equals sign and a pair of quotation marks. This property specifies the exact MIME media type structure used to serialize your data characters before they travel across network lines, and it is only functional when your method is set explicitly to POST. If you omit this attribute, the engine defaults to the value application /x-www-form-erl encoded. This default text serialization method converts your keys and values into a single line of plain text where spaces are encoded into plus symbols or hexadecimal codes, and variables are linked via ampersand characters. This works flawlessly for basic text parameters and logins. However, if your form architecture includes file uploads where users stream binary photos, PDF logs, or document bytes to your database, the default text serialization will destroy the file data. To handle file objects, you must override the encoding state by writing the exact string literal multipart /form-data inside your ENCTYP quotation marks. This structural setting commands the browser engine to split your data payload into distinct, isolated block units separated by automated system boundary markers, preserving your raw file bytes without any destructive character escaping loops. For specialized debugging pipelines, you can also declare text /plain, which transfers raw strings without any wrappers, though this is highly discouraged for production application stacks. To finish our master tag configuration setup, let us look at target and novalidate. Add a space, and type the word TARGT, an equals sign, and a browsing window context token inside quotation marks. Passing underscore self loads your server's incoming data response inside the current tab, while passing underscore blank spawns a brand new window tab context. Right next to that, you can add a space and type the standalone Boolean attribute novalidate. Declaring this attribute tells the browser's built-in validation core to completely shut down its interactive constraint checks, forcing the form to pass immediate raw input state straight to the network without triggering client-side validation pop-ups. Finally, let us organize our form-wide tracking variables directly inside the opening tag layout. You can add a space and type the word name, an equals sign, and a unique tracking title string inside quotation marks to identify this specific form block within your developer script file scopes. Next, implement the autocomplete attribute by typing autocomplete, an equals sign, and passing either the token string on to allow browser engines to cache input history values for user suggestions, or the token string off to block all local caching loops for heightened system security. Lastly, you can declare the text encoding rule by adding a space, typing the letters ACCPT-CHARSET, an equals sign, and the encoding standard string UTF-8 inside quotation marks, ensuring that every data byte passing out of your element enclosure conforms to universal international character sets. By building your form containers with this level of precision, sealing your tag boundaries securely first, selecting your transport methods strategically, and adjusting your encoding standards to match your underlying file datasets, you construct a bulletproof, enterprise-ready interactive interface that routes data flawlessly across the web. Section 5.2. Labels and Field Sets. Welcome to Section 5.2, Labels and Field Sets. In this lesson, we are mastering the structural formatting rules required to pass strict accessibility validation checkpoints and maintain immaculate organization across massive, multi-team engineering repositories. To build professional web applications, interactive form control nodes cannot simply float in space alongside raw, unjoined text descriptions. They must establish unbreakable programmatic bonds in memory so that browser layout engines, accessibility trees, and testing scripts can map out the data canvas with total precision. To help visualize this layout matrix before we write our markup, let us look at a structural control tree diagram mapping out exactly how labels, field sets, legends, and input elements securely bind together in system memory. Following our core engineering workflow, we will always initialize our opening and closing bracket pairs together first before defining our layout parameters. Let us examine the absolute cornerstone of form accessibility, the label element. Write a less than sign, the letters label, and a greater than sign to form your opening tag, and follow it immediately with a less than sign, a / label, and a greater than sign to lock down the closing boundary. Step inside this tag pair and type out your human-readable text description, like user tracking token or access passphrase. Under the web standard specification, you can establish this programmatic connection using two distinct structural approaches: explicit association or implicit association. Explicit association is widely recognized as the gold standard engineering practice for huge projects. Under this model, your label and your input field exist as completely separate, adjacent sibling tags on the page. To link them, you go inside the opening bracket of your input control tag and declare a unique identifier by writing ID, an equals sign, and a unique name string inside quotation marks. Next, you move back to your opening label tag, add a space, and implement the configuration property by writing the letters FOR, an equals sign, and that exact same unique identifier string inside quotation marks. The browser engine processes this identical match as an unbreakable physical link. Clicking or tapping the descriptive text automatically jumps the user's cursor focus straight into the input box, which drastically expands the physical hit area of your interface on mobile screens and ensures screen reader engines announce the exact label field accurately. Alternatively, you can implement an implicit association through structural encapsulation. Under this method, you open your label tag, write your description text. Nest your entire input tag directly inside the label's character boundaries, and then write your closing label tag. Proximity alone forces the browser engine to compute the programmatic link automatically, which eliminates the need to coordinate hard-coded FOR and ID string properties across your files. Now, let us expand our focus to handle large-scale data group boundaries using the field set and legend elements. When an enterprise application form expands to hold dozens of complex configuration vectors, separating related inputs into clean visual and semantic subblocks is vital to keeping development teams organized and preventing code degradation. To build an independent data tracking subblock, we use the control aggregator known as the field set element. Write a less than sign, the letters FIELDSET, and a greater than sign to open the container, and right next to it, write a less than sign, a / FIELDSET, and a greater than sign to seal the boundary. The field set element provides an incredibly powerful programmatic switch for development teams. If a system event requires you to temporarily lock down an entire subset of inputs, you do not need to hunt through your file to deactivate every individual box. Instead, you simply go inside the first opening bracket of your FIELDSET container, add a space, and write the standalone Boolean attribute disabled. The browser engine instantly cascades this block command down your entire document subtree, completely graying out, deactivating, and blocking every single nested label and input inside its boundaries from participating in network payload serialization loops. To give this field set group a clear identity anchor, you must implement the legend element inside. Write a less than sign, the letters LEGND, and a greater than sign to open the tag, and follow it with its closing tag pair with a /. To maintain absolute validation compliance inside the document object model, your LEGND tag must sit as the absolute first child node position directly underneath your opening FIELDSET tag, before any label or input tracks are written. Only one legend is permitted per group, acting as a permanent structural caption that accessibility devices read instantly to give immediate context to the entire subblock dataset. By engineering your input fields with these precise labeling hooks and logical field set boundaries, you transform loose interaction tracks into a highly secure, universally accessible, and industrial-grade user interface. Section 5.3. The input element. Welcome to Section 5.3, the input element and its classic types. In this lesson, we are going to break down the absolute workhorse of the HTML interactive ecosystem. The input tag is a highly versatile inline void element, which means it has a standalone physical footprint that never contains child nodes and completely omits a separate closing tag. Despite its small footprint, it behaves exactly like a structural chameleon. Its entire data processing pipeline, visual presentation layer, native validation rule set, and mobile touch keyboard layout switch completely based on the string value you assign to its type attribute. To help visualize this incredible architectural transformation before we write our markup, imagine a visual layer diagram showing a single, raw input block sitting in memory, while a series of different type attribute keys plug into it, instantly morphing its layout interface from a hidden tracking line into an obfuscated password field, a numeric filtering box, or an operating system file bridge. Let us first examine alphanumeric character ingestion frameworks, which are built to capture single lines of text while intercepting input errors before a payload ever leaves the browser pipeline. Following our strict engineering workflow, we write our standalone void tag by opening a less than sign, typing the letters INPUT, adding a space, and declaring our configuration properties inside. The absolute baseline placeholder state is text input. If you write your type attribute by typing the word type, an equals sign, and the string value "text" inside quotation marks, you initialize a standard baseline sandbox field. This box accepts raw single-line text data with zero built-in structural filtering passes. If you omit the type attribute entirely or misspell its value, the browser engine automatically defaults straight back to this text state. To process sensitive security credentials safely, we change our configuration to password input. Inside your input tag, write type =, and the string value password inside quotation marks. When this configuration activates, the browser's layout engine deliberately intercepts standard character painting steps on the screen canvas, instantly obscuring visible alphanumeric glyphs and replacing them with generic masking dots or bullet symbols to shield data from nearby screens. Let us issue an architectural security warning here. This masking property is purely a visual layout defense. The raw characters remain completely unencrypted in system memory and will be transmitted as standard plain text unless your form is wrapped inside a secure POST HTTPS network pipeline. Next, to validate data strings automatically, we can implement email and URL types. For an email field, write type =, and the string value email inside quotation marks. This commands the native constraint validation engine to check the entered text against a built-in regular expression checklist, requiring an @ symbol followed by a domain host before allowing a submission cycle. On mobile touch viewports, it also alters the hardware layer to bring up a dedicated @ symbol key on the primary keyboard. For web address mapping, write type =, and the string token URL inside quotation marks. The validation engine will actively block the submission if a user inputs a domain name without its absolute transfer protocol prefix, such as https://. For telephone registries, we implement the tel input type by writing type =, and the string token tel inside quotation marks. Because telephone dialing sequences vary wildly across global international networks, using spaces, parentheses, or plus signs, the browser engine intentionally skips strict text formatting passes. However, it intercepts touchscreen hardware interfaces, forcing mobile devices to launch a dedicated phone-style numeric dialing pad instead of an alphabetical layout. To create a strict numeric filter box, we implement the number type by writing type =, and the string value number inside quotation marks. This configuration blocks all standard alphabetical keyboard entries, permitting only raw digits and mathematical symbols like decimals, negative signs, or exponent characters. It unlocks 3 specialized control properties that you can write directly inside the tag bracket. Add a space and write min and =, and a minimum integer limit inside quotes. Add another space and write max and =, and a maximum integer limit inside quotes. Finally, add a space and write stp and =, and a pacing multiplier value inside quotes, such as step equals "0.5", which restricts valid entries strictly to half-unit intervals. To complete our text frameworks, we use the search input type by writing type =, and the string token *serch* inside quotation marks. This hooks the cell directly into accessibility search landmark trees and automatically injects a native clear icon button, displayed as an X glyph on the right edge of the frame, allowing users to wipe their input query clean instantly with a single click. Now, let us transition our focus to specialized action and non-textual controls, where inputs do not ingest typed characters but act as backend channels or interface triggers. The most critical backend channel is the hidden input field. Write a less than sign, the word input, a space, type =, and the string token "HIDDEN" inside quotation marks. The rendering engine completely blocks this tag from painting any visual box onto the user's viewport stage. However, it remains fully active within the document object model tree. Programmers use this silent channel to house server-side keys, transaction tracking identifiers, or database session tokens that must be bundled into the form serialization payload automatically without any user knowledge or physical interaction. To stream data files directly from a host operating system, we construct a local file security bridge. Write your input tag with type =, and the string value "file" inside quotation marks. This opens an interface button that lets users select items from their local hard drive storage. You can restrict their options cleanly by adding a space and implementing the accept attribute, writing ACCPT, an equals sign, and specific media type extensions inside quotation marks, such as accept equals quote application /PDF unquote. You can also add a space and declare the standalone Boolean attribute multiple to allow users to select and stream multiple files simultaneously. To handle form state changes and network actions, HTML provides submission, reset, and button types. Writing type equals quote submit unquote creates the primary execution switch that commands the parent form to gather all local input variables, serialize the key value data paths, and fire its network request pipeline to the destination server. Writing type equals quote reset unquote builds a trigger that instantly reverts all interactive controls inside the form back to their absolute default initialization states, completely clearing out typed text strings. Writing type equals quote button unquote renders a completely blank interactive structure carrying zero default fallback browser routines, acting as an empty anchor waiting for custom JavaScript automation parameters. Finally, you can implement a coordinate capture tool by writing type equals sign and the string token quote imag unquote inside quotation marks. This configuration replaces standard text buttons with a graphical visual asset using a src attribute. When a user clicks a coordinate on the image canvas, the browser engine gathers the exact pixel horizontal and vertical click paths, appending them directly to your form's serialization array as X and Y coordinate pointers. To ensure absolute integrity across your inputs before data ever hits a backend API, let us master classic sizing and data constraints that you can declare as properties directly inside your input brackets. First, you can write placeholder, an equals sign, and a descriptive string inside quotation marks to inject a temporary, dimmed background hint into an empty field, which vanishes instantly the moment a user types a single character. Second, you can declare the standalone Boolean attribute required to flag a field as completely mandatory, which halts the submission loop and flashes an automated browser error bubble if the cell is left blank. Third, you can write the Boolean attribute disabled to gray out a box and stop user interactions, which completely drops that entire key value pair from the final network payload string. Fourth, you can implement the readonly Boolean attribute, which blocks typing inputs but leaves focus paths active, rendering the text selectable and fully functional for standard form submissions. Fifth and sixth, you can control character counts precisely by adding a space and writing maxlength, an equals sign, and an integer limit inside quotes to cap how many characters a user can physically type into the input buffer, or minlength, an equals sign, and an integer token to throw a native validation error if the typed text string fails to meet your minimum length threshold. Now, let us execute a complete, step-by-step spoken walkthrough of an enterprise-grade registration production blueprint, showing exactly how these classic input types and data constraints interlock inside an active project file. Imagine opening your master form element. We configure its opening parameters by setting its action attribute to the API routing path /API/v1/auth/registr unquote, setting its method attribute explicitly to POST, and giving it the unique ID string token registration-engine unquote. Right inside this form, we open our structural field set aggregator block and immediately anchor it by opening and closing a legend tag containing our group identity caption text identity and system registration protocols unquote. Let us build our first interactive content track inside this field set for the username field. We open a layout row container, and inside it, we write our opening and closing label tags, setting the FOR attribute to reghyphenusername unquote, filling the label with the text system username registry label unquote. Directly below that label, we initialize our classic alphanumeric void input. We write less than input, add a space, set type equals text set its ID to match the label exactly as reghyphenusername set its name attribute to username add a placeholder set to eg.admin_alpha and enforce strict boundaries by adding min length equals 4 max length equals 20 and the standalone Boolean attribute required before closing the bracket. Directly underneath this row, we want to inject a silent, invisible data channel to pass session parameters to our backend handler without user interaction. We open a brand new standalone input tag, setting its type attribute to HIDDEN setting its tracking name attribute to SYSTEM_SESSION_ID and hard-coding its tracking payload data by adding value equals SESS-2026-XYZ-909 Next, let us establish our password checkpoint. We open our next layout row container and write our section 5.4. Welcome to section 5.4, the input element, modern types and mobile hints. In this lesson, we are stepping completely beyond classical alphanumeric text fields to master the modern, full-spectrum capabilities of the HTML data ingestion engine. Modern HTML configurations expand the input element's processing controls to replace heavy, complex third-party JavaScript calendar, color, and selection widgets with highly performant, system-level native user interface controls. Furthermore, they provide enterprise developers with granular hardware modification parameters to retune virtual touchscreen keyboards on mobile devices, vastly increasing typing speed and eliminating input errors across global networks. To help your animation and design teams visualize these advanced layout capabilities before we build our framework, let us examine an illustrative graphic displaying mobile native date selectors, sliding range tracks, and color wheel panel frames rendering dynamically across mobile operating systems. Let us first examine the execution loops for native chronological, visual, and fluid selection components. Following our strict structural engineering workflow, we always initialize our tag frameworks clearly in memory as standalone void blocks before configuring their behavioral properties. To build an automated calendar interface, open a less than sign, write the letters input, and write a greater than sign to establish your void tag. Now, go inside that bracket, add a space after the word input, and configure its characteristics. Type the word type and equals sign, and the string value .dat inside quotation marks. Next, add a space, and write the name attribute by typing name, an equals sign, and the tracking string schedule_date. This modern type commands the browser to spawn a localized calendar pop-up card that automatically harvests selections into a strict, standardized machine parsable string format consisting of a 4-digit year, a hyphen, a 2-digit month, a hyphen, and a 2-digit day. This prevents data corruption caused by regional database variations. If your database requires exact timestamp arrays including hours and minutes, you configure a new input void tag and set its type attribute to the string value .dattimelcal inside quotation marks. To isolate broader calendar windows or daily clock increments without a full date, HTML provides highly specific temporal filters. To restrict a selection strictly to a calendar month, open your input void tag, add a space, and set its type attribute to the string value .month inside quotation marks, which harvests data into a 4-digit year and a 2-digit month code. To isolate a timeline by fiscal weeks, open your input void tag and set its type attribute to the string value .week, returning a data string formatted with a year, the capital letter W, and a 2-digit week integer. To capture standalone daily execution times completely independent of calendar dates, open your input void tag and set its type attribute to the string value .time inside quotation marks to launch a native digital clock spinner panel that safely captures a 24-hour and minute coordinate. To collect absolute hexadecimal color codes from an interface, open your void input tag, add a space, set its type attribute to the string value "color" inside quotation marks, and set its submission name to "element_theme". When clicked, the browser automatically fires a system-native interactive color wheel panel, returning a flawless 7-character hexadecimal string verification code directly to your form payload. To build a fluid slider selection bar, open your input void tag, add a space, set its type attribute to the string value "rang", and assign its network name to "transmission_pacing". This converts the standard entry cell into a horizontal sliding gauge. To control its mathematical boundaries, add a space inside the bracket and write min an equals sign, and your minimum limit inside quotation marks, add a space and write max an equals sign, and your maximum limit inside quotation marks, then add another space and write step an equals sign, and your incremental stepping pacing value inside quotation marks. Now let us master state-based selection options using checkbox and radio inputs. Imagine an interface graphic displaying a list of checkboxes where multiple items can be turned on at once, contrasted against a circular radio button group where clicking one option instantly forces the others to turn off. For a binary toggle control, open your void input tag, set its type attribute to "checkbox", and assign its name attribute. When building a form where a user can select multiple options simultaneously, you will write a sequence of these tags. The absolute rule of web architecture for checkboxes is that every single checkbox in that specific choice set must share the exact same string value inside their name attributes, while possessing a completely unique value property on each tag to differentiate the choices for your database, such as value equals "protocol alpha" on the first, and value equals "protocol beta" on the second. The browser automatically bundles all active values into a single array dataset under that shared name key during submission loops. To pre-turn a checkbox on when the page loads, add a space inside its opening bracket and declare the standalone Boolean attribute checked. For programmatic mutual exclusion sets where a user is strictly allowed to select only one single option from a group, open your input void tag and set its type attribute to the string value "radio" inside quotation marks. To force mutual exclusion across a cluster of radio buttons, you must assign the exact same name string to every single radio tag in that group, while giving each individual tag its own distinct payload key via the value attribute. Activating a new option instantly switches focus and deactivates the previous item automatically in system memory. Second, let us walk through the architecture of autocomplete suggestions using the data list element. This framework allows developers to attach a dynamic suggestion drop-down matrix directly to a standard text input field without locking the user into a rigid, non-editable pick list. To construct this mechanism, we create two separate, linked nodes. First, initialize your standard text input void tag by writing <input, a space, type equals "text", a space, id equals "system node", and a space, name equals "cluster_node". To hook this input into our autocomplete data map, we add a space inside the bracket and implement the list attribute. Type the letters list, an equals sign, and a unique identification target string "node suggestions" inside quotation marks, then close the input bracket. Directly underneath this input, we build our suggestion data provider using the data list container. Write a less than sign, the letters DATALIST, and a greater than sign to form your opening tag, and immediately follow it with a less than sign, a /, the letters DATALIST, and a greater than sign to seal the closing boundary. Step back inside the opening tag, add a space, and write ID, an equals sign, and the exact matching target string "node suggestions" inside quotation marks to forge the unbroken programmatic connection in memory. Now, step inside the open space between your data list tags to populate the index with option items. For each suggestion, we initialize our option tag pair together by writing <option greater than, followed immediately by <option greater than. Go inside the first opening bracket of your option, add a space, and write the word value, an equals sign, and your explicit database tracking string inside quotation marks, such as value equals "node alpha east" or value equals "node beta west". When a user types inside the linked text box, the browser instantly surfaces these filtered options as an autocomplete dropdown. Third, let us master mobile hardware interface adaptations. When an enterprise application renders inside a touchscreen layout footprint, default virtual keyboards often slow down user input and cause spelling mistakes. Professional programmers override these default hardware states by implementing explicit virtual keyboard design modifiers directly inside their input tags. The first modifier is the input mode attribute, which alters the physical layout of the touchscreen keyboard. Open your void input tag, add a space, and write the letters input mode, followed by an equal sign and a pair of quotation marks. If you pass the string value numeric inside these quotes, you command mobile devices to completely hide standard alphabetical keys and launch a clean, phone-style number pad, which is vital for security pins or numeric identification tracking codes. If your field requires decimal calculations, pass the string value decimal inside the input mode quotes, which launches a numeric pad that features a dedicated dot button on the main layout board. If you pass the string token tel, it spawns a phone dialing keypad containing asterisk and pound symbols. If you pass the string token URL, it modifies the standard alphabetical layout to surface dedicated shorthand buttons for forward slashes and .com extensions directly on the primary typing board. The second modifier is the enter keyhint attribute, which customizes the action button text painted in the lower corner of the virtual keyboard layout. Add a space inside your input bracket, type the letters entrkeyhint, an equals sign, and a standardized action string inside quotation marks. Passing the token string "go" or "send" changes the enter key icon into an explicit command description, matching the interactive context of your form. The third modifier is the auto-capitalize attribute, which controls automated capitalization shifts as users type characters on touchscreen glass. Add a space inside your input bracket, type the letters AUTOCAPITALIZE, an equals sign, and a control option inside quotation marks. Passing the option string "none" completely deactivates automated capitalization passes, which is absolutely mandatory whenever you are configuring fields for system usernames, electronic mail addresses, or programming variables, preventing mobile operating systems from accidentally altering the integrity of your backend data strings. Now, let us execute a single, comprehensive, step-by-step spoken walkthrough of an enterprise-grade control panel production blueprint, showing exactly how every single one of these modern input types, selection matrices, data lists, and hardware hints interlock inside an active project file. Imagine opening your master form element. We configure its opening parameters by setting its action attribute to the routing path /API/control, setting its method attribute explicitly to POST, and giving it the unique ID string token SYSTEM-PANEL. Right inside this form, we open our structural field set aggregator block and immediately anchor it by opening and closing a legend tag together, filling it with our group identity caption text Enterprise Cluster Management Dashboard. Let us build our first modern interactive content track inside this field set for the maintenance schedule date. We open a layout row container, and inside it, we write our opening and closing label tags together first, setting the FOR attribute to MNT-DAT, filling the label with the text target system maintenance date. Directly below that label, we initialize our modern chronological void input. We write less than input, add a space, set type equals DAT, set its ID to match the label exactly as MNT-DAT, and set its name attribute to MAINTNANC_DAT, before closing the bracket. Next, let us establish our native color workspace customization. We open our next layout row container and write our label tag pair together first, setting its FOR attribute to "PNL-THEME" and filling it with the text description "UI interface identification accent color". Right next to it, we open our visual void input tag, setting its type attribute to "COLOR" so the engine spawns a native palette wheel, mapping its ID to "PNL-THEME", and setting its network name to "PANEL_THEME". Moving down, we configure our fluid range slider control track to limit core performance thresholds. Open your row container, write your label tag with the FOR attribute set to "CPU-LIMIT", and fill it with the description text "maximum permissible core ingestion allocation threshold". Directly below, write your void input tag, setting its type attribute explicitly to "RANG", configuring its ID to "CPU-LIMIT", setting its name attribute to "CPU_CAPACITY", and restricting its math paths by writing MIN equals "TEN", MAX equals "ONE-HUNDRED", and STEP equals "FIV". To handle dynamic data suggestion lists without locking out manual entry, we build our connected text data list node tracker. Open your next layout row, write your label tag with the FOR attribute set to "DB-LOCATION", and fill it with the text "designated database target region". Right underneath, initialize your text void input by setting its type attribute to "TXT", its matching ID to "DB-LOCATION", its submission name to "DATABASE_REGION", and adding the structural list hook by typing list equals "REGION-OPTIONS". Directly below this input, we open and close our data list container tags together first. Go inside the opening bracket and set its ID to match the input list hook exactly as "REGION-OPTIONS". Inside this data list space, we open and close our individual option tag pairs together. Inside the first opening option bracket, add a space and set value equals "US-EAST". Inside the second opening option bracket, add a space and set value equals "EU-WEST". Now, let us append our multi-selection checkbox matrix track. We open a new layout row container, and inside it, we write our label tag with the FOR attribute set to "CHK-alpha", filling it with the text "enabled security logging protocols". Directly below, we initialize our first checkbox void tag. Write <INPUT, add a space, set type equals "CHECKBOX", map its ID to "CHK-alpha", set its shared tracking name to "SYSTEM_PROTOCOLS", assign its unique database value string by writing value equals "alpha", and pre-activate it by adding the Boolean attribute CHECKED before closing the bracket. Right next to it, we open our second checkbox void tag, setting type equals "CHECKBOX", setting its ID to "CHKBeta", matching its shared name attribute exactly as "SYSTEM_PROTOCOLS", and assigning its unique value payload to "BETA". Directly underneath, we establish our mutually exclusive radio button choice environment. Open a new layout row container, and write your label tag with the FOR attribute set to "radprod", filling it with the text description "active deployment target cluster". Below it, we open our first radio void tag. Write <INPUT, add a space, set type equals "RADIO", set its ID to "radprod", set its grouping name attribute to "ENV_TARGT", assign its database value payload to "PRODUCTION", and pre-select it with the CHECKED Boolean attribute. Right next to it, open a second radio void tag, setting type equals "RADIO", setting its ID to "RAD_stage", matching its grouping name attribute exactly as "env_targt", and setting its distinct value payload to "staging". Clicking the staging radio button on the glass interface will instantly uncheck the production circle in system memory. Now, let us append our specific isolated temporal filters. Open a new layout row, write your label tag with the FOR attribute set to "logmonth", and fill it with the text "designated system archival month". Below it, write your void input tag, setting its type attribute explicitly to "month", configuring its ID to "logmonth", and setting its submission name to "archive_month". Open your next layout row, write your label tag with the FOR attribute set to "backtime", and fill it with the clock description text "scheduled daily backup execution time". Directly below, write your temporal clock void input tag, setting its type attribute explicitly to "time", to spawn the clock spinner, mapping its ID to "backtime", and setting its network submission name to "backup_time". Finally, let us build our touchscreen mobile hardware interface optimizer track to handle system passcodes cleanly. Open your layout row, write your label tag with the FOR attribute set to "auth-token", and fill it with the text description "secure ingestion passcode integer". Below it, write your alphanumeric void input tag, setting its type attribute to "text", mapping its matching ID to "auth-token", and setting its payload name to "verification_code". Now, let us retune the mobile touchscreen keyboard parameters by adding a space and writing inputmod equals "numeric", to force a phone-style number pad, adding a space and writing entrkyhint equals "done", to customize the virtual enter key label, and adding a space and writing autocapitaliz equals "none", to block mobile operating systems from accidentally auto-capitalizing security tokens. At the absolute bottom of our form layout, we close our rows and open a specialized execution action row to hold our master engine submit button trigger. We write a void input tag, setting its type attribute to "submit", and setting its visual text button string by adding value equals "transmit command matrix". We have now populated our data paths completely, so we write our closing field set tag, and finally, we seal the entire interactive pipeline by writing our master closing form tag with a /. By masterfully deploying these modern input types, nesting your chronological and selection matrices, linking them securely to structured data list containers, and fine-tuning mobile hardware virtual keyboards, you eliminate user entry errors and build an incredibly responsive, flawless interactive data layer. Section 5.5. Welcome to Section 5.5, Other Form Controls. In this lesson, we are expanding our interactive workspace completely beyond classical and modern void input elements to master advanced structural containers. Complex business dashboards and live system telemetry networks demand a diverse array of data capture variations, including rich multi-line description text blocks, categorized drop-down selection trees, explicit button control boundaries, and real-time scalar measurement gauges. Let us walk through these highly specific elements step by step, continuing our strict engineering discipline of initializing our opening and closing tag pairs together in memory before ever declaring their attributes or populating them with text, ensuring our enterprise user interfaces remain perfectly stable, organized, and completely accessible to every compiling machine on the web. First, let us examine multi-line data blocks using the textArea element. Unlike standard input tags that act as inline void elements, the textArea is an explicit container tag pair engineered specifically to hold extensive paragraphs or plaintext data blocks. To build this container, write a less than sign, the letters textarea, and a greater than sign to form your opening tag, and immediately follow it with a less than sign, a /, the letters textarea, and a greater than sign to lock down the closing boundary. Step back inside the opening tag after the element name to configure its layout proportions and behavior parameters. Add a space, and write the rows attribute by typing ROWS, an equals sign, and an integer value enclosed inside a pair of quotation marks to set the default visible line height capacity of the field block. Next, add a space, and write the columns attribute by typing COLS, an equals sign, and an integer inside quotation marks to define the standard horizontal character width capacity on the user viewport canvas. To govern how text formatting handles automatic line breaks, we implement the wrap attribute by adding a space, typing the word WRAP, an equals sign, and passing either the token string SOFT to visually wrap text within the interface boundaries while stripping out those line breaks during network transmission, or the token string HARD to inject literal line break characters into your database payload string. Let us issue a critical engineering requirement here. Whenever you declare a hard wrapping rule, you must provide an explicit COLS configuration number inside the tag so the engine knows exactly where to break the character stream lines. Second, let us walk through standard drop-down selection trees using the select, opt group, and option elements. This multi-tiered hierarchical framework allows you to organize massive database tracking choices into clean, human-readable pick lists. We initialize this layout by creating 3 nested layers of tags. First, write your master selection anchor by opening and closing your select tag container pair together, adding a space inside the opening bracket to set its unique ID and its network submission name attribute. To group related options inside the drop-down under an unclickable header, open and close your option group tag pair together inside the select block by writing the letters OPTGROUP inside your angle brackets. Inside this group bracket, add a space and define the category label by writing LABEL, an equals sign, and your category title string inside quotation marks. Now, nest your individual selection units directly inside the opt group boundaries by opening and closing your option tag pairs together. Go inside the opening bracket of each option tag, add a space, and write the word VALUE, an equals sign, and your strict database key token string inside quotation marks, while leaving the open space between the opening and closing option tags populated with user-friendly plain text for human reading. Third, let us examine explicit button definitions and master critical layout behavior known as the button trap. The button element is an explicit container tag pair written by putting the word BUTTON inside a pair of angle brackets, followed immediately by its closing tag with a /. This element offers immense formatting flexibility across development teams because it allows you to nest visual icons, structural style spans, and plain text directly inside its clickable canvas. However, under the standard browser parsing specifications, the default type of a button element placed inside a form is automatically assigned to type equals *submit*. This means if a developer inserts a generic button inside a form layout to trigger an inline calculator or clear a local menu box, but forgets to declare its type explicitly, tapping it will automatically fire the entire form server submission cycle, crashing your user interaction tracking lines. To avoid this trap, you must always declare an explicit type attribute property inside the opening bracket, either type equals *submit* for form submissions, type equals *reset* to wipe the form clean, or type equals *button* to render a blank slate carrying 0 default fallback browser routines. Section 5.6. Advanced Form Techniques. Welcome to the lesson on Advanced Form Techniques. In this session, we are going to dive deep into the highly sophisticated orchestration capabilities of modern HTML architectures. When you are engineering complex corporate application environments or intricate enterprise dashboard panels, you frequently need your data frameworks to bend across complex visual layouts without destroying the semantic layout of your code tree. To achieve this extreme level of structural flexibility, modern HTML provides 2 massive capabilities: localized form control submit overrides and completely decoupled form input links. Let us walk through how these advanced attributes operate in system memory, maintaining our strict engineering workflow of initializing our opening and closing tag pairs together before populating them with properties, spelling out every single attribute and tag token from top to bottom so you can visualize the entire system structure perfectly. Let us look first at form control submit overrides. In a standard interactive workflow, the data transmission parameters are completely dictated by the global attributes declared at the root level inside the parent form tag, meaning every button in that form triggers the exact same network behavior. However, advanced software systems routinely require a single form framework to execute completely different backend functions based on exactly which button a user activates, such as publishing an operational metrics log versus saving a partial draft backup file. To solve this problem without writing heavy JavaScript event handlers, developers implement localized submit overrides declared directly inside the opening brackets of individual button or input submit elements. These localized parameters intercept the form execution loop and completely override the parent settings on a per-button basis. The first property is the form action override, written as FORMACTION. Add a space inside the opening bracket of your button, type the letters FORMACTION, an equals sign, and a secondary destination endpoint URL string inside quotation marks. When clicked, this button routes your payload to an entirely separate server script path. The second property is the form method override, written as FORMMETHOD. Add a space, type the letters FORMMETHOD, an equals sign, and a protocol switch string inside quotes, allowing you to flip a standard POST form into a GET query stream exclusively for that action track. The third property is the form encryption override, written as FORMENCTYPE. Add a space, type the letters FORMENCTYPE, an equals sign, and a media type string inside quotes, which is essential if a secondary button needs to upload binary zip logs while the main form handles plain text. The fourth property is the form target override, written as FORMTARGT. Add a space, type the letters FORMTARGT, an equals sign, and a window context token like quote underscore blank unquote to launch the server response in an isolated browser tab. The fifth property is the form validation bypass, written as FORMNOVALIDATE. Add a space and type the standalone Boolean attribute FORMNOVALIDATE inside your button bracket, which completely shuts down the native browser constraint engine, allowing an incomplete draft dataset to submit immediately without throwing layout validation alerts. Now, let us master decoupled form links using the form attribute. Under legacy HTML layout specifications, any interactive input field, text area, or button had to reside physically within the opening and closing boundaries of a form element to participate in dataset serialization. This rigid layout rule completely handcuffed web engineers, routinely forcing them to compromise their document semantics and break clean table grids purely to wrap interactive cells inside form blocks. Modern specifications completely eliminate this structural deficit by establishing decoupled logical networks in system memory. Imagine an architectural mapping diagram displaying interactive input fields scattered across a distant table grid and a sidebar panel completely outside the form tags, with direct programmatic tracking lines pointing straight back to a single form container located elsewhere in the tree. To construct this decoupled connection framework, you assign a completely unique text identifier to the ID attribute of your master form container. Now, you are free to position your inputs, drop-down pick lists, and activation buttons anywhere else in the entire document object model tree, nesting them inside distant columns, footers, or completely unrelated layout divisions. To link an external element back to your master harvester, you go inside the first opening bracket of the distant input node, add a space, and implement the form attribute. Type the letters FORM, followed by an equals sign, and a pair of quotation marks. Inside these quotes, you input the exact matching ID token string of your target form container. The browser's layout engine compiles the structural link in real time, gathering, and serializing the decoupled elements variables smoothly alongside the core form dataset during execution loops. Chapter 6. Embedded Media. Section 6.1. Images and Pictures. Welcome to Section 6.1, Images and Media Asset Routing Pipelines. In this lesson, we are stepping completely beyond plain narrative textual components, data matrices, and interactive user inputs to master the high-performance graphics embedding architecture of the web. The absolute cornerstone of visual media deployment is the inline image element, written using the characters img. The image tag is a standalone inline void element, which means it carries a self-contained data footprint that never hosts nested child nodes and completely omits a separate closing tag. Despite its minimal footprint in your repository files, it operates as a heavy-lifting network conduit that commands the browser engine's graphics rendering pipeline to intercept, decode, and paint rasterized pixel arrays or scalable vector geometries directly onto the visual stage of the viewport. Let us execute an exhaustive walkthrough of this graphic node, expanding our technical horizon to master the data transport mechanics of the source attribute, known as SRC, by analyzing the crucial structural split between absolute and relative file paths. We will look closely at industry design laws regarding what you must do and what you must actively avoid, responsive collection setups, and next-generation art direction wrappers, executing our strict engineering workflow of spelling out every tag token and configuration parameter from top to bottom so you can visualize the entire system architecture flawlessly. To establish our media asset connection safely, let us analyze the core network properties of our image tag, beginning with the source attribute, written as the letters SRC type a less than sign, the characters img, a space, the letters SRC, an equal sign, and an open quotation mark. The string token you place directly inside these quotation marks serves as a hard-coded lookup pointer that tells the browser's asset loader exactly where to retrieve the binary graphic payload across database records or host directories. Making a direct callback to what we thoroughly mastered when examining the href pathing rules inside the anchor link element. The network routing instructions mapped inside your SRC attribute must conform to one of two absolute architectural layout models, absolute paths or relative paths. An absolute path is a fully qualified uniform resource locator that provides an exhaustive, independent map to a file asset from anywhere on the global Internet network. When you declare an absolute path inside your SRC quotation marks, you must explicitly include the transfer protocol stream, written as HTTP or HTTPS, followed by a literal colon, 2 forward slashes, the domain name host registry, the subdirectory paths, and the final item file name with its format suffix extension. For example, you would type https://cdn.enterprisesystems.com/assets/telemetry.png. Web engineering teams implement absolute path routing whenever they deploy assets onto a decentralized, external cloud server infrastructure or a dedicated content delivery network, known as a CDN. This architecture offers the benefit of decoupling your heavy graphic payloads from your primary web application host. However, it introduces an external runtime dependency, forcing the user's browser to perform additional domain name system resolutions and network handshakes before it can pull the media bytes down to the viewport canvas. Conversely, a relative path defines a localized directory traversal route that is evaluated entirely relative to the current location of the document file within your project's repository tree structure. Because relative paths omit protocol strings and domain registries, they allow software development teams to move entire website application folders across completely different server domains or local staging environments without breaking a single asset link. To master relative file navigation inside your SRC attribute, you must understand the 4 distinct structural movement tokens parsed by the browser engine. The first movement state is same directory selection, implemented when your graphic sits inside the exact same folder level as your active HTML file. You can target this asset by simply typing its raw literal file name, such as metrics.jpg, or by explicitly pinning the local directory anchor using a single dot followed by a / and the file name, written as ./metrics.jpg. The second movement state is subdirectory downward tracking, executed when your asset sits nested inside an adjacent subfolder. You type the name of that specific asset drawer, a /, and the target name, written as assets /analytics.webp. The third movement state is parent directory upward scaling, which is required when your file sits trapped outside the active workspace folder, higher up in the repository hierarchy. To command the browser's file parser to jump back up out of the current folder layer, you use the double dot token. Type a dot, a second dot, and a /, written as /, which shifts the root context up one full level in the directory architecture before you specify your folder tracks and file name targets. The fourth movement state is root relative navigation, initiated by writing a single, lone / character at the absolute beginning of your source string, such as /assets /layout.png. This structural instruction commands the engine to instantly ignore the local file position, completely aborting directory traversal paths to jump all the way back to the root directory origin of the domain before tracking downward, ensuring absolute file paths are mapped uniformly across the entire system network. Directly alongside our source routing attribute, you must always implement our structural accessibility foundation known as the alternative text property, written as the characters ALT. Add a space after your source parameter, type the letters ALT, an equals sign, and a descriptive content string inside a pair of quotation marks. The alternative text is a vital accessibility lifeline. When an automated assistive text-to-speech screen reader hits the image node, it voice synthesizes this literal string to describe the data directly to a visually impaired user. Furthermore, if a network timeout occurs or bad connectivity breaks the asset download stream, the browser engine halts layout rendering and prints this alt string directly inside a broken image frame on the layout canvas so the true contextual intent of the asset is never lost to the user. Let us establish an absolute industry directive regarding what to do and what not to do with alternative text mappings. If an image graphic is purely decorative, such as an abstract background color shape, an aesthetic border separator line, or a stylistic accent grid, you must not write a narrative sentence. However, you must also never omit the alt attribute completely from your code. Instead, you must explicitly declare an empty null string by writing ALT, an equals sign, and two adjacent quotation marks with 0 text inside. This explicit structural null setting signals the browser's internal accessibility tree to silently skip over the node in memory, completely saving blind users from listening to assistive hardware read out raw, unmapped network file names. Now, let us tackle one of the most critical laws of modern layout performance engineering, sizing your media blocks and preventing page layout invalidation. Let us directly address a massive industry failure point and correct a common misconception. Many junior developers mistakenly believe that because modern presentational styling scripts can dynamically resize graphics across viewports using fluid responsive style sheets, they can completely omit the width and height attributes from their raw HTML image elements. Do not do this. Omitting these parameters is a severe structural mistake that actively damages page rendering performance. When you leave them out, the browser engine assigns an initial dimensional state of 0 by 0 pixels to the image node within system memory. As the web page files stream down the line, text rows are parsed and rendered tightly packed together on the screen. Suddenly, seconds later, the binary graphic file finishes downloading over the network, and the browser's layout engine reads the file metadata to discover the image's true layout footprint. The rendering engine is instantly forced to execute an expensive layout recalculation, violently throwing existing text lines downward and creating a jarring layout shift known as cumulative layout shift, or CLS. To achieve absolute visual stability, you must hardcode the raw intrinsic dimensions directly onto your HTML image tag using integers. Type the word width, an equals sign, and your pixel integer value inside quotation marks, followed by a space and the word height, an equals sign, and its vertical integer value inside quotation marks, such as width equals "800" and height equals "450". Crucially, do not write presentation unit symbols like px or percentage tokens inside these quotes. The browser engine requires raw, clean integers. When the layout parser encounters these explicit numbers, it instantly computes the image's exact mathematical aspect ratio before a single byte of the actual binary graphic data streams down the network. The engine leverages this computed ratio to reserve a secure, perfectly proportioned spatial block on the layout canvas, keeping the entire page structure anchored and completely immune to unexpected content jumps. While fluid responsive behavior and maximum width caps can be added later using presentation style rules, these underlying HTML layout attributes must be declared to anchor the document geometry cleanly from the start. To optimize this layout structure for the modern responsive multi-device web, serving a single massive high-resolution graphic to a low-bandwidth smartphone viewport is a massive waste of user data, while serving a tiny mobile file to a high-density Retina desktop display causes blurry pixelation. To resolve this distribution crisis natively, we completely bypass external script libraries and implement the advanced source set property, written as srcset, paired with the layout sizes rule set, written as sizes. This architecture delegates resource allocation calculations entirely to the browser engine, matching real-time viewport parameters against an asset collection matrix. To implement this responsive framework, add a space inside your image void tag and type the letters srcset, followed by an equals sign and a pair of quotation marks. Inside these quotes, you pass a comma-separated array of your available image source file paths, where each individual file path link is explicitly paired with a horizontal width descriptor token written as a trailing number followed immediately by the lowercase letter w. For instance, you write analytics-mobile.jpg space 400w, comma, analytics-tablet.jpg space 800w, comma, and analytics-desktop.jpg space 1600w. This tells the browser's asset manager the exact horizontal pixel dimensions of your raw source files and storage. Next, add a space and declare your layout media guidelines by typing the word sizes, an equals sign, and a pair of quotation marks. Inside these quotes, you map your layout breakpoints using standard media queries coupled with viewport width target tokens. For example, you write left parenthesis max hyphen width colon 600px right parenthesis space 100 VW, comma, followed by 50 VW. This structural statement informs the parsing engine that on small mobile viewports under 600 pixels wide, the graphic will expand to consume 100% of the total screen width, while on wider desktop views, it will occupy exactly 50% of the screen frame layout. Armed with this comprehensive architectural map, the browser engine instantly evaluates the device's screen pixel density and network speed, intercepting the download cycle to fetch the single most optimal resolution file, maximizing system performance without requiring a single line of procedural programming logic. For advanced engineering scenarios demanding complex art direction changes or next-generation media optimization, HTML provides the specialized picture container element, written using the characters PICTURE. The picture element is an explicit wrapper block that manages multiple inner source elements to enforce automated format switching or modify visual layout crops across distinct display footprints. To construct this advanced framework, we open and close our master picture tag pair together by putting the word PICTURE inside our angle brackets. Inside this container block, we place a sequential list of standalone void source elements, written as SOURCE, and we position our primary, classic IMG tag as the absolute final fallback target at the very bottom of the nested list. The browser scans this source list sequentially from top to bottom, evaluating the properties of each tag. To optimize performance via next-generation image formats, you go inside your first opening source bracket and write srcset equals analytics.avif unquote, followed by a space and the type attribute, writing typ equals imag /avif unquote. Directly below it, you write a secondary source tag configured with type equals imag /WEBP. If the host browser's inner compiler supports modern, hypercompressed formats like AVIF or WebP, it intercepts the stream and compiles that specific file format instantly, completely ignoring the remaining code blocks. If it lacks support for modern formats, it safely passes down the tree to compile your standard legacy JPG fallback image tag at the bottom. To execute strict art direction cropping across breakpoints instead of simple format switching, you implement the media attribute on your source tag. Go inside the source bracket, add a space, and write media an equals sign, and a query string inside quotation marks, such as media equals left parenthesis min hyphen width 1024 px right parenthesis unquote, combined with a source set pointing to your panoramic wide landscape layout file. Right underneath, you place a source tag targeting smaller viewports with a source set pointing to your tight, centered mobile vertical square asset. This ensures your visual data remains perfectly framed and fully readable, no matter how drastically a user resizes their display interface canvas. To round out our image toolkit, modern web standards grant developers direct control over runtime performance profiling using explicit download prioritization and resource allocation attributes declared inside the image tag brackets. The first property is native lazy loading, configured via the loading attribute. Add a space, and write the word loading, an equals sign, and the string token lazy inside quotation marks. This structural command tells the browser's asset manager to completely freeze the image download loop if the element sits deep below the fold, deferring data transmission until the user scrolls close to the active viewport perimeter, saving massive system bandwidth. Conversely, for critical above-the-fold hero elements, you can explicitly write loading equals EAGR to force immediate download passes. The second property is asynchronous image processing, handled via the decoding attribute. Add a space, and write the word decoding, an equals sign, and the string value async inside quotation marks. This instructs the graphics pipeline to decode your binary image data off the main user interface thread, completely preventing scrolling stutters and keeping animation routines perfectly smooth. Finally, you can control network priority paths using the fetch priority attribute. Add a space, and write the word fetchpriority, an equals sign, and the high priority string token high inside quotation marks, which commands the network layer to prioritize this specific resource request, accelerating your page's first contentful paint metrics for vital brand assets. Now, let us execute a complete, step-by-step spoken walkthrough of an enterprise-grade, highly optimized production scaffolding blueprint for year 2026, showing exactly how absolute paths, relative traversal links, aspect ratio stability anchors, and next-generation picture formats interlock cleanly within your file repository. We begin by establishing our advanced art direction container, opening our master picture tag by writing a less than sign, the word picture, and a greater than sign. Directly below, on our first nested layer, we place our high-performance absolute path track sourcing an AVIF asset from an external content delivery network for wide viewports. We write less than source, add a space, configure its width boundaries by writing media equals left parenthesis min hyphen width one0 twour px right parenthesis unquote, add a space, and implement our fully qualified source lookup pointer by writing srcset equals https://cdn.entr_assc.com/assetrs/telemtry-wide-width.avif unquote. Before declaring its explicit media format type equals imag/avif unquote and closing the source bracket. Right below, we create a secondary source option utilizing a localized relative path link to catch mobile screens using a WebP asset housed in an adjacent project folder. We write less than source, add a space, Target small screens by writing MEDIA equals quote left parenthesis MAX hyphen WIDTH colon ONE0 TWOTHREEPX right parenthesis unquote, add a space, and execute downward relative directory pathing by writing srcset equals quote ASSETS /MOBILE /TELEMETRY hyphen SQUARE.WEBP unquote, followed by its format descriptor typ equals quote imag /WEBP unquote before closing the bracket. Finally, at the absolute bottom of our picture tree, we embed our classic core image element to act as both our baseline runtime fallback target and the primary anchor for layout stability. We write less than img, add a space, and use parent folder relative traversal to grab a legacy fallback asset by typing src equals quote //fallback hyphen core.jpg unquote. Next, we enforce strict geometry preservation to eradicate layout shift by writing WIDTH equals quote EIGHTHUNDRED unquote and HEIGHT equals quote FOURHUNDRED FIFTY unquote. To ensure fluid browser resource resolution optimizations across the remaining tracks, we append our width descriptor array matrix by typing srcset equals quote fallback hyphen mobile.jpg space fourhundredw, fallback hyphen desktop.jpg space eighthundredw unquote, and map display boundaries by typing sizes equals quote left parenthesis max hyphen width colon sixhundredpx right parenthesis space onehundr edvw fiftyvw unquote. We seal the node with elite performance optimization profiling and accessibility checks by writing loading equals quote lazy unquote, decoding equals quote async unquote, and alt equals quote comprehensive production analytics dashboard grid display mapping real-time system resource allocation datasets unquote, before writing our final greater than sign to close the image void node. We finish the entire media scaffolding block by writing our master closing picture tag with a /. By enforcing this absolute level of routing precision and structural discipline across your assets, your media layers remain flawlessly performance-tuned, fully responsive, and completely optimized for every environment on the web. Section 6.2. Images Maps. Welcome to Section 6.2, Image Maps. In this lesson, we are unlocking an incredibly powerful native architectural capability of HTML that allows developers to transform a single, static visual image into a highly sophisticated matrix of interactive coordinate hotspots without writing separate layout container boxes or relying on presentation style sheets. Imagine an intricate graphical interface, such as a multi-rack data center blueprint layout, a structural map of global network server nodes, or a detailed engineering schematic diagram. With an image map, you can plot precise geometric shapes directly over different visual sectors of that single graphic, giving each localized region its own distinct anchor destination hyperlink and individual accessibility description string. To understand how a browser engine compiles an interactive image map, you must first master the spatial Cartesian coordinate grid system of the digital canvas. When an image renders on a device viewport, the layout engine establishes a two-dimensional grid axis across the surface of the asset. The absolute mathematical origin point is located at the absolute top left corner of the image frame, registering in system memory as coordinate 0, 0. As you trace horizontally across the canvas to the right side, the horizontal x-axis integer value increases pixel by pixel. As you trace vertically downward from the top edge to the bottom edge, the vertical y-axis integer value increases step by step. Every single pixel position across your visual graphic possesses an explicit, unique coordinate identifier representing its exact horizontal and vertical intersections. To help visualize this geometric plotting field before we construct our tags, let us examine an instructive layout diagram displaying rectangular, circular, and polygonal tracking paths actively mapping out coordinate vectors across a visual grid origin. Following our strict, uncompromised engineering discipline, we will always initialize our opening and closing tag boundaries together first in system memory before we ever declare their attributes or populate them with content. This structural habit ensures our document trees remain perfectly balanced and immune to syntax errors. Let us execute our walkthrough of the parent-child nesting framework required to build an image map. We begin by initializing our primary visual asset using the classic inline void image element. Write a less than sign, the letters img, and a greater than sign to establish your standalone void tag bracket. Because this is an inline void node, it carries an empty data structure that completely lacks a separate closing tag. Now, let us go inside that bracket, add a space after the word input, after the word image, and configure its characteristics. Type the letters src, an equal sign, and your file directory string inside quotation marks, such as quote.assets/datacenter.png. To ensure absolute visual stability and eradicate cumulative layout shift, add a space and hardcode the raw pixel layout dimensions by typing width equals "1200" and height equals "600". Crucially, do not append layout units like px inside these quotes. The engine requires clean integers to reserve an exact spatial block on the layout canvas before the asset finishes downloading. To bridge this image directly to our upcoming coordinate system, add a space and implement the specialized useMap attribute. Type the letters USEMAP, followed by an equal sign, and a pair of quotation marks. Inside these quotes, you must write a literal hashtag symbol followed immediately by a unique tracking name string, such as #datacenter-master. This hashtag character is absolutely mandatory. It signals the browser's asset loader to search the document tree for a matching data map coordinate anchor. Now, let us construct the structural coordinate aggregator container known as the map element, applying our strict workflow rules. Write a less than sign, the letters map, and a greater than sign to establish your opening tag, and follow it immediately by typing a less than sign, a /, the characters map, and a greater than sign to lock down the closing boundary. Your container framework is now securely sealed in memory. Step back inside the first opening map tag bracket, add a space after the element token, and implement the global identification link. Type the word NAME, an equal sign, and that exact unique identification name string inside quotation marks, omitting the hashtag prefix entirely, written as name equals "datacenter-master". The browser engine processes this identical match to bind the image and the map together in an unbreakable programmatic bond. To define the individual interactive hotspot targets inside your map container, we nest a sequence of standalone inline area void elements, written using the letters AREA step inside the open, empty space between your closed map tag pair. Write a less than sign, the letters AREA, and a greater than sign. Because this is a standalone void node, it never uses a separate closing tag. Let us look at how the formatting requirements of the coordinates attribute, written as COORDS, alter completely based on your chosen geometric shape string. The first schema is the quadrilateral bounding box, configured via the rectangle shape. Go inside your first open area bracket, add a space, and write the word SHAPE, an equal sign, and the string value token "RECT" inside quotation marks. The rectangle shape demands an array of exactly 4 pixel coordinate integers mapped inside your COORDS attribute, separated cleanly by commas. Add a space, type COORDS, an equal sign, and open your quotation marks. These 4 values must follow a strict sequential path, x1, y1, x2, y2. The first pair of values, x1 and y1, represents the precise horizontal and vertical pixel position of the top left corner of your desired rectangular zone. The second pair of values, x2 and y2, represents the horizontal and vertical pixel position of the diagonally opposite bottom right corner of that same zone. For example, pass the string value "50" 50, 300, 350 unquote. To complete the target, add a space and write href equals /rack -alpha unquote, followed by a space and your absolute mandatory accessibility description string, typing alt equals access performance telemetry records for server rack alpha section unquote. The second schema is the radial zone, handled via the circle shape. Directly below, open a new area tag bracket by writing area, add a space, and set its geometry by typing shap equals circle unquote inside quotation marks. The circle shape requires an array of exactly 3 coordinate integers inside your coordinates attribute, written as x, y, r. Add a space and type CORDS, an equal sign, and open your quotation marks. The first 2 integers, x and y, define the absolute horizontal and vertical pixel center point of your circular target zone, while the third integer, r, defines the exact radius size extending outward from that center point in raw pixels. For instance, write 600, 300, 85 unquote. Complete the node by adding a space and writing href equals /backbone -switch unquote, a space, and your accessibility label alt equals inspect operational diagnostics for central core switch unquote. The third schema is the complex irregular boundary, executed via the polygon shape. Drop down and open your third area tag bracket by writing area, add a space, and set its shape type by writing shap equals poly unquote inside quotation marks. The polygon shape offers limitless architectural flexibility because it accepts an open-ended, sequential array of coordinate pairs representing an infinite list of vertices along an irregular path, written as x1, y1, x2, y2, out to xn, yn. Add a space, type CORDS, an equal sign, and open your quotation marks. You plot each turning point of your irregular shape sequentially around its perimeter, and the browser engine automatically finishes the layout geometry by drawing an implicit line from your final coordinate pair straight back to your original x1 y1 starting points, sealing your complex multi-sided tracking shape. Complete this line by mapping its href path and its explicit descriptive alt string so assistive screen readers can voice its intent clearly to users. Let us issue a critical engineering guardrail regarding what you must actively avoid when deploying traditional HTML image maps. Traditional image maps are inherently static layouts. If an image asset is resized dynamically on a mobile touchscreen using fluid responsive style sheets, such as setting its style width to 100%, the raw visual pixels scale down smoothly, but the underlying HTML coordinates remain completely frozen at their original static values. This creates a severe physical mismatch where the visual targets shift on the glass while the invisible interactive hotspots remain stuck in their original layout scale. For massive production projects that require fluid scalability across infinite breakpoints, industrial web architectures prefer vector-based inline SVG structures over legacy image maps, as vector paths natively recalculate their coordinate systems automatically alongside viewport changes. Now, let us execute a complete, continuous spoken walkthrough of our entire, completed enterprise-grade advanced image map blueprint from top to bottom, reinforcing our initialization rules. We initialize our baseline image tag bracket. Write ~img, add a space, set src equals /assets/datacenter-infrastructure.png unquote, add a space, set width equals 1200 unquote, set height equals 600 unquote, add a space, set usemap equals #dc-mastr unquote, add a space, set loading equals lazy unquote, and seal its accessibility track by writing alt equals main server room floor plan layout diagram unquote. Before typing a greater than sign to close the void graphic node. Directly below, we construct our structural map aggregator container, initializing its boundaries together first. Write less than map and a greater than sign to open the container, and right next to it, write less than /map and a greater than sign to seal the boundary. Now, step back inside that opening map bracket, add a space, and write name equals DC-mastr to complete the programmatic connection link. Step inside the open, empty space between your closed map tags to populate your 3 advanced hotspot targets. Drop down to a new line and write your first rectangular area tag. Write less than area, add a space, set shap equals rect add a space, set coords equals 50, 50, 300, 350 add a space, set href equals /infrastructure /rack-alpha-core and add a space followed by alt equals access telemetry records for server rack alpha core section before writing a greater than sign to close the void area tag. Drop down to the next line to implement your circular target. Write less than area, add a space, set shap equals circle add a space, set coords equals 600, 300, 85 add a space, set href equals /backbone-switch and add a space followed by alt equals inspect diagnostics for central core distribution switch before writing a greater than sign to close the void area tag. Drop down to the next line to implement your irregular multi-sided polygon target tracking sector. Write less than area, add a space, set shap equals poly add a space, and type out its 6 sequential vertex coordinate turning points by writing coords equals 900, 100, 1150, 100, 1150, 500, 1000, 500, 1000, 300, 900, 300 inside quotation marks. Now finish the target line by adding a space, setting href equals //environmental-vault adding a space, and mapping its final accessibility descriptor string alt equals review environmental containment status flags for cryptographic storage vault sector before writing your final greater than sign to close the void area node. Below this line sits your master closing map tag that we initialized earlier, cleanly locking down the entire layout matrix. By masterfully aligning your coordinate tracking anchors, enforcing explicit geometry settings, and initializing your tag pairings systematically, you transform flat graphics into highly interactive, secure, and universally accessible data layers. Section 6.3. Video and Audio. Welcome to Section 6.3, Audio and Video. In this lesson, we are breaking completely away from legacy, security-flawed third-party client plugin architectures, such as obsolete Flash engines, to master high-performance, hardware-accelerated native multimedia streaming runtimes engineered straight inside the browser rendering layer. By implementing native multimedia structures, our web applications gain direct, low-latency hooks into underlying operating system media subsystems, delivering battery-optimized decoding, low-latency playback execution, and advanced time-synchronized accessibility layer loops. To help your animation and design teams visualize this modern hardware-linked playback pipeline before we write our markup code, let us examine an architectural layer diagram displaying a master multimedia container managing network data packets, mapping out multi-codec fallback paths, and aligning synchronized text tracks in system memory. Let us first examine the primary multimedia container elements. To build an audio player framework, write a less than sign, the letters AUDIO, and a greater than sign to establish your opening anchor, and immediately follow it by typing a less than sign, a /, the letters AUDIO, and a greater than sign to seal the closing boundary. To build a video playback framework, follow the exact same structural layout, write a less than sign, the letters VIDEO, and a greater than sign to open the container, and right next to it, write a less than sign, a /video, and a greater than sign to lock down the closing perimeter. Both of these frameworks are explicit container tag pairs designed to enclose nested structural tracks and legacy fallback code blocks. To configure the initial behavior and visual interface state of these runtimes, we declare dedicated control parameters inside the opening tag brackets. The first property is the native controls interface, written as the letters CONTROLS. Go inside the opening bracket of your video tag, add a space after the word video, and type the standalone attribute CONTROLS. This tells the browser engine to paint its native graphical utility panel right over the media canvas, instantly surfacing play and pause triggers, interactive timeline seek bars, volume adjustment sliders, full-screen viewport triggers, and native picture-in-picture options. The second property is the Boolean muting parameter, written as MUTD. Add a space inside the bracket and write the word MUTD to forcibly initialize the media stream's volume profile to 0 decibels. The third property is automated playback execution, written as AUTOPLAY. Add a space and type the word AUTOPLAY to command the engine to decode data packets and fire timeline playback the absolute millisecond the document parser instantiates the node. Let us issue an absolute native user experience safeguard directive here, to protect users from intrusive, data-wasting audio disruptions. Modern web browsers implement strict autoplay blocking matrices. The native engine will permanently kill automated playback execution unless your opening tag explicitly combines the autoplay attribute with the MUTD property, or the underlying audio stream track is completely silent. The fourth property is timeline recycling, written as LOOP. Add a space and type the word LOOP to programmatically tie the completion marker of the video timeline back to the 0-second mark, creating an endless loop. The fifth property is mobile interface preservation, written as the characters PLAYSINLINE. Add a space and type the word PLAYSINLINE inside your video opening bracket. This configuration is vital for touchscreen mobile devices. It forces the video timeline to render directly within its precise inline document layout envelope. Omitting this attribute causes mobile operating systems to hijack the interface, launching an external, non-semantic native application player that breaks your application's visual flow. Second, let us construct a multi-codec resiliency pipeline using the source element. Because different browser platforms, desktop operating systems, and hardware mobile chipsets maintain entirely separate software licensing paths and dedicated hardware decoding chips for proprietary and open-source media containers, serving a single video file format will cause fatal playback failures on non-supported platforms. To achieve zero-fault execution across all user devices without generating separate pages, we implement a multi-source fallback tree inside our containers using the standalone inline void source element, written using the letters SOURCE. Step inside the empty space between your closed video or audio tag pair, write a less than sign, the letters SOURCE, and a greater than sign. Because this is a standalone void tag, it never uses a separate closing token. To configure your source track, add a space inside its bracket and define its file location by typing src, an equal sign, and your file directory path inside quotation marks, such as "media/stream.webm". Next, add a space and define its explicit decoding instructions by writing the type attribute, typing type, an equal sign, and an explicit container plus codec configuration string inside quotation marks. For example, to serve a high-compression open-source file format, write type equals "video/webm codecs equals single quote vp9, vorbis single quote unquote". Directly underneath that node, you open a secondary void source tag pointing to a legacy compatibility container, writing src equals "media/stream.mp4 and type equals "video/mp4 codecs equals single quote avc1.42e01e, m-p-4.40.2 single quote unquote". The browser engine processes this nested sequence from top to bottom, evaluating the capabilities of its internal hardware layers. It executes the absolute first codec configuration it supports, instantly streaming its data bytes down the wire while completely ignoring the remaining code tracks. To manage server data streams intelligently during this initialization cycle, we implement the bandwidth allocation property known as preload, written as preload. Go inside the master opening bracket of your video container, add a space, and write preload, an equals sign, and an explicit engineering allocation token inside quotation marks. If you pass the token string "none," you permanently block network data transmission when the document loads, freezing background buffering entirely until a user physically engages the play icon, maximizing bandwidth conservation on data-heavy system dashboards. If you pass the token string "metadata," the asset loader streams only the initial file header packets, which is the industry standard setting because it safely parses track durations, visual canvas frame dimensions, and language streams without wasting user cellular data on unplayed content. If you pass the token string "auto," the engine initiates background network buffer pipelines immediately, streaming file chunks down the wire to achieve instant, zero latency playback speeds for critical hero assets. Third, let us master the time-synchronized accessibility layer using the track element. The track element is an inline void node nested inside multimedia containers to map external, time-coded text document streams straight into the browser's dynamic subtitle layer. This system relies exclusively on the standardized WebVTT plain text format, ending in a .vtt extension, which maps millisecond-accurate timestamp blocks directly to literal content lines. Step inside the open space between your video tags, write a less than sign, the letters TRACK, and a greater than sign. To configure this accessibility node, you must define 4 distinct attributes inside its bracket. First, add a space and implement the kind attribute, typing KIND, an equals sign, and a structural variant token inside quotation marks. If you pass the token string "subtitles," you load textual translations of spoken dialogue optimized for multilingual internationalization, which requires you to add a space and declare the language marker by writing srclang equals "en" inside quotes. If you pass the token string "captions," you initialize a comprehensive audio-to-text translation layer engineered specifically for deaf or hard-of-hearing accessibility. Captions go beyond simple spoken words to map vital environmental audio data, displaying visual text tracks like bracket alarm klaxon sounds bracket or bracket low sub-bass rumble bracket. If you pass the token string "chaptrs," you map structural navigational milestones along the visual timeline bar, allowing users to jump cleanly across data chapters or video sections. To finalize the track configuration, add a space and map its file path by typing src, an equals sign, and your VTT directory string inside quotes, add a space and set its menu label by writing label, an equals sign, and a human-readable title inside quotes, and you can add the standalone Boolean attribute default to force that specific text string to turn on automatically when the page loads. Now, let us execute a complete, step-by-step spoken walkthrough of our entire, completed enterprise-grade streaming media blueprint codebase. We begin by initializing our visual layout envelope wrapper container tags together bare. Write a less than sign, the letters div, and a greater than sign, and follow it immediately with a less than sign, a / div, and a greater than sign to close the box. Now, step back inside that first opening bracket to declare your layout context, adding a space and typing CLASS equals VIDEO-runtime-WRAPPER. Step inside this wrapper layout space, drop down a line, and initialize your master video container boundaries together first completely empty. Write less than VIDEO greater than to open the tag, and right next to it, write less than / VIDEO greater than to close it, creating a secure open space in between them where our nested source, track, and fallback elements will live. Now, step back inside that first opening video tag bracket to configure its hardware playback parameters. Add a space after the word video, type the standalone interface attribute controls, add a space and type the Boolean muting modifier mutd, add a space and configure its data bandwidth allocation tracker by typing preload equals metadata unquote. Add a space and define a fallback graphical preview card by typing postr equals media-capture-placholder.jpg unquote. Add a space and lock down absolute geometric dimensions to eliminate layout shifts by typing width equals 1920 unquote and height equals 1080 unquote. And add a space followed by the mobile viewport lock attribute playsinline. Now, drop down into the open, empty space inside your video container tags to populate your nested asset streams. On the first line, we write our next-generation open-source video file alternative. Write >source, add a space, set its file track location by typing src equals media-telemetry-matrix.webm unquote, and map its explicit codec parameters by typing typ equals vido/webm codecs equals single quote vp9, vorbis single quote unquote before closing the void tag with a greater than sign. Directly below, on a new line, we map our high compatibility legacy file backup track. Write >source, add a space, set its network link path by typing src equals media-telemetry-matrix.mp4 unquote, and map its data structure by writing typ equals vido/mp4 codecs equals single quote avc1.42e01e, m-p-4.40.2 single quote unquote before closing the void tag with a greater than sign. Moving down, we attach our time-synchronized text overlays for absolute accessibility, writing out our 3 explicit track configurations. On the next line, we initialize our translation subtitle stream. Write >track, add a space, set kind equals subtitles unquote, add a space, set src equals media-tracksdialogue-en.vtt unquote, add a space, set srclang equals en unquote, add a space, set label equals englishsystmsubtitles unquote, and add the standalone attribute default before closing the void bracket with a greater than sign. Directly below, we map our descriptive caption stream for the hearing impaired. Write >track, add a space, set kind equals captions unquote, add a space, set src equals media-tracksaccsbility-en.vtt unquote, add a space, set srclang equals en unquote, and add a space followed by label equals englishsaudiodescriptions unquote before writing a greater than sign to close the bracket. Directly below, we map our navigational milestone index track. Write >track, add a space, set kind equals chapters unquote, add a space, set src equals media-trackscaptrs-mastr.vtt unquote, add a space, set srclang equals en unquote, and add a space followed by label equals systemarchitectures unquote before writing a greater than sign to close the void track tag. Finally, at the absolute bottom of our nested video list, we initialize a secure, semantic layout fallback container block to protect users operating older legacy software machines. Initialize your fallback tags together first entirely empty by writing a less than sign, the letters div, and a greater than sign, and follow it immediately with its closing tag less than /div greater than. Now, step back into that opening fallback bracket, add a space, and write CLASS equals MEDIA-ENGINE-ERROR . Inside this closed fallback space, we type the informative plain text message "The active browser architecture fails to support native, hardware-accelerated HTML media streaming platforms," and insert an explicit direct download link using an anchor element so the user can grab the file assets directly onto their hard drive storage arrays. Below this fallback row block sits your master closing video tag and your closing div tag that we initialized together earlier, cleanly sealing the entire multimedia interactive pipeline. By masterfully aligning your streaming media controls, structuring resilient multi-codec source trees, and syncing time-coded WebVTT accessibility tracks with this rigid level of architectural discipline, you build a bulletproof, energy-efficient, and universally accessible media interface that renders flawlessly across every user device on the web. Section 6.4. Embedded Content. Welcome to Section 6.4, Embedding External Content. In this lesson, we are discovering how to build secure structural gateways that encapsulate outside web resources, document assets, and completely independent third-party software environments right within our core document page layer. Orchestrating these components demands intense focus on security boundary isolation, cross-origin mapping, and sandboxed execution loops. If you deploy external code carelessly, you expose your users to major web vulnerabilities like cross-site scripting, known as XSS, and clickjacking attacks. To help you visualize how a browser isolates these embedded layers, let us examine an architectural diagram showing the security boundary wall created by an iframe sandbox layer separating the parent document from untrusted data streams. Let us master the inline frame element, written using the letters iframe. An inline frame instantiates a completely independent, nested browsing context embedded within your main document tree structure. Under the HTML specification, an iframe is built as a container tag pair. To initialize its boundary tree, write a less than sign, the letters iframe, and a greater than sign to create your opening node, and right next to it, write a less than sign, a /, the letters iframe, and a greater than sign to lock down the closing boundary bear. Now that the tag pair is securely anchored in memory, step back inside the opening iframe tag bracket, add a space after the element token, and define its lookup path by typing src, an equals sign, and your specific path string inside quotes. To secure this pipeline, we implement the specialized sandbox attribute. Add a space inside your opening bracket and type the standalone word sandbox, followed by an equals sign, and a pair of quotation marks. If you declare an empty sandbox property by putting nothing inside the quotes, you trigger a maximum zero trust security shield. To safely restore only the exact operational tracks your application requires, you pass a space-separated matrix of explicit structural tokens inside those sandbox quotes, such as allow scripts to permit internal script execution, allow forms to process form controls, and allow same origin to allow local session cache mapping. Next, manage hardware boundaries by adding a space and typing ALLOW, an equals sign, and your explicit permission string inside quotes. Finally, add a space and type LOADING equals LAZY to defer network request pipelines until a user scrolls close to the frame coordinates. Next, let us examine runtime wrappers used for document parsing, specifically the object element container tag pair. Following our layout discipline, we write less than object greater than and immediately pair it with its closing tag less than / object greater than to seal the block blank in memory. Step back inside the first opening object bracket, add a space, and specify your file resource path by typing DATA, an equals sign, and your target asset path string in quotes. Directly next to it, declare its precise target MIME stream by typing TYPE, an equals sign, and your format identifier string inside quotation marks. If the user's browser fails to compile that specific MIME format, It smoothly ignores the data path entirely and drops inside the closed tag boundaries to process whatever alternative fallback elements you nested between the tag pairs as a graceful failure layout mode. Now, let us execute a complete, continuous spoken walkthrough of our entire, completed enterprise-grade advanced external content encapsulation blueprint, demonstrating our strict tag initialization workflow from top to bottom so you can visualize the data tracking pipeline perfectly. We begin at line 1 of our file by initializing our master layout envelope wrapper container tags together entirely bare. Write >div greater than to open the element, and write /div greater than right next to it to close it. Step back inside that opening bracket, add a space, and type CLASS equals extrnal-resource-envelope unquote. Step inside the empty space between those closed div tags and drop down a line to create our descriptive header. Initialize an h3 header tag pair together bare by writing h3 greater than followed immediately by /h3 greater than. Step inside the boundaries of this sealed header and type the content text secure corporate telemetry processing node unquote. Directly below, on a new line, we construct our secure sandboxed frame pipeline, initializing the container pair together first. Write iframe greater than and follow it immediately by typing /iframe greater than to seal the frame boundaries blank in system memory. Now, step back into that opening iframe tag bracket to configure its extensive security variables. Add a space after the word iframe. Set its resource source tracker by typing src equals https://analytics-core.entrprise-hyphen-embrix.embed/node-0 unquote, add a space, and satisfy mandatory global accessibility rules by typing title equals real-time system matrix core analytics dashboard frame unquote. Next, implement your zero trust authorization lock parameters by adding a space and typing sandbox equals allow-scripts space allow-forms space allow-same-origin unquote. Configure its hardware permissions by adding a space and typing allow equals golocation semicolon encrypted-media quote. Optimize network loading profiles by adding a space and typing loading equals lazy unquote, and stabilize its structural grid dimensions by adding a space and typing width equals 100% unquote and height equals 650 unquote. Moving down to a new row, initialize a thematic separator void line by writing a single, standalone hr greater than bracket block. Directly below that line, initialize your structural section header container pair together bare. Write h3 greater than and /h3 greater than together, step inside, and type the title phrase system engineering architecture documentation unquote. Directly below that header row, we implement our resilient multi-tier document object handling matrix, initializing its outer container boundaries together first entirely bare. Write object greater than and write /object greater than right next to it to lock down the boundary envelope. Now, step back inside that first opening object tag bracket to attach its asset metadata properties. Add a space after the word object. Declare its file track location by typing data equals docs/manual-v12.pdf unquote, add a space. Define its media type string typ equals application/pdf unquote, and anchor its display boundaries by typing width equals 100% unquote and height equals 800 unquote. Now, drop inside the open, empty space between your closed object tag pair to engineer your alternative visual accessibility fallback block. This entire content row remains totally dormant in modern web viewports unless the underlying rendering engine lacks a native PDF viewing plugin context. First, initialize your internal fallback layout panel container tags together bare. Write less than div greater than followed immediately by less than / div greater than. Step back into its opening tag bracket, add a space, and type class equals plugin hyphen failure hyphen fallback hyphen panel unquote. Step inside this fallback div space to write your warning text nodes. First, initialize an h4 alert header tag pair together bare. Write less than h4 greater than and less than / h4 greater than together, step inside, and type the text native document plugin evaluation alert unquote. Below that heading, initialize a paragraph container tag pair together bare. Write less than p greater than and less than / p greater than together, step inside, and type the message the host browser architecture lacks a native document plugin tool to render the documentation manual layout inline unquote. Below that paragraph row, initialize a secondary paragraph container tag pair together bare by writing less than p greater than and less than / p greater than. Step inside the second paragraph container and type the initial text string please access the document data records directly by executing a local download : unquote. Right next to that text token, still inside the paragraph boundaries, we embed our structural file download link anchor, initializing its tag pair together bare first. Write less than a greater than and less than / a greater than together. Step back inside its opening anchor bracket, add a space, set its directory target path by typing href equals docs /manual v12.pdf unquote, and implement the native hardware download trigger property by adding a space and typing download equals entrprise manual v12.pdf unquote. Finally, step inside the canvas text field of your sealed anchor tag pair and type the display text label download raw PDF manual archive, 3.4 megabytes, unquote. Reviewing your tree structure, below this link sits your closed paragraph tag, your closed fallback div panel tag, your master closed object tag matrix, and the ultimate closed master envelope division div tag that we initialized together at the very start of our project file. By masterfully executing your external content gateways using this hyperdisciplined approach, initializing tag pairings completely bare in system memory before appending attributes, locking down a frame permissions grids, and constructing multi-tier fallback object paths using clean digits, you deliver an industrial-grade, highly secure, and exceptionally resilient layout architecture that parses flawlessly across every web platform. Section 6.5. Inline Graphics. Welcome to Section 6.5, Inline Graphic Schemas and Mathematical Runtime Architectures. In this lesson, we are breaking completely away from standard external file referencing channels to master the hyper-efficient world of inline geometric data layout compilation. Up to this point in Chapter 6, we have treated graphics and media elements as separate binary files that the browser must fetch over the network using resource paths inside src or data attributes. While that workflow is perfect for massive rasterized imagery or continuous multimedia streams, it introduces an inherent network request latency and completely isolates those elements from the active document tree. To solve this problem for vector illustrations, complex equations, and dynamic programmatic drawing boards, modern HTML allows XML-based syntax structures to be interleaved directly within the text document stream. This inline approach causes elements to render instantly during the initial document parser phase, saves valuable HTTP connection bandwidth, and drops these elements directly into the main document object model tree as live, targetable data nodes. Let us execute an exhaustive technical deep dive into this integrated ecosystem. We will explore the semantic structure of mathematical markup language deeply, introduce the architecture of vector assets and canvas pixel fields, and execute our strict engineering workflow of initializing our opening and closing tag pairs completely bare in system memory before we ever declare their attributes or fill their canvases with data. Let us first master the deep, analytical syntax of mathematical markup language, written as the characters MATHML. For generations, displaying complex scientific equations, fractions, square roots, and algebraic matrices on a web page was a massive headache, forcing development teams to either upload static images of formulas, which broke text alignment when fonts scaled, or load heavy, performance-dragging client-side formatting script libraries. MathML resolves this natively by treating equations as structured semantic layout trees. The browser engine reads these specialized tags and automatically applies exact mathematical typography spacing rules recursively in memory. To understand how this formatting tree computes variables and expressions, you must master its core vocabulary of semantic tokens. The absolute root of any mathematical block is the math element, which tells the parser to switch its compilation layer to math rendering physics. Inside this container, expressions are broken down horizontally into distinct structural blocks using the math row element, written row. To define individual text components within a row, you must wrap them in precise data type wrappers, alphabetical variables, symbols, and algebraic characters like $x$, $y$, $a$, or $b$ are wrapped inside the math identifier node, written me, which tells the engine to automatically italicize the character. Plain numerical values and raw digits are wrapped in the math number node, written mn, which keeps the font face clean, blocky, and strictly vertical. Mathematical operators, equal signs, plus symbols, and structural wrappers like brackets are contained within the math operator node, written mo. To scale equations vertically across multi-tier structures, MathML provides advanced spatial container tags. The math fraction element, written frac, accepts exactly two nested child rows. The first child node is computed as the numerator layout, and the second child node is computed as the denominator layout. The math square root element, written MSQRT, acts as a structural wrapper that automatically draws a perfect radical line across the top of all its internal child elements, scaling dynamically based on the total width of the nested tokens. The math superscript element, written sup, attaches an exponent to a base variable. It requires exactly two sequential child elements inside its brackets. The first node defines the base factor, and the second node acts as the elevated exponent value. By combining these structural blocks recursively, you can construct clean, accessible equations that screen readers can natively voice step by step to a user. Next, let us introduce the architecture of vector assets using the scalable vector graphics element, written using the letters SVG. Sourcing a vector file through a standard image link turns that graphic into an uninspectable flat box. However, dropping raw SVG code straight into the HTML document tree places the underlying graphic vectors right inside the DOM. This means every internal component, such as a coordinate path written as path, a circle written as circle, a rectangle written as rect, or a grouped graphic track written as G, becomes a true, live document node. These individual shapes can be targeted cleanly by interactive mouse events, and any text components nested inside them remain fully readable to screen reader devices and searchable by web crawlers. To define the rendering boundaries of a vector asset, you use the critical viewbox attribute, which maps out the internal coordinate system and aspect ratio of the vector workspace canvas using four clean, space-separated integers representing its minimum x-axis, minimum y-axis, horizontal width scale, and vertical height scale. However, let us establish an absolute production reality here, because scalable vector graphics carry a massive, infinite universe of geometric shapes, complex path plotting nodes, reusable symbol grids, structural clipping masks, and native programmatic animation controls. The SVG specification is too infinitely deep to truncate here and fully deserves an entire multi-part standalone video course of its own. For this chapter, we will master its core initialization hooks and accessibility roles to ensure it integrates seamlessly with our document layouts. Similarly, let us introduce the dynamic pixel drawing canvas element, written using the letters CANVAS. Unlike the declarative nature of an inline SVG, which populates the document tree with explicit nested shape elements, a canvas is completely devoid of internal document code nodes. It acts as an empty container framework designed to expose an open, high-performance pixel backbuffer workspace straight to client-side procedural scripting engines, such as the HTML5 2D context or hardware-accelerated WebGL API pipelines. To configure a canvas space properly in your markup files, you must obey the absolute dimension boundary law by explicitly hard-coding width and height attributes using clean digits directly onto the HTML tag. If you omit them, the browser engine applies a standard default hardware buffer size of 300 pixels wide by 150 pixels high. Let us address a massive layout trap and structural performance warning regarding canvas scaling. There is an absolute difference between changing the intrinsic attributes on the HTML tag versus modifying visual sizes later via presentational styles. The HTML properties dictate the actual number of targetable drawing pixels instantiated in system memory. If you leave these attributes off and try to scale a canvas up using style parameters, the browser takes that small default 300 by 150 pixel coordinate grid and forcibly stretches it out like a cheap rubber bitmap sheet, resulting in heavy blurriness and edge pixelation. Furthermore, because a canvas maps raw pixels directly into memory, search engine crawlers and screen readers are completely blind to whatever is drawn dynamically inside its frame. To eliminate this severe accessibility deficit, the HTML specification establishes a nested fallback channel pattern. Any elements, semantic text blocks, data tables, or anchor links placed directly between the opening and closing canvas tags are computed entirely as an accessibility alternative layer. When a script runs successfully, the browser hides this internal block entirely from viewports while drawing graphics over the top. If a script drops out, a network restriction blocks execution, or a blind user encounters the node, the engine completely bypasses the pixel plane and reads the nested alternative content data structure directly. However, because a canvas functions strictly as an empty vessel awaiting execution parameters from complex algorithmic code structures, the Canvas Drawing API and WebGL Rendering Loop fully deserve an entire separate dedicated video guide series of their own. For our structural roadmap, we will master its markup envelope setup and fallback data tree assembly. Section 7.1. Interactive Elements and Web Components. HTML side. Welcome to Section 7.1, Native Disclosure Widgets. In this lesson, we are discovering how to build interactive, expandable accordion-style components using purely declarative markup rules. Up to this point in our architecture course, making content toggle open and closed on a user click required writing custom procedural scripts or manipulating input state hacks inside presentation-style sheets. The details and summary elements completely eliminate this complexity by providing a native, browser-driven disclosure engine directly inside the rendering layer. When a user interacts with this component, the browser automatically calculates the layout canvas changes, shifts the display boxes, and instantly updates the accessibility tree without a single line of JavaScript. To help your layout teams visualize how the browser manages these expandable blocks natively, let us examine an architectural state mapping diagram displaying the internal mechanics of a disclosure widget transitioning between its collapsed and expanded states. Let us analyze the operational runtime engine of this disclosure widget, which is entirely governed by the presence or absence of the global Boolean attribute known as open. When a document parses, the component operates in one of two distinct states. In the collapsed state, when the open attribute is completely absent from your code, the layout engine executes a highly optimized visibility suppression routine. It loops through the node tree and skips the painting execution phase for all nested content blocks inside the widget, rendering only the primary summary tag. The hidden child elements are fully instantiated inside the live DOM memory, but they occupy exactly zero physical space on the layout canvas, preventing them from interfering with your structural flow. Conversely, when the open attribute is present on the tag, the engine activates the expanded state profile. It instantly calculates the layout bounds of the internal child subtree, paints the nested text fields down the wire to the viewport canvas, and fires a native system toggle event to update the browsing context. Let us break down the accessibility tree integration and presentational layout rules for these nodes. The browser engine automatically applies an implicit ARIA roll button to your summary tracking tag. It maps state changes automatically, flipping ARIA expanded equals false to ARIA expanded equals true in perfect synchronization with your visual updates. Visually, the user agent automatically prepends a native disclosure triangle indicator icon directly to the left side of your summary content text. This icon is rendered using a pseudo-element known as the marker selector. If your user experience specifications demand a completely customized design layout, you can disable this default browser triangle arrow by targeting your summary element and explicitly declaring a presentational rule of list style, none, combined with a vendor-specific fallback style property to erase the marker footprint cleanly. Step-by-step spoken code walkthrough. Now, let us execute a complete, continuous spoken walkthrough of our production-grade native disclosure widget blueprint, demonstrating our strict tag-saving initialization workflow from top to bottom so you can visualize the data architecture perfectly. We begin at line 1 of our layout block by initializing our master structural box wrapper container, pairing our tags together completely bare first. Write less than details greater than to open the element, and right next to it, write less than / details greater than to lock down the closing boundary. Now that the master framework is safely anchored in system memory, step back inside that first opening details tag bracket, add a space after the word details, and define its identity and runtime state properties. Type the tracking attribute ID, an equals sign, and your unique identification string inside quotation marks, written as ID equals diagnostic accordion. Next, add a space and enforce an initial open visibility state by typing the standalone Boolean attribute open. Step inside the open, empty space between those closed details tags, drop down a line, and construct your interactive semantic trigger control node, applying our pairing rules perfectly. Initialize the summary tag boundaries together first entirely bare. Write less than summary greater than followed immediately by less than / summary greater than to seal the boundary line. Because this node is completely enclosed, step inside the core text track of this sealed summary tag pair and type the human readable visual display string, System Analytics Architecture Registry. Directly below that summary row, still inside the master details container, we build our hidden disclosure content compartment, initializing its tag structures together first completely bare. Write less than div greater than and write less than / div greater than right next to it to secure the envelope block. Step back inside that opening division bracket, add a space after the word div, and assign its style hook parameters by typing class equals disclosure content envelope . Now, drop inside the open space between those closed division tags to populate the hidden data fields. Drop down a line and initialize a structural paragraph container tag pair together bare. Write less than p greater than followed immediately by less than / p greater than to close it. Step inside the text canvas area of this sealed paragraph pair and type the hidden content statement string. Operational status flags have successfully verified all clean core ingestion parameters. Reviewing your completed element tree, below this text row sits your closed paragraph tag, your closed internal content division box tag, and the ultimate master closing details tag that we locked down at the very initialization phase of our file setup. By masterfully orchestrating your interactive disclosure panels using this hyperdisciplined approach, initializing tag pairings completely bare in system memory before appending attributes, leveraging the browser's native state execution engine, and monitoring layout visibility profiles with clean digits, you build a highly resilient, performant, and universally accessible document interface that parses beautifully across every client viewport on the web. Section 7.2. Welcome to Section 7.2, Document Modal Layer Configurations. In this lesson, we are exploring the native HTML dialog element, a powerful architectural structure designed to handle modal and non-modal overlay panels natively within the browser rendering engine. Historically, creating a pop-up modal required heavy JavaScript libraries, complex Z-index layering, and delicate manual keyboard focus trapping routines to prevent screen readers from leaking back into the background content. The native dialog element renders all of these workarounds obsolete by providing built-in top-layer rendering pipelines, native focus isolation loops, and automated form synchronization states directly out of the box. To help your production and rendering teams visualize how the browser handles overlay boundaries, let us examine an architectural diagram mapping out a native modal component floating above the main document canvas within the browser's sovereign top-layer stacking space. Let us analyze the operational mechanics of the dialog layout block. A dialog frame can be toggled into one of two distinct visual profiles depending on which native method is called. When you activate it using the standard .show method, it initializes as a non-modal panel. In this mode, it behaves like a standard floating inline asset box, staying constrained within its relative document tree stacking order and allowing full user interaction with background page elements. Conversely, when you activate the element via the programmatic .show modal method, the browser engine fires its top-layer overlay script. This action detaches the visual box from normal page layout physics and places it in a sovereign overlay stack rendering above every single node on the canvas, completely bypassing any CSS index properties. Simultaneously, the engine attaches an automatic keyboard focus trap, looping the tab key exclusively through interactive inputs within the dialog. It also generates a full-screen background overlay layer directly beneath the box, targetable natively via the backdrop CSS pseudo-element. A major capability of this specification is its native integration with the browser form engine. When an interactive form nested inside a dialog container is explicitly declared with method equals dialog, submitting the form triggers an automated intercept loop. The browser completely bypasses standard network URL routing, prevents page reloads, closes the target dialog frame automatically, and catches the explicit string passed to the activation button's value attribute. This string is then populated natively onto the dialog element's DOM return value property for instant processing. Now, let us execute a complete, continuous spoken walkthrough of our production-grade native dialog modal configuration blueprint, demonstrating our strict tag pairing initialization workflow from top to bottom so you can visualize the data architecture perfectly. We begin at line 1 of our layout view by constructing our master overlay frame container, initializing our tags together completely bare first. Write less than dialog greater than to open the element, and right next to it, write less than / dialog greater than to lock down the closing boundary completely bare. Now that the framework is securely anchored in memory, step back inside that opening dialog tag bracket, add a space after the word dialog, and assign its system identification handle. Type the tracking attribute ID, an equals sign, and your unique identification string inside quotation marks, written as ID equals system authorization modal. Step inside the open, empty space between those closed dialog tags, drop down a line, and construct your internal structural grid division wrapper, pairing your tags together completely bare first. Write less than div greater than followed immediately by less than / div greater than to seal the boundary box completely bare. Step back inside that opening division bracket, add a space after the word div, and set its design layout hooks by typing class equals dialog internal grid . Now, drop inside the open space between those closed grid division tags to populate your internal modal text headings and descriptions. Drop down a line and initialize an H4 section heading tag pair together completely bare first. Write less than H4 greater than and right next to it write less than / H4 greater than to lock down the boundaries. Step inside the text bounds of this sealed heading pair and type the display content, critical ingestion override authorization required. Directly below that header row, initialize a structural paragraph container tag pair together completely bare first. Write less than p greater than and less than / p greater than together to seal the boundary. Step inside this sealed paragraph text area and type the notification statement, *, you are accessing an isolated runtime node gateway layer. *. Directly below the descriptive paragraph line, we implement our automated form closing execution stack, initializing our container tags together completely bare first. Write less than form greater than and right next to it write less than / form greater than to secure the boundary completely bare. Step back inside that opening form tag bracket, add a space after the word form, and declare its specialized closing processing behavior by typing method equals dialog unquote. Next, add a space and define its layout hook style identifier by typing ID equals modal closure form unquote. Drop inside the open, empty space between those closed form tags to deploy your explicit closure buttons, applying our tag pairing rule cleanly to each input element. On the first line, initialize a cancellation button container tag pair together completely bare first. Write less than button greater than followed immediately by less than / button greater than to lock down its boundaries completely bare. Step back inside that opening button bracket, add a space after the word button, define its input behavior by typing type equals submit unquote, add a space and map its cancellation data string by typing value equals abort unquote, and add a space followed by class equals btn cancel unquote. Now, step inside the inner text track of the sealed cancellation button pair and type the visual action label, abort link execution. Directly below on a second line, initialize your confirmation button container tag pair together completely bare first. Write less than button greater than and less than / button greater than together to seal the boundary line completely bare. Step back inside that opening button bracket, add a space after the word button, set its element behavior by typing type equals submit unquote, add a space and assign its tracking return payload token by typing value equals authorize _confirmed unquote, and add a space followed by class equals btn confirm unquote. Step inside the core text path of this sealed confirmation button pair and type the display command, confirm credentials. Now, step completely outside of your sealed master dialog container block, drop down 2 lines, and let us construct the external page control trigger button that users will click to open the modal interface. Initialize this activation button tag pair together completely bare first. Write less than button greater than and follow it right next to it with less than / button greater than to secure the boundary loop completely bare. Step back inside that opening button bracket, add a space after the word button, and attach its native click execution block. Type the interactive property handler onClick, an equals sign, and open your quotation marks. Inside these quotes, reference your target modal element identifier and call its top layer initialization command by typing your dialog id.showModal followed immediately by an empty set of parentheses, written as onClick equals systemauthorization_modal.showModal. Finally, step inside the open text space of this sealed trigger button pair and type the display instruction, open modal layer. Reviewing your complete node hierarchy, you have initialized your external trigger button pair, your master structural dialog frame container pair, your internal layout grid divisions, and your nested form rows completely bare and sealed in system memory before filling their properties or data tracks. By masterfully aligning your modal overlays using this hyperdisciplined approach, you establish an exceptionally secure, performance-optimized, and universally accessible layer configuration that displays flawlessly across all computing environments. Section 7.3. Popover API. Welcome to Section 7.3, the Popover API, Structural Setup and Linkage Bindings. In this lesson, we are discovering a revolutionary native capability of HTML that allows us to create layered user interface elements like tooltips, drop-down menus, and informational overlays completely declaratively. Up to this point, creating any floating layout box that sits on top of your main page required writing absolute layout containers, managing overlapping layer positions, and using script handlers to show or hide the box when a user clicks a button. The Popover API completely replaces that manual architecture. By using simple, native HTML attributes, the browser handles the layering, rendering orchestration, and user dismissal rules entirely on its own. To help your production team visualize how the browser natively isolates and tracks these floating boxes, now, let us execute a complete, continuous spoken walkthrough of our production-grade native popover linkage blueprint, demonstrating our strict tag pairing initialization workflow from top to bottom so you can visualize the data architecture perfectly. We begin at line 1 of our template file by constructing our interactive control trigger element, initializing our tags together completely bare first. Write less than button greater than to open the element, and right next to it, write less than / button greater than to lock down the closing boundary completely bare. Now that the tag pair is securely anchored in memory, step back inside that first opening button tag bracket, add a space after the word button, and establish your declarative linkage properties. Type the attribute popovertarget, an equals sign, and your target container's unique identifier inside quotation marks, written as popovertarget equals telemetry dropdown. Next, add a space after those quotes and define the trigger click action by typing popovertarget equals quote toggle unquote. Now that your button attributes are set, step inside the inner text track of this sealed trigger button pair and type the display visual command label, inspect telemetry metrics. Directly below that trigger button line, we build our native floating popover box container, initializing its layout tags together completely bare first. Write less than div greater than and follow it right next to it with less than / div greater than to secure the framework envelope completely bare. Step back inside that first opening division tag bracket, add a space after the word div, and assign its matching tracking identification handle. Type the selector attribute ID, an equals sign, and the exact matching string value inside quotation marks, written as ID equals telemetry dropdown. Next, add a space after those quotes and activate its native browser overlay profile by typing popover equals quote auto unquote. Now, drop inside the open, empty space between those closed popover division tags to populate your internal structural dashboard content. Drop down a line and initialize an H4 section heading tag pair together completely bare first. Write less than H4 greater than and less than / H4 greater than together to seal the boundary lines. Step inside the text bounds of this sealed heading pair and type the display content phrase, livestream status flags. Directly below that header row, still inside the popover container, initialize an unordered list data aggregator frame, pairing your tags together completely bare first. Write less than ul greater than followed immediately by less than / ul greater than to lock down the list boundaries completely bare. Step inside the open space between those closed unordered list tags, drop down a line, and construct your individual list data item rows, applying our strict pairing rule cleanly to each row element. On the first line, initialize your first list item container tag pair together completely bare first. Write less than = greater than and less than / = greater than right next to it to seal the boundary. Step inside the core text track of this sealed first list item pair and type the data reporting string, node ingestion, normal. Directly below on a second line, initialize your second list item container tag pair together completely bare first. Write less than = greater than and less than / = greater than together to lock down the boundary line completely bare. Step inside the text path of this sealed second list item pair and type the remaining diagnostic metric string, buffer bounds, 0 errors. Reviewing your complete code hierarchy, you have initialized your external controller button pair, your master structural popover division container pair, your internal textual headings, and your nested list data rows completely bare and sealed in system memory before filling their properties or data fields. By masterfully orchestrating your interactive overlays using this hyperdisciplined approach, you establish an exceptionally secure, performance-optimized, and universally accessible layer configuration that displays flawlessly across all computing environments without a single line of JavaScript or CSS. Section 7.4. Web Components Basics. Welcome to Section 7.4, Web Components Basics, Template, Slot, and Custom Elements. In this lesson, we are discovering how to construct modular, reusable layout blueprints directly inside the native HTML markup engine. Up to this point in our development workflows, creating repeatable UI elements meant copying and pasting blocks of code across different files or relying on external frameworks to inject structures into our pages. HTML natively resolves this architectural bottleneck by introducing a standard suite of element hooks that store hidden markup fragments, define content injection windows, and bridge semantic elements directly to modular component definitions. This pure HTML setup allows us to ship highly structured component envelopes down the wire that remain completely invisible until they are instantiated. To help your layout teams visualize how these component layers arrange themselves, let us look at an architectural diagram mapping out a reusable component blueprint containing internal structural slots awaiting external data deployment. Let us analyze the operational mechanics of the three fundamental pillars of HTML web components. The first pillar is the template element, which functions as a specialized structural storage vault. Any elements, text blocks, or graphics nested inside a template container are classified by the browser as inert markup content. The parsing engine reads the tag syntax, validates the element tree integrity, and holds it quietly inside system memory, completely suppressing network asset downloads, rendering passes, or layout box calculations. The content exists as a dormant fragment until it is called into the visible page layout. The second pillar is the slot element, which operates as an explicit entry gateway or placeholder nested inside a component template. It enables external layout content from the main page body to safely project straight into designated zones of your modular template structure. You can deploy slots in two ways. A default slot features no identifying markers and acts as a catch-all funnel for generic data, while a named slot uses an explicit identification string to map multiple, distinct content insertion points. The third pillar is the HTML site integration bridge for custom elements, handled via the Semantic customized built-in element parameter known as the isAttribute. By declaring this attribute on a standard native tag, you instruct the browser that the element must retain its full native accessibility roles and foundational layout rules while preparing its envelope to seamlessly absorb a modular component asset blueprint. Now, let us execute a complete, continuous spoken walkthrough of our enterprise-grade reusable component blueprint, demonstrating our strict tag pairing initialization workflow from top to bottom so you can visualize the data architecture perfectly. We begin at line 1 of our project view by constructing our master inert blueprint container, initializing our tags together completely bare first. Write less than template greater than to open the element, and right next to it, write less than / template greater than to lock down the closing boundary completely bare. Now that the master framework is safely anchored in memory, step back inside that opening template tag bracket, add a space after the word template, and assign its structural identification handle. Type the configuration attribute ID, an equals sign, and your unique identity string inside quotation marks, written as ID equals system card blueprint. Step inside the open, empty space between those closed template tags, drop down a line, and construct your internal structural component wrapper box, pairing your tags together completely bare first. Write less than div greater than followed immediately by less than / div greater than to seal the boundary envelope completely bare. Step back inside that opening division bracket, add a space after the word div, and set its layout style selector hook by typing class equals card envelope . Now, drop inside the open space between those closed wrapper division tags to engineer your multi-tier component layout sections. Drop down a line and construct your component header panel, initializing your container tags together completely bare first. Write less than header greater than and write less than / header greater than right next to it to lock down the boundary completely bare. Step back inside that opening header bracket, add a space after the word header, and define its layout hook style identifier by typing class equals card header zone . Step inside the open, empty space between those closed header tags to deploy your first advanced content projection slot, pairing your tags together completely bare first. Write less than slot greater than followed right next to it by less than / slot greater than to seal the boundary line completely bare. Step back inside that opening slot bracket, add a space after the word slot, and transform it into a dedicated named insertion window by typing name equals "card title". Now, step inside the inner text track of this sealed named slot pair and type your fallback display content phrase, fallback system heading. Next, step completely past that closed header block but stay inside your closed master wrapper division, drop down a line, and construct your component body panel, initializing your container tags together completely bare first. Write less than section greater than and less than / section greater than together to lock down the boundary completely bare. Step back inside that opening section bracket, add a space after the word section, and define its structural placement hook by typing class equals "card body zone". Step inside the open, empty space between those closed section tags to deploy your generic content projection gateway, pairing your tags together completely bare first. Write less than slot greater than followed right next to it by less than / slot greater than to seal the boundary completely bare. Leave the internal tracking space of this standard default slot entirely empty, allowing it to serve as an open catch-all funnel for incoming data blocks. Finally, step completely outside of your sealed master template container block, drop down 2 lines, and let us construct an extended custom button element that maps directly to our component logic on the HTML side. Initialize this custom button tag pair together completely bare first. Write less than button greater than and follow it right next to it with less than / button greater than to secure the boundary loop completely bare. Step back inside that opening button bracket, add a space after the word button, and attach your declarative custom element binding connection link. Type the specialization parameter attribute is an equal sign, and your unique custom component identifier string inside quotation marks, written as is equals fancy button. Finally, step inside the open text space of this sealed custom button pair and type the display instruction text, "Click me." Reviewing your complete node hierarchy, you have initialized your master structural template container pair, your internal layout division boxes, your component headers, your named and default projection slots, and your external custom button triggers completely bare and sealed in system memory before filling their properties or content tracks. By masterfully orchestrating your modular blueprints using this hyperdisciplined approach, you establish an exceptionally clean, performance-optimized, and universally stable web component architecture that loads flawlessly across all browsing environments. Chapter 8. Global Attributes, Microdata and the Rest. Section 8.1. Global Attributes. Welcome to Section 8.1, Global Attributes, Complete Overview. In this lesson, we are mastering the universal configuration parameters that can be validly declared on every single element node across the entire HTML specification. Up to this point in our course, we have looked at highly specialized attributes built exclusively for single tags, such as the source attribute for images or the method attribute for forms. Global attributes are completely different. They act as a foundational layer of global controls that provide standard hooks for document styling, internationalization parsing, keyboard focus routing, inline editing loops, and custom programmatic data tracking on any element container you build. To help your development teams visualize how these universal flags bind directly to active element structures in browser memory, let us examine an architectural diagram mapping out global attribute states tracked directly inside the living document object model tree. Let us analyze the operational mechanics of these global parameters across their 5 primary behavioral categories. Now, ID and class we have already used, but let us take a quick look at them again along with the other global control anchors. The unique identifier attribute, written as ID, assigns a case-sensitive identity token to a specific element node. This token must be entirely unique across the active page canvas to ensure rock-solid anchor jumping and element target lookups. The class attribute assigns a space-separated list of presentational selector tokens to an element, mapping the node to external style sheets. The style attribute houses raw presentational code directly inside an element's opening bracket. Let us issue a critical architectural design warning here. Using the inline style attribute is a direct violation of the separation of concerns principle. It mixes presentation layer mechanics directly into structural semantic files, making your layouts highly fragile and incredibly difficult to maintain at scale. To finish our core anchors, the title attribute offers a generic text string description that user agents typically display as a floating visual tooltip panel when a user hovers their cursor over the element box. The second category governs internationalization, text direction, and automated translation pipelines. The language attribute, written as lang, declares the primary human language context of your text content using standardized language subtag codes, such as lang equals N for English, lang equals ES for Spanish, or lang equals Hi for Hindi. It directly guides font rendering selections, screen reader pronunciation loops, and browser translation matrices. The direction attribute, written as dir, sets the layout flow of text streams. Setting dir equals LTR enforces standard left-to-right processing, while dir equals RTL activates right-to-left tracking for scripts like Arabic or Hebrew. If you declare dir equals auto, the browser engine automatically analyzes the first character containing strong directional data and toggles the layout flow on its own. To protect technical data, you use the translate attribute. Setting translate equals no explicitly locks down technical keywords, brand identifiers, server strings, or code fragments from being altered and corrupted by automated translation services. The third category manages interactivity and viewport keyboard focus indexing states. The tab index attribute configures keyboard tab focus routing profiles. Passing an integer of 0 inserts a naturally non-interactive container directly into the natural keyboard tab flow, while passing an integer of -1 removes the node from the sequential tab loop entirely while keeping it open to programmatic focus redirects. The global Boolean attribute autofocus commands the layout processing engine to instantly capture viewport keyboard focus onto your designated element the absolute millisecond the parser instantiates the tag during page initialization. The content editable attribute converts standard text containers into live interactive text editors. Setting content editable equals true opens character input privileges, while nesting content editable equals false inside an editable container isolates specific badges or metadata text boxes from being modified. The spellcheck attribute toggles linguistic dictionary verification over these inputs, where setting spellcheck equals false kills noisy grammatical error lines when editing technical documentation or alphanumeric server query strings. Finally, the draggable attribute declares whether an element node can be natively grabbed and moved across the screen layout via system pointer device mechanics. The fourth category controls semantic visibility and structural interactivity freezing. The hidden attribute specifies that an element is completely irrelevant to the page's current view state, commanding the rendering engine to completely suppress its visual paint routine and permanently expunge it from the active system accessibility tree tracker. For more advanced state control, we implement the global Boolean control switch known as inert. When you flag a container with the inert attribute, the browser engine completely optimizes the state by neutralizing that element and its entire nested child node subtree from user interaction loops. It blocks all pointer-click events, purges the entire subtree from the keyboard navigation path, and completely blinds assistive screen readers to the node's existence, making it an indispensable compliance tool to freeze background content when top-layer dialog modals are active. The fifth category defines custom extensibility metadata using the datablank format. This standard allows us to attach custom, machine-readable parameter data strings directly to any native HTML element tag without breaking HTML validation compliance rules. The syntax rules dictate that the attribute must begin with the literal lowercase characters data followed by a lowercase string token identifier at least one character long, such as data node status or data refresh interval. This provides a safe, standard data storage envelope embedded straight within the markup tree, letting automation checkers and testing scripts cleanly extract custom structural flags without hijacking standard semantic layout attributes. Now, let us execute a complete, continuous spoken walkthrough of our production-grade global attribute profile blueprint, demonstrating our strict tag pairing initialization workflow from top to bottom so you can visualize the data architecture perfectly. We begin at line 1 of our document file by constructing our master system module card wrapper, initializing our tags together completely bare first. Write less than div greater than to open the element, and right next to it, write less than / div greater than to lock down the closing boundary completely bare. Now that the master framework is safely anchored in memory, step back inside that first opening division tag bracket to declare your extensive global properties. Add a space after the word div, set its unique identity token by typing id equals "node processor 8". Add a space and assign its style sheet selector hook by typing class equals "system module card". Add a space and configure its internationalization track by typing lang equals "n". Add a space and set its text orientation flow by typing dir equals "ltr". Add a space and append your first custom metadata flag by typing datanode status equals "active". And add a space followed by your second custom tracking metadata flag data refresh interval equals "45". Step inside the open, empty space between those closed master division tags, drop down a line, and construct your internal protected system heading node, pairing your tags together completely bare first. Write less than h3 greater than followed immediately by less than / h3 greater than to seal the boundary box completely bare. Step back inside that opening heading tag bracket, add a space after the characters h3, and lock down its text strings against translation degradation by typing translate equals "no". Now, step inside the inner text track of this sealed heading pair and type the technical identity content string, system_core_matrix. Directly below that header row, still inside the master wrapper container, we construct our interactive inline text editing zone, initializing our tags together completely bare first. Write less than p greater than and right next to it write less than / p greater than to lock down the paragraph boundary completely bare. Step back inside that opening paragraph tag bracket, add a space after the word p, and configure its input environment toggles. Type the attribute content editable equals "true". Add a space after those quotes, and turn off noisy grammar scanning lines by typing spellcheck equals "false". Finally, step inside the open text canvas area of this sealed paragraph container tag pair and type the display instruction text statement, update structural logs here. Reviewing your complete node hierarchy, you have initialized your master structural division container pair, your internal protected headings, and your interactive rich text paragraph rows completely bare and sealed in system memory before filling their properties or content data tracks. By masterfully orchestrating your universal web blocks using this hyperdisciplined approach, you establish an exceptionally clean, highly performant, and universally stable web architecture that parses flawlessly across all computing environments. Chapter 9. Advanced Document Metadata and Head Configuration. Section 9.1. Textual Metadata and Crawler Instructions. Welcome to Section 9.1, Textual Metadata and Crawler Instructions. In this lesson, we are performing a comprehensive architectural dive into the browser head element to master how our applications securely broadcast indexing summaries and operational rule sets directly to automated web search systems. Up to this point in our journey, we have focused extensively on building elements inside the active rendering viewport stage of the body tag. The body is the place where human eyes interact with typography, data grids, and interactive form fields. However, professional software engineering demands that we also master the non-visual operational metadata control block nested within the document head. When automated search engine crawlers, network indexers, or social media scrapers request your application over the network wire, they bypass visual display considerations entirely. Instead, they scan the technical metadata structures inside your document's head to categorize your site, assess its privacy levels, and index its content maps. If your head configurations are broken or missing, automated bots will struggle to parse your site, hurting search visibility and system discoverability. Let us highlight a vital structural rule mapping directly to the meta elements we are deploying today. As established in our special syntax module, the meta tag is a true, conforming void element. It possesses an internal content length of exactly 0 and is completely banned from holding text streams or nested child element blocks. The exact millisecond the parser scans a meta tag token, it registers the properties and closes the context in memory instantly. Attempting to force a closing slash or an independent closing meta tag token is a structural defect that will trigger parser recovery errors. Let us analyze our first major textual case, which isolates the description meta element. To construct this metadata profile textually, visualize opening a single bare meta tag bracket. Inside this tag boundary, we add a space and define its name identity token by typing name equals description . We add a space and declare its companion data payload property by typing content equals , and inside these quotes, we place our high-precision summary string text, master production-grade HTML core metadata architectures. Optimize application indexing tracking structures for modern automated crawling networks. We then close the single bracket completely. When an automated web spider decodes this node, it extracts the description text and caches it directly to serve as the structural descriptive text snippet underneath your application title on the search results screen. If you neglect to declare this attribute, the crawler will scrape random text fragments from your body layout, frequently displaying fragmented navigation menus or broken introductory text strings to your potential users. By explicitly declaring this void meta element within the 150 to 160 character limit, you prevent text truncation and maximize your user acquisition metrics. Let us analyze our second textual code implementation, which establishes absolute database indexing controls using the robots metadata tag. Visualize opening a standalone bare meta tag bracket box. Inside the bracket, add a space and type name equals robots . Add a space and configure its programmatic permissions by writing content equals noindex, nofollow, norchive , and close the single tag bracket cleanly. This command acts as an ironclad security guardrail for your private system layers. The noindex directive tells the web spider to block the document from entering public search indexes. The nofollow instruction tells the engine to completely freeze link traversal, preventing the crawler from passing authority or wandering down hyperlinks in the page tree. Finally, the norchive directive blocks the engine from saving a cached copy of the data in its public archives. By mastering these explicit metadata channels and maintaining total control over crawler parsing scripts, you establish an exceptionally secure, search-optimized, and professionally engineered web document architecture that scales flawlessly across the global web ecosystem. Section 9.2. Pragma Directives and Security Policy Mappings. Welcome to Section 9.2, Pragma Directives and Security Policy Mappings. In this lesson, we are discovering how to control the browser's networking behavior and establish advanced security boundaries right from our document head using the specialized HTTP equivalent meta tag configuration parameter. Up to this point in our architecture course, we have used meta tags exclusively to describe our content, passing descriptive text snippets to search engine bots and setting up indexing tracking parameters for automated crawlers. However, the HTML Living Standard includes a highly powerful operational mode that transforms our meta tags into active browser directives. By declaring the HTTP equiv attribute, which stands for HTTP equivalent, we create what is technically known as a pragma directive. When the browser's lexical parser scans an HTTP equivalent token, it intercepts the instruction and treats it as if it were a direct response header sent by the web server itself. This gives us the immense power to alter browser behavior, control data loading rules, and secure our application environments even when we have zero control over the underlying server infrastructure settings. Because the meta tag is a true, conforming void element, it possesses an internal content length of exactly 0 and can never hold nested child tags or raw text flows. The exact millisecond the parser reads its closing bracket, the node is sealed in memory instantly. Let us analyze our first major textual case, which isolates the refresh pragma directive to create an automated rerouting pipeline. To construct this directive textually, visualize opening a single bare meta tag bracket box. Inside the tag boundary, add a space and define its HTTP equivalence parameter by typing HTTP equiv equals refresh . Next, add a space and declare its configuration data payload by typing content equals 5 space URL equals https://cord infrastructure.systems/dashboard and close the single bracket cleanly. When the browser parses this node, it initializes an internal countdown timer. It waits exactly 5 seconds, drops its current execution thread, and instantly routes the user across the network to the new target URL address. While this client-side refresh hook is highly effective for simple state resets, you must maintain severe engineering caution. Automated redirects can disorient screen reader tools and trap users within infinite navigation loops, meaning you should deploy them judicially in production code. Let us analyze our second textual code implementation, which establishes an ironclad security defense line using the Content Security Policy Directive. Visualize opening a standalone bare meta tag bracket. Inside this tag boundary, add a space and initialize the security header directive by typing HTTP equiv equals content security policy . Next, add a space and map your strict resource restrictions by writing content equals default src space single quote self single quote semicolon space script src space single quote self single quote semicolon space style src space single quote self single quote semicolon double quote, and seal the single tag bracket block. The exact millisecond the browser engine reads this content security policy directive, it fundamentally rewrites its runtime compilation rule set for the remainder of the document file. The default source, script source, and style source tokens set to self command the engine to instantly block and reject any script file, style sheet, or asset that attempts to load from an external third-party domain. More importantly, this policy completely neutralizes the threat of cross-site scripting injections. By declaring this strict policy context, the browser automatically disables the execution of any inline scripting strings and bans dangerous legacy attributes like onClick completely. Even if an attacker successfully injects a malicious payload down the network line, the browser scans your head configuration, identifies the script as a policy violation, and kills the execution loop instantly before a single line of rogue data can run. By masterfully deploying these high-precision pragma directives and isolating your script perimeters using native browser security controls, you establish an exceptionally secure, high-performance, and professionally hardened web document architecture that stands completely bulletproof against data exploitation. Section 9.3. Social Graph Configurations. Welcome to Section 9.3, Social Graph Configurations. In this lesson, we are discovering how to transform our flat text hyperlinks into highly interactive, media-rich preview boxes that display beautifully across messaging platforms and social networks using the Open Graph protocol and Twitter card configurations. The exact microsecond a user shares your application link inside a communication platform, an automated metadata scraper immediately fetches your document head. If your head element is completely bare of social graph pointers, the platform will scrape arbitrary paragraphs or default graphics from your page layout, frequently displaying broken or unappealing link previews to potential users. By explicitly declaring structured social metadata, you take absolute control over how your application is represented, packaged, and visualized across the entire digital ecosystem. Following our strict, uncompromised engineering layout rules, we will reinforce this structural discipline by executing our mandatory workflow loop, utilizing our tag pairing technique. For standard containers, we always initialize our opening and closing tag boundaries together completely bare and closed first in system memory before we ever declare attributes or populate internal text tracks. However, let us review how the tag pairing technique applies flawlessly to the specialized metadata elements we are deploying today. As established in our special syntax module, the meta tag is an absolute, conforming void element. A void element possesses an internal content length of exactly 0 and is permanently banned from holding nested child nodes or inner text streams. Therefore, our engineering workflow adapts perfectly. The tag pairing technique for a void node means we initialize its single boundary bracket completely closed in memory first, and then step back inside that isolated perimeter to map its structural attributes cleanly. The exact millisecond the parser reads the closing angle bracket, the void node is instantly satisfied and sealed within the memory layout. Attempting to deploy an independent closing meta tag token is a structural defect that will trigger parser recovery errors down the line. Let us analyze our first major textual case, which utilizes the tag pairing technique to configure the core Open Graph metadata framework for shared links. To construct our preview title textually, visualize initializing a standalone bare meta tag bracket completely closed in system memory. Step back inside its single tag boundary, add a space, and declare its Open Graph identity token by typing property equals OG:title. Next, add a space and map its companion data payload by typing content equals production infrastructure framework and seamlessly verify the single boundary bracket is sealed. To supply the absolute media asset tracking link, initialize your second standalone bare meta tag bracket box closed first. Step inside its perimeter, add a space, and write property equals OG:image. Add a space and pass the absolute graphic address by typing content equals https://core.systems/assets/shared thumbnail.jpg and confirm the void boundary is closed. When the automated network scraper decodes these property tokens, it extracts the title string and maps the thumbnail image directly into its social graph layout cache, ensuring your preview paints flawlessly. Let us analyze our second textual code implementation, which establishes an optimized timeline visualization using the Twitter card directive framework. Visualize initializing a new standalone bare meta tag bracket completely closed first in system memory. Step back inside its single perimeter, add a space, and declare its platform identification token by typing name equals Twitter:card. Next, add a space and configure its structural layout presentation rules by writing content equals summary_large_image and ensure the single bracket is sealed. By executing this specific configuration path using our void tag layout workflow, the browser head commands the timeline platform to abandon its tiny default thumbnail layout rules entirely. Instead, the engine enforces a cinematic, full-width media presentation block directly above your title text across user feeds. By masterfully deploying these high-precision social graph attributes and managing your void tag boundaries with total architectural discipline, you deliver an exceptionally polished, optimized, and professionally hardened web document structure that communicates flawlessly across the global web network. Section 9.4. Relationship links and resource performance optimization. Welcome to Section 9.4, Relationship links and resource performance optimization. In this lesson, we are discovering how to control the browser's network scheduling engine right from our document head, using specialized resource hints and relationship markers to build exceptionally fast, production-grade web pages. The exact millisecond the browser downloads your HTML stream, it scrambles to locate the external files needed to assemble the page, things like style rule sets, website icons, and custom web typography. If your head element is completely bare of proactive optimization directives, the browser is forced to work reactively, discovering assets only when it happens to hit them down the body track. This delayed discovery slows page loading speeds, triggers erratic layout rendering blocks, and hurts your core web performance vitals. By explicitly declaring relational links, you establish direct communication lines with external servers ahead of time, optimizing the browser's processing queue before a single visual layout box is painted on the screen. Following our uncompromised engineering layout rules, we will reinforce this structural discipline by executing our mandatory tag pairing technique. As established in our special syntax module, the link tag is a true, conforming void element. A void element has an absolute content length of exactly 0, meaning it can never contain nested child nodes or inner plain text streams. Therefore, our workflow adapts perfectly. Our tag pairing technique for a void node means we initialize its single boundary bracket completely closed in system memory first. Once that isolated boundary box is anchored, we step back inside the perimeter to map its configuration tracking attributes with total precision. The moment the parser reads the final closing angle bracket, the void node is instantly sealed. Attempting to deploy a separate closing link tag down the line is a structural defect that will trigger parser recovery errors. Let us analyze our first major textual case, which utilizes the tag pairing technique to configure the authoritative canonical relationship link for search engines. To construct this node textually, visualize initializing a standalone bare link tag bracket completely closed in system memory. Step back inside its single tag boundary, add a space, and define its master relationship type by typing rel equals canonical . Next, add a space and map its absolute authoritative address target by typing ref equals https://core.systems/network-dashboard , and smoothly verify the single boundary bracket is closed. When an automated search spider reads this node, it logs that explicit web address as the single, definitive master source of truth for your page. Even if duplicate tracking links exist across the web, the engine consolidates all indexing metrics and authority values straight to this exact path, protecting your application from duplicate content penalties. Let us analyze our second textual implementation, which sets up an advanced resource prioritization pipeline using the high-priority preload framework. Visualize initializing a new standalone bare link tag bracket completely closed first in system memory. Step back inside its single perimeter, add a space, and command the browser to capture the resource immediately by typing rel equals preload . Next, add a space and define the absolute file location path by typing ref equals assets:/typography/main_font.woff2 . To ensure the network scheduler handles this asset with perfect technical alignment, add a space and declare its execution category by typing as equals :font , followed by a space and the cross-origin security parameter cross-origin, and confirm the single void bracket is sealed. By executing this configuration loop using our void tag workflow, the browser head commands the network queue to download that critical font file instantly during the primary HTML scan, preventing ugly text flickering visual bugs before the layout paints. By masterfully deploying these high-precision relationship attributes and managing your void tag boundaries with total architectural discipline, you deliver an exceptionally fast, optimized, and professionally hardened web document structure that loads flawlessly across the global network. Section 9.5. Script Placement Mechanics and Render Impact. Welcome to Section 9.5, Script Placement Mechanics and Render Impact. In this lesson, we are discovering how to master the browser's runtime execution threads right from our document head, exploring the critical differences between blocking operations and modern non-blocking scripting architectures. The exact microsecond a browser engine downloads your HTML stream, its lexical parser begins tokenizing characters to construct the live memory tree. However, the default behavior of a script tag acts as an absolute roadblock. The instant a standard external script is encountered, the parser drops everything, freezes DOM tree construction, and refuses to move forward until the file is fully downloaded and executed across the network. Placed carelessly inside the head element, this default behavior leaves your user staring at a completely frozen, blank viewport screen while the browser processes background code. By explicitly declaring modern script modifiers, you take absolute control over the compiler, commanding the engine exactly when to download, execute, and pause layout operations. To execute this, we type ~script greater than followed immediately by ~script greater than to lock down the boundary boxes completely bare. Now that the structural framework is safely anchored in system memory, we step back inside the opening tag bracket to deploy our configuration attributes cleanly. This disciplined habit guarantees our element trees remain perfectly balanced and well-formed. Let us analyze our first major textual case, which utilizes the tag pairing technique to configure a non-blocking application script using the defer framework. To construct this node textually, visualize initializing our opening and closing script tag boundaries together completely bare and sealed in system memory first. Now, step back inside that opening script tag bracket, add a space after the word script, and map its external source location by typing src equals ~assets /scripts/app_runtime.js . Next, add a space and assign the non-blocking execution modifier by typing the single, Boolean attribute keyword defer. By executing this configuration path using our tag pairing workflow, you command the browser to download the file asynchronously in a parallel background thread while the parser continues reading the HTML file smoothly. The defer modifier guarantees the script will wait patiently, executing only after the DOM tree is 100% complete, preventing runtime script crashes. Let us analyze our second textual implementation, which establishes a guarded layout initialization utilizing the modern render blocking directive. Visualize initializing a new script opening and closing tag container pair completely bare first in system memory. Step back inside the opening tag bracket, add a space, and set its file location path by typing src equals ~assets/scripts/themengine.js . To deliberately manage layout painting routines, add a space and declare the render blocking constraint by typing blocking equals ~render . And ensure your trailing closing script tag remains perfectly locked down. By deploying this specific configuration block, you command the browser to actively halt its layout paint loop. While the background parser continues reading markup nodes, the engine is strictly forbidden from painting pixels onto the canvas until this script executes. This eliminates ugly layout flickering or flashes of unstyled content, providing a premium user experience. By masterfully deploying these high-precision script attributes and managing your tag pairing boundaries with total architectural discipline, you deliver an exceptionally optimized, stable, and professionally hardened web document structure that executes flawlessly across the global web network. Section 9.6. Extended Metadata Properties. Welcome to Section 9.6, Extended Metadata Properties. In this lesson, we are discovering how to bridge the gap between our semantic documents, the browser's interface shell, and the client operating system using advanced metadata configurations to create deeply integrated application experiences. The exact microsecond a web page loads on a modern mobile device or a desktop engine, it lives within a complex hardware and software ecosystem. If your document head remains completely bare of extended properties, your application stays locked inside a generic browser sandbox frame. The browser window tint defaults to a jarring white, native scroll bars ignore system dark mode tokens, and the document canvas clips awkwardly around hardware notch cutouts. By explicitly declaring extended meta keys, you command the operating system directly, customizing the browser bar interface, expanding the layout boundaries edge to edge, and logging production credentials seamlessly inside system memory. Let us analyze our second textual implementation, which establishes an optimized progressive application shortcut label and author log. Visualize initializing a new standalone bare meta tag bracket completely closed first in system memory. Step back inside that single opening bracket space, add a space, and declare its short icon title profile by typing name equals double quote application name double quote. Next, add a space and assign the device home screen short label by typing content equals double quote course suite double quote, and ensure the tag is satisfied. Right below this line, initialize another standalone bare meta tag bracket completely closed first. Step back inside its opening bracket, add a space, and map your developer provenance tracking index by typing name equals double quote author double quote, followed by a space and your explicit credit payload content equals double quote shaghalf, double quote, and verify the closing bracket is sealed. By executing this precise configuration loop using our void tag workflow, you declare a pristine, secure, and production-ready metadata architecture that integrates perfectly across all modern mobile and desktop operating systems. Chapter 10. How HTML Works. Section 10.1. Welcome to Chapter 10, Section 1. The Rendering Pipeline Sequence and Speculative Optimization. When you look at a line of code on your screen, your brain reads it instantly as a structural element, a heading holding text, a button awaiting a click, or a link connecting documents. If you ask most developers what a browser does with this code, they will tell you that the browser reads the file and displays the page. But the browser engine does not see text, it does not see tags, and it certainly does not see a layout when it first begins its work. To the network stack, your elegant web application is nothing but an erratic, fragmented stream of incoming binary data, raw ones and zeros traveling through physical fiber optic cables or wireless frequencies. The process of turning those blind electrical pulses into a live, interactive, visually perfect user interface is one of the most complex and highly optimized engineering pipelines in modern software. To truly master web performance, we must trace this journey down to the microscopic level, observing the four distinct phases of the critical rendering pipeline, alongside the speculative background architectures that accelerate modern browsing. The journey begins at the network layer. When a user navigates to a URL, the browser dispatches an HTTP request, and the server responds by breaking the HTML document down into discrete packets, transmitted across the network via TCP sockets. Typically, the first wave of data arrives in a 14 kilobyte chunk, representing the initial network congestion window. At this entry point, the browser engine receives a raw memory buffer filled with raw bytes, also known as octets. For example, the less than character that begins every HTML tag looks like the single byte 0x3c in hexadecimal format. The lowercase letter h is represented by 0x68. The number 1 is 0x31, and the greater than symbol is 0x3e. The rendering engine cannot perform any structural operations with these isolated numbers. It must first execute phase 1 of the pipeline, which is conversion. During conversion, the engine reads the raw binary data blocks from the socket buffer and translates them into a linear array of individual, distinct characters based on a specified character encoding rule set. In almost all modern development, this rule set is UTF-8. The engine must determine this encoding accurately. It looks at the byte order mark at the very beginning of the file, or inspects the content type header sent by the server, or checks the early inline meta tags in the document. Once the character encoding is matched, the bits are decoded, and the browser outputs a continuous stream of characters, ready for the next structural analysis phase. However, if the browser parsed this character stream purely from start to finish on a single thread, the modern web would feel incredibly sluggish. Under normal circumstances, the primary HTML parser operates sequentially on the main thread. But the web is highly interactive and interconnected. The moment the main parser encounters a synchronous script tag, it must halt all document construction immediately. The parser must wait for the network to fetch that external JavaScript file, and then wait for the JavaScript engine to compile and execute it. This strict block is mandatory because the script has the power to run commands like document write, which can fundamentally alter the remaining, unparsed text stream. While the main thread sits frozen waiting for the network and execution layers, your internet connection would normally sit completely idle, stalling the retrieval of other essential page resources. To prevent this massive inefficiency, modern browser engines deploy a shadow optimization layer known as the preload scanner, or the speculative parser. While the main thread is completely blocked by a script or style sheet, the preload scanner activates on a background thread. It does not construct the document object model, and it does not spend energy calculating layout rules. Instead, it rapidly schemes ahead through the incoming character stream with a singular, high-speed mission to scan for high-priority external sub-resources, such as external scripts, style sheets, images, and web fonts. The moment it detects an src or ref attribute, it bypasses the main parser blocks and immediately dispatches speculative network requests in parallel. By the time the main thread finally finishes executing its synchronous code and resumes parsing, those heavy structural styles and images are already downloaded and sitting in the memory cache, drastically shortening the overall critical rendering path. With the background network requests firing, the main thread can execute phase 2 of the primary pipeline, which is tokenization, also known as lexical analysis. This is the stage where a flat string of characters is transformed into structured, distinct operational data. The engine runs a lexical analyzer, which is a complex state machine defined with extreme rigidity by the global standard specifications. The tokenization engine consumes characters one single unit at a time, shifting dynamically between hundreds of internal states. Let us look closely at how the state machine operates as it scans your code. By default, the parser rests in the data state. While in this state, it reads ordinary text characters and prepares to emit them as content. However, the absolute millisecond it consumes a less than symbol, the machine triggers an instant state transition, moving into the tag open state. If the very next character it reads is an ASCII alphabetical letter, the machine transitions once again into the tag name state. It will remain in this tag name state, continuously absorbing characters, until it encounters a space, a forward slash, or a greater than symbol. The moment it consumes that closing greater than symbol, it packages the accumulated text string and emits a distinct start tag token. If the machine instead encounters a forward slash immediately following a less than symbol, it switches into the end tag open state, which ultimately emits an end tag token. Through this continuous, character-by-character cadence, the state machine translates a flat text file into a chronological stream of clear, operational tokens, including start tags, end tags, character tokens, comment tokens, and document type tokens. Once these tokens are emitted, they flow directly into phase 3, which is tree construction. A flat sequence of tokens is highly structured, but it does not represent the nested, visual reality of a web page. Elements live inside other elements, forms contain inputs, and articles contain paragraphs. To map this structural hierarchy, the tree constructor relies on a crucial internal memory structure known as the stack of open elements. This stack continuously tracks the nesting depth and context of the document during the parsing phase. When the tree constructor receives a start tag token, it performs two distinct steps simultaneously. First, it instantiates a native C++ object in memory that represents that specific structural element. This object is called a node. Second, the constructor looks at the node currently sitting at the absolute top of the stack of open elements. It programmatically attaches our newly created node as a direct child of that top element, instantly creating a parent-child link inside the growing data graph. Once attached, the new node is pushed onto the top of the stack, becoming the current context. Every subsequent text character token or child tag token that arrives will be automatically appended to whatever node is currently sitting at the summit of the stack. The stack continues to grow vertically as the engine encounters deeper, nested structures in your layout markup. The moment the parser consumes an end tag token, it verifies the tag name against the top of the stack, and then pops that element off. The parsing focus immediately drops back down to the parent element below it. Through this continuous, highly disciplined push and pop stack cycle, the browser weaves individual nodes into a massive, multi-branch structural data graph, the document object model, or the DOM tree. This entire multi-phase orchestration happens in a matter of milliseconds, completely invisible to the end user. The DOM tree is not a passive configuration file or a temporary data dump. It is a live, structural data architecture resident in the browser engine's C++ memory space. It serves as the absolute single source of truth for every process that follows, including the matching of CSS selectors, the execution of the JavaScript runtime via engine wrappers, and the physical vector calculations of the layout and painting phases. Understanding this precise sequence from byte to tree is the foundation of advanced web engineering, enabling you to optimize the critical rendering path for flawless, high-speed execution. Section 10.2. The HTML parser, interlocking, and fault tolerance. Welcome to Section 10.2. The HTML parser, interlocking, and fault tolerance. In the previous section, we mapped out the clean, idealized sequence of the rendering pipeline. We looked at how a well-formed stream of bytes transforms elegantly into characters, tokens, and nodes. But the real-world web is rarely clean, and it is almost never idealized. The network layers are unpredictable, stylesheets and scripts constantly fight for access to the main thread, and decades of legacy markup have left the web filled with malformed, structurally broken source files. To survive in this environment, the browser HTML parser cannot operate like a rigid compiler. It must be a highly resilient, adaptive streaming engine built around absolute fault tolerance and strict execution interlocking. Let us first examine the engineering behind streaming parsing mechanics. When a software compiler processes a traditional file, like a C++ source file, it expects the entire file to be completely resident in memory before it begins execution. The browser HTML parser behaves entirely differently. It begins working on the very first chunk of data that drops into the network socket buffer. As raw network packets arrive, they are instantly converted into characters and passed directly into the tokenization state machine. This means the browser is actively building the document object model tree for the top half of a web page while the bottom half of the web page has not even been transmitted by the server. The tokenizer and the tree constructor operate continuously on these incomplete code fragments. If the parser runs out of characters because the network is running slow, it pauses, saves its state, and waits for the next chunk to stream in. The moment the next network packet arrives, the parser wakes up exactly where it left off, converting new bytes into tokens and grafting new nodes onto the existing tree. This incremental architecture dramatically cuts down the time to first paint, but it also introduces volatile timing variables that the browser must constantly manage. The most dangerous of these variables is the deep architectural entanglement between HTML parsing, JavaScript execution, and CSS rendering. This brings us to the style script interlock. As we established, when the HTML parser encounters a synchronous script tag, it must halt document parsing immediately. It relinquishes the main thread so the JavaScript engine can download and execute that script. But the interlock goes much deeper than that. Imagine a scenario where your HTML document contains an external stylesheet link tag, followed immediately by a synchronous script tag. The script asset finishes downloading over the network faster than the stylesheet. You might think the browser should run the script immediately to save time. However, the browser engine will refuse to run that script. It will freeze the script execution and keep the HTML parser completely blocked until the stylesheet has finished downloading and the entire CSS object model tree, or CSSOM, is fully constructed. Why does this interlock occur? The browser engine must prevent an operational race condition. JavaScript has full programmatic access to the page layout and styles through APIs such as getComputedStyle or bounding client rect. If the browser allowed the JavaScript engine to run a script before the stylesheet was fully parsed, the script would query the styling properties of an element and receive outdated or non-existent data, leading to catastrophic application failures. To prevent this, the engine enforces a strict dependency chain. The HTML parser is blocked by the script, but the script is blocked by the pending stylesheet. The main thread sits in a state of controlled suspension until the CSSOM locks into place, ensuring that the runtime environment remains completely predictable for the script, even if it delays the parsing of the remaining HTML document. Beyond these structural timing blocks, the HTML parser must also contend with broken author code. This is where the concept of deterministic error recovery and engine resilience becomes critical. If you feed malformed or invalid code into an XML parser, the rules dictate that the engine must fail instantly, throw a hard parsing error, and crash the interface. The web, however, was built on the principle of maximum leniency. If early web browsers had crashed every time a developer forgot a closing tag, the web would have failed to gain widespread adoption. When the modern HTML5 parsing specification was written, the engineers did not try to ban bad code. Instead, they spent years documenting every common mistake developers make and created mathematical, deterministic error recovery algorithms directly inside the tree construction rules. This means that no matter how malformed an HTML document is, every single compliant browser engine in the world will reconstruct the exact same DOM tree graph from it. Let us break down exactly how the engine resolves these errors on a microscopic level using concrete architectural examples. The first common scenario involves unclosed or overlapping inline formatting elements, such as a bold tag followed by an italic tag, where the developer closes the bold tag before closing the italic tag. To handle this without mangling the document structure, the tree constructor maintains a secondary internal data structure alongside the stack of open elements, called the list of active formatting elements. When the parser encounters overlapping tags, it invokes a highly sophisticated routine known as the adoption agency algorithm. Instead of creating a broken, deeply nested mess, the algorithm intercepts the tokens, unwinds the stack of open elements to isolate the misaligned formatting tags, clones the necessary formatting nodes, and reparents the text elements safely underneath them. The layout remains visually correct, and the DOM tree retains a valid, legal hierarchy. A second extreme example of error recovery is the phenomenon known as foster parenting. This occurs when a developer writes loose content, like plain text or a stray div tag, directly inside a structural table element but completely outside of a valid table cell or table row tag. A rigid parser would place that node inside the table data tree, which violates the core layout specifications of the browser engine. To resolve this, the tree constructor triggers a structural correction. It actively searches backward through the stack of open elements until it finds the exact location where the table element is being constructed. It then takes the illegal, stray node and hoists it completely outside of the table structure, placing it immediately before the table in the parent DOM tree. This process of foster parenting ensures that the visual table layout remains pristine, while the illegal text content is still safely preserved and rendered on the screen rather than being discarded. This absolute engine resilience is driven by the supreme directive of web architecture: never break the web. The web is a historical archive spanning decades. Monolithic enterprise systems, legacy academic portals, and old personal blogs built in the early 90s must continue to function perfectly on modern browsers. By embedding these complex error recovery systems directly into the streaming parser runtime, browser engines ensure flawless backward stability. They absorb broken inputs, execute real-time structural healing, and continuously deliver a functional, interactive user interface from bytes to pixels, regardless of how chaotic the underlying source strings truly are. Section 10.3. The Live Tree Architecture. Welcome to Chapter 10, Section 3. The Live Tree Architecture. Once the tree constructor completes its work, the raw network bytes and flat tokens are completely gone. In their place lies a complex, highly dynamic data structure known as the Document Object Model, or the DOM tree. Developers frequently interact with the DOM using JavaScript, but few understand its true architectural reality inside the browser engine. The DOM is not a text document, and it is not a native JavaScript object. It is a live, highly structured graph of interconnected C++ objects memory managed by the browser engine. To build high-performance applications and debug complex layout bugs, we must understand how this architecture maps different node types, how it treats invisible source code spaces, and why what you see in your code editor is fundamentally different from what lives in the engine memory. Let us first analyze the structural object types that make up this live hierarchy. At the base of the entire architecture is a generic master class, known simply as the node. Every single object within the DOM tree inherits from this base node class. The browser engine uses specialized subclasses to handle different types of content, and each type has a radically different footprint and behavior in system memory. The most prominent of these are element nodes. An element node represents an actual HTML tag, such as a div, a section, or an input. Element nodes are heavy objects because they must store structural metadata, including tag names, namespaces, pointer lists to parent and child nodes, and dictionaries of local attributes like classes, identifiers, and custom data attributes. However, an element node does not actually hold text content directly within itself. If you write a paragraph tag with a sentence inside it, the sentence does not live as a text property inside the paragraph element node. Instead, the character payload is spun off into an entirely separate object type called a text node. A text node is a lean, specialized node whose sole purpose is to manage a raw character string in memory and link it to a parent element. Alongside element and text nodes are non-rendering object types, most notably comment nodes. When you write a comment inside your source HTML, it is completely hidden from the visual viewport. Yet, on an architectural level, the browser engine does not discard it. The parser processes the comment tokens, instantiates a native comment node object, allocates real memory for its string content, and grafts it directly into the live DOM graph. It remains fully accessible via script interfaces, occupying a physical slot in the tree structure until the document is destroyed. This strict categorization of characters brings us to one of the most misunderstood aspects of browser architecture, the whitespace generation rules. When developers write HTML, they naturally use line breaks, carriage returns, tabs, and spaces to indent their code and make it readable. To a human, this whitespace is just empty layout structure. To the HTML tokenizer state machine, however, characters like the space, which is hexadecimal 0x20, the tab, which is 0x09, and the line feed, which is 0x0a, are fully valid character inputs. Unless the parser is operating inside specialized structural zones like a table element, the tree constructor obeys a rigid rule. Any sequence of whitespace characters located between two element tags must instantiate a literal text node in memory. Consider a simple list structure where you hit enter and indent each item tag on a new line. The browser engine inserts a literal whitespace text node containing a line break and several spaces between every single list item. This is not just an academic nuance, it has profound implications for visual layout flow. If you arrange elements using an inline or inline block formatting context, the browser engine treats these invisible whitespace text nodes as literal layout content. It renders them as small physical gaps on the screen, usually resulting in the infamous 4-pixel separation between inline blocks that leaves developers desperately shrinking margins or eliminating code indentation. The memory architecture prioritizes the literal character stream over developer intent, forcing the engine to allocate thousands of tiny text nodes just to hold the empty spaces between your tags. This disparity between written text and memory structures highlights the necessity of advanced document inspection. There is a fundamental architectural divide between your uncompiled source file characters and the active DOM data model running inside the browser engine. When you open the browser developer panels and look at the Elements tab, you are not looking at your HTML file. You are looking at a real-time, high-level visual serialization of the engine's active C++ memory graph. The raw source text file is entirely static and dead the moment it finishes downloading. The DOM tree, conversely, is fluid and highly reactive. As soon as the page initializes, the live DOM tree begins to diverge from the original source text. Third-party browser extensions inject new elements, JavaScript frameworks dynamically append or destroy nodes, and runtime state changes continuously alter element attributes. Furthermore, as we explored in our discussion of fault tolerance, the live DOM tree includes all the structural healing modifications forced by the browser's error recovery algorithms. If your source file had omitted a body tag, or left a table cell floating in the open, the source code remains permanently broken, but the developer panel will show a perfectly organized, structurally corrected node layout. By comparing the raw characters inside the View Source panel against the live, dynamic graph inside the Elements panel, you can instantly observe the engine's architectural changes in real time. You see the exact nodes currently consuming system memory, the precise parent-child pointer relationships driving the layout engine, and the true structural layout of the application as it shifts and responds to user interaction. Master this architectural view, and you master the exact runtime model that controls the modern web interface. Section 10.4. Character Encodings. Welcome to Chapter 10, Section 4. Character Encodings and the 1024-byte buffer rule. Every computational step we have discussed so far, from tokenization to the construction of C++ node graphs, depends entirely on a singular, massive assumption that the browser engine knows exactly what language your bytes are speaking. If the engine misinterprets the binary stream, the entire pipeline collapses. A sequence of bytes representing an accent mark or an international character can easily corrupt downstream tokenization, turning valid elements into malformed text strings. To prevent this, browser engines execute a rigorous, highly prioritized evaluation path to determine the document's character encoding, governed by a strict architectural constraint known as the 1024-byte buffer rule. Let us trace the precise hierarchy of the codec evaluation paths. When the network stack delivers the initial stream of data to the rendering engine, the engine cannot afford to guess blindly if it can avoid it. It inspects the binary data through 3 distinct layers of authority. The absolute highest authority in the entire pipeline is the byte order mark, or BOM. The byte order mark is a specific, unique sequence of bytes inserted at the very beginning of a text file by text editors to signify the encoding format. For example, in a UTF-8 encoded document, the byte order mark manifests as the 3-byte sequence 0xEF, 0xBB, 0xBF. If the browser engine detects these exact bytes at the 0 index of the incoming stream, the debate is instantly over. The byte order mark overrides all other configurations, headers, and declarations. The engine firmly commits to the specified encoding and immediately passes the subsequent bytes into the conversion phase. If the byte order mark is absent, the browser drops down to the second level of authority, the network transport layer. The engine reads the HTTP transport headers sent by the web server, specifically looking for the content type header. A correctly configured server will transmit a header stating content type, text/HTML, ;, charset equals UTF-8. The network parser extracts this charset value before the primary HTML parser even wakes up. If present, this transport instruction dictates the rules of character conversion. However, a massive percentage of the web relies on misconfigured or completely generic web servers that omit the charset parameter entirely, delivering a raw content type header of text/HTML. When this occurs, the browser engine is forced to fall back to the third and lowest level of authority, the inline meta charset tag embedded directly within the HTML document text itself, typically written as meta charset equals UTF-8. This creates a fascinating engineering paradox. The browser engine must parse the HTML document to find the meta charset tag. But it cannot safely parse the HTML document until it knows the character encoding. To resolve this catch-22, the browser engine enters a highly volatile state known as speculative parsing under a presumptive codec. Lacking a definite encoding instruction from a byte order mark or an HTTP header, the engine chooses a default, localized presumption, usually Windows 1252 or ISO 8859-1, depending on the user's geographic locale. It then starts converting bytes, emitting tokens, and building a speculative DOM tree, all while constantly watching the token stream for the arrival of the inline meta charset tag. This brings us to the core performance vulnerability, the 1024-byte performance block and its rigid boundary rules. Browser architects recognize that parsing a document under a false presumption is incredibly dangerous. Therefore, the HTML specification enforces a strict spatial boundary. The engine will only search for an inline character encoding declaration within the first 1024 bytes of the document stream. Let us look at exactly what happens inside the engine architecture when this boundary is tested. If the engine discovers the inline meta charset tag within the first 1024 bytes, it pauses and compares the declared encoding against its speculative presumption. If the declared encoding matches the presumption, the engine breathes a sigh of relief and continues parsing smoothly without interruption. However, if the declared encoding differs, say the engine presumed Windows 1252 but the meta tag declares UTF-8, the engine cannot simply change its settings midstream. Doing so would mean the first portion of the document was parsed under one set of rules, and the rest under another, fracturing the integrity of the data. To correct this mismatch, the browser engine executes a catastrophic operation known as a speculative restart or a layout drop and restart processing cycle. The engine instantly halts parsing. It completely flushes the tokenization state machine, purges and destroys the speculatively constructed DOM tree nodes from memory, resets the network stream pointer back to byte 0, alters its core conversion codec to UTF-8, and restarts the entire rendering pipeline from scratch. If this restart happens instantly within the first few hundred bytes, the performance penalty is minimal. But if the developer has filled the top of the document with massive inline scripts, massive comment blocks, or heavy embedded data strings, pushing the meta charset tag down to byte 1025 or deeper, the engine reaches a terminal threshold. Past 1024 bytes, the browser engine completely stops looking for encoding changes. It locks in its initial, blind presumption permanently. When a late declared or completely omitted charset forces the engine to parse a UTF-8 document using a legacy codec like Windows 1252, the visual result is the infamous phenomenon known as mojibake. Mojibake occurs when the multi-byte character sequences of a modern encoding are broken apart and forced through a single byte legacy decoder. For example, a beautifully typeset apostrophe, an international character, or a standard emoji that requires 3 or 4 bytes in UTF-8 is suddenly interpreted as 3 or 4 isolated, individual characters under the legacy rules. Elegant text transforms instantly into a chaotic, unreadable mess of accented vowels, random currency symbols, and broken question marks. Furthermore, because the structural tokens themselves might contain these complex characters, the state machine can misidentify tag names or attribute boundaries, causing massive layout drops where entire sections of the web page fail to render, or collapse entirely into broken text nodes. The engineering takeaway is absolute: To guarantee maximum pipeline efficiency, eliminate speculative restarts, and prevent the destructive visual failures of Mojibake, the character encoding must be declared as close to byte 0 as possible. It should ideally be managed at the network layer via HTTP headers, or placed as the absolute first child element inside the document head, safely within the 1024-byte safety zone, ensuring the rendering engine can lock down its structural foundations before a single node is ever generated. Section 10.5. User Agent Stylesheets and Element Defaults. Welcome to Chapter 10, Section 5. User Agent Stylesheets and Element Defaults. When the browser engine finishes building the document object model tree, every single node represents a structural component of your content, but none of those nodes possess physical dimensions, colors, or visual layouts yet. If you do not link a custom external stylesheet to your document, the web page does not render as a chaotic, overlapping pile of unformatted text. Instead, headings appear large and bold, paragraphs are separated by clean vertical spaces, lists display structured bullet points, and links are colored blue with an underline. This structured presentation happens because the browser engine never begins rendering on a blank canvas. Before a single line of developer code is ever parsed, the engine injects its own native rule set, known as the user agent stylesheet. Let us conduct a structural analysis of this internal user agent stylesheet and see how it operates before author styles load. The user agent stylesheet is not an external network asset. It is a highly specialized, hard-coded configuration file written by the browser engineers and compiled directly into the binary architecture of the browser engine itself. For instance, in Chromium's Blink rendering engine, this rule set lives natively as a core source file named html.css. In Apple's WebKit engine, it is designated as modernua.css. The primary architectural purpose of the user agent stylesheet is to translate pure document semantics into legible visual baselines. HTML is designed strictly to describe what data is, not what data looks like. A paragraph tag states that a text block is a paragraph, but it says nothing about margins or fonts. The user agent stylesheet steps into this void, mapping default visual properties to every valid HTML element tag. When the browser engine enters the style resolution phase, also known as style recalculation, it uses the CSS cascade mechanism to determine the final visual state of every node. The user agent stylesheet forms the absolute lowest layer of this cascade hierarchy. The order of priority moves from the user agent rules at the bottom, up to user accessibility configurations, and finally to author stylesheets, which are the custom styles written by you, the web developer. Because the user agent rules sit at the bottom, any standard style rule you write in your custom CSS will automatically override the browser defaults due to the laws of cascade specificity. However, if a user agent rule uses the exclamation important declaration, it creates a highly rigid constraint that is difficult for basic author styles to overwrite without explicit adjustments. Understanding this foundational layer is critical because many common web layout bugs are caused by developers forgetting that the user agent stylesheet is actively running in the background, injecting unexpected margins, paddings, and font weights into elements that were assumed to be completely unstyled. This brings us to the core architectural divide governed by the user agent defaults, global element layout properties, and the separation between block-level box generation and inline element character groupings. When the style engine processes a DOM node, it reads the element's display property from the resolved stylesheet rules. The value of this display property tells the layout engine exactly what type of physical geometric container, or layout box, it must generate for the visual render tree. The user agent stylesheet establishes two primary default layout behaviors that dictate how the entire web moves and flows: block-level box generation and inline formatting context participation. Let us first examine block-level elements, which the user agent stylesheet explicitly assigns as display block. This category includes structural tags such as divs, paragraphs, headers, sections, and list items. When the layout engine instantiates a block box, it enforces rigid geometric rules. A block-level box automatically creates a new block formatting context, or participates within one. By default, a block box stretches horizontally to occupy 100% of the available width of its parent container, behaving like a liquid filling the entire horizontal width of a pipe. It completely rejects sharing horizontal space with any neighboring elements. Even if a block box contains only a single short word, it forces a mandatory layout line break before it opens and a line break immediately after it closes. Subsequent elements are pushed directly downward, stacking vertically like bricks in a wall. Furthermore, the user agent stylesheet applies default top and bottom margins to elements like paragraphs and headers, measured in em units relative to the font size. This activates the layout engine's margin collapsing algorithms, where adjacent vertical margins blend together into a single space, preventing double spacing between paragraphs. The second major category consists of inline elements, which the user agent stylesheet designates as display inline. This group includes textual tags like spans, anchors, strong emphasis tags, and line breaks. The layout engine treats inline elements with an entirely different mathematical logic. Inline elements do not generate independent, structural block boxes. Instead, they participate inside an inline formatting context, breaking apart into character groupings that flow horizontally within a shared, horizontal structure called a line box. Inline elements sit side by side on the same line, wrapping smoothly to the next line only when they collide with the horizontal boundary of the parent block container. The architectural constraints placed on pure inline boxes are absolute. The layout engine completely ignores any explicit width or height properties applied to them. You cannot change the vertical dimensions of a pure inline span by writing height 50 pixels. The engine will bypass the instruction entirely. The physical height of an inline box is dictated strictly by its internal text font metrics and its line height properties. While horizontal padding and horizontal margins will physically. Section 10.6. The Dual Viewport Specification. Welcome to Chapter 10, Section 6. The Dual Viewport Specification. When the web was young, the relationship between your layout and the physical screen was incredibly straightforward. A user sat in front of a desktop monitor, opened a browser window, and the dimensions of that browser window determined the exact space available for rendering. If the window was 1000 pixels wide, the CSS engine calculated layouts based on a width of 1000 pixels. But the sudden explosion of mobile smartphones shattered this simple architecture completely. If mobile browser engines had mapped layouts directly to the tiny physical screens of early mobile devices, which were often only 320 pixels wide, the desktop-oriented web of the early 2000s would have fractured instantly. Columns would have compressed into unreadable vertical strips, layouts would have completely broken, and navigation would have become impossible. To solve this problem without forcing the entire world to rewrite every website overnight, browser engineers had to re-engineer how the engine understands space. They invented the dual viewport specification, separating physical site from virtual layout geometry. To master mobile responsive web design, you must understand the interaction between these two distinct viewports, the layout viewport and the visual viewport. The layout viewport is the virtual canvas space where the browser engine calculates all your CSS geometries, percentages, and media queries. When you write a rule stating that a main element has a width of 100%, or when you set a media query to trigger at a maximum width of 768 pixels, the engine evaluates those numbers strictly against the dimensions of this layout viewport. It is the architectural sandbox that the CSS layout engine thinks it lives in. The visual viewport, conversely, is the literal tracking scope of the physical screen. It represents the exact portion of the web page that the user can currently see on their device monitor at any given millisecond. Under normal desktop conditions, the layout viewport and the visual viewport are identical in size, locking together perfectly. But on mobile devices, they act as completely independent tracking layers. Think of the layout viewport as a massive static canvas, and the visual viewport as a fluid glass window floating above it. If a user utilizes a pinch to zoom gesture to magnify a specific paragraph on their phone, the visual viewport contracts, covering a much smaller physical area of the page. However, the layout viewport remains completely unchanged. The elements do not execute a reflow, paragraphs do not wrap differently, and columns do not shift positions. The engine simply magnifies the pre-calculated visual bitmap within the visual viewport, decoupling sight from structural layout computation. This separation of space explains the historical mechanics behind mobile legacy adaptations. When early smartphones were introduced, their physical screens were too narrow for standard desktop web designs. To prevent catastrophic rendering failures, mobile software engineers hard-coded a default layout viewport width directly into the browser engines, set universally to 980 pixels. When you loaded a standard desktop site on an early mobile browser, the engine did not use the phone's true screen width. Instead, it fooled the layout engine into believing it was running on a desktop monitor that was exactly 980 pixels wide. The parser built the document object model, the style engine constructed the layout boxes, and the page rendered completely smoothly at a width of 980 pixels. Once this massive virtual layout was finalized in memory, the engine took the entire resulting bitmap and scaled it down uniformly, like shrinking a large photograph, until it fit perfectly within the narrow boundaries of the small physical screen. This legacy trick is exactly why old desktop websites look like tiny, microscopically small versions of themselves when opened on a phone, requiring the user to immediately double-tap and zoom in just to read a single line of text. While this 980-pixel adaptation preserved backward web stability, it made modern, fluid mobile layouts impossible to execute cleanly. To bypass this legacy shrinking behavior and achieve modern viewport normalization, web developers must explicitly instruct the browser engine to disable its default mobile assumptions. We do this by utilizing the viewport meta settings, injecting a highly specific instruction tag directly into the document head metadata. When you write the standard declaration, meta name equals viewport, content equals width equals device width, initial scale equals 1.0, you are fundamentally altering the engine's layout geometry calculations. Let us break down exactly what this configuration forces the rendering engine to do. The instruction width equals device width tells the engine to completely discard the default 980 pixel legacy canvas limit. Instead, it forces the virtual layout viewport width to match the exact independent pixel width of the physical hardware device. If the web page is loaded on a phone with an independent pixel width of 390 pixels, the layout viewport becomes exactly 390 pixels wide. The secondary instruction, initial scale equals 1.0, establishes a strict, unyielding 1-to-1 pixel mapping ratio between standard CSS layout pixels and the device-independent screen pixels. It completely deactivates the engine's automatic visual scaling and shrinking routines. By normalizing these viewports, you unlock the true power of responsive web design. Media queries now fire accurately based on the true dimensions of the device, layout percentages translate perfectly to the actual screen space, and text scales naturally to a highly legible, comfortable reading size. You effectively eliminate the separation between the virtual canvas and physical screen, forcing the layout engine and the visual frame to work in absolute harmony from the very first token to the final rendered pixel. Section 10.7. HTML Content Categories and Nesting Restrictions. Welcome to Chapter 10, Section 7. HTML Content Categories and Nesting Restrictions. When most developers think about how elements relate to one another, they rely on the old, traditional binary division of the web, block versus inline. They assume that if an element stacks vertically, it can hold anything, and if it flows horizontally, it can only hold text. But when the modern HTML5 specification was architected, browser engineers realized this binary approach was far too simplistic to handle the semantic and interactive complexity of modern applications. They completely deprecated the strict block and inline model for content validation and replaced it with a sophisticated framework of 8 overlapping content categories. During the tree construction phase, the browser engine acts as a strict compliance officer, evaluating every single node against these categories to determine whether your nesting structures are legally valid or fundamentally broken. Let us break down the core categories that govern the structural DNA of the modern web. The first is metadata content. These are the elements that set up the structural configuration, behavior, or styling layers of the document without directly appearing in the primary visual layout. This category includes tags like meta, link, script, style, and title. They typically cluster inside the document head, acting as the operational setup for the rendering engine. The second, and largest, category is flow content. Flow content represents the massive master group of the layout. Almost every single element that renders inside the body of a web page belongs to this category. Divs, paragraphs, headings, articles, sections, spans, buttons, and raw text nodes are all classified as flow content. It is the baseline currency of the document structure. Within flow content, the engine isolates specialized subsets, starting with sectioning content. Sectioning content consists of elements that define explicit semantic scopes and structural boundaries within the document outline. This group is strictly limited to 4 key elements: article, aside, NAV, and section. When the engine encounters these nodes, it uses them to construct the internal semantic outline of the page, which is heavily utilized by assistive technologies and search engines to understand the hierarchy of the information. Next is heading content. Heading content is dedicated purely to structural titles, including all headers from H1 through H6, as well as the group element. The engine mandates that heading content must live within flow or sectioning zones to mark the entry points of your content blocks. Below headings lives phrasing content. Phrasing content represents the actual textual fabric of the document, alongside the specialized inline markup elements that modify or wrap that text. This includes elements like span, strong, emphasis, code, and image tags, as well as raw text nodes. Phrasing content is a strict subset of flow content, but its nesting rules are significantly more restrictive. A zone that accepts phrasing content will strictly reject heavier block-level flow elements like sections or articles. We also have embedded content. Embedded content includes elements that import external data payloads or instantiate isolated, sandboxed rendering contexts inside your page. This category includes image tags, iframes, video players, audio elements, canvas graphs, and inline scalable vector graphics. When the engine processes embedded content, it often spins up secondary internal layout subroutines to manage the foreign media coordinates. The final primary group is interactive content. Interactive content consists of elements specifically engineered for direct user interface engagement. This includes anchor tags, buttons, inputs, select menus, labels, and text areas. The engine treats interactive content with extreme caution because these elements dictate how the browser tracks focus, manages keyboard tab indexing, and dispatches user click events. Beyond these core groups, the specification defines 2 specialized architectural behaviors that alter standard parsing rules. The first is palpable content. Palpable content refers to any element that renders a tangible, physical presence on the screen. To be considered palpable, an element must not be hidden and must contain at least one rendering node, such as text or an image. If an element is completely empty, many optimization algorithms or accessibility systems will treat it as a ghost box and bypass it entirely. The second specialized architecture is the transparent content model, which represents a fascinating dynamic shift in tree construction. A transparent element is an element whose nesting rules are not fixed. Instead, it derives its legal nesting permissions directly from whatever parent element it happens to be placed inside. The most famous example of a transparent element is the anchor tag. If you place an anchor tag inside a paragraph, the anchor tag inherits a phrasing content model. It can only legally contain other text nodes, spans, or strong tags. If you try to drop a massive structural section or a heading inside that anchor, you violate the local phrasing rules. However, if you take that exact same anchor tag and place it inside a generic div, the anchor inherits a flow content model. Suddenly, it becomes completely legal for that single anchor tag to wrap around multiple headers, paragraphs, lists, and structural boxes. The tree constructor evaluates transparency dynamically in real time, checking the stack of open elements to see what context sits immediately above the transparent node before validating the incoming tokens. This dynamic validation brings us to the rigid landscape of common nesting restrictions. Browser engines embed strict, hard-coded negative constraints that completely prohibit specific containment structures, regardless of your CSS layout settings. Two classic interactive boundaries illustrate this perfectly. You can never nest an anchor tag inside another anchor tag, and you can never nest a button element inside another button element. To understand why the engine blocks these structures, we must look at how the browser manages interactive geometry and event propagation. Imagine if the engine allowed an anchor tag to live inside another anchor tag, and a user clicked on the overlapping text space. When the user interacts with the screen, the browser performs an operation called hit testing. It casts a geometric vector through the rendered layers to see exactly which C++ node matches the screen coordinates. If two interactive anchor nodes overlap perfectly, the engine's event bubbling system enters an ambiguous, conflicting state. Which URL should it navigate to? Which focus ring should it activate? How should it map the node to the internal accessibility tree? To prevent this catastrophic interactive confusion, the HTML parser enforces strict structural healing rules the moment it encounters these illegal combinations. If the tokenizer is processing an open anchor tag and suddenly strikes a second start tag token for another anchor, it refuses to nest them. Instead, the tree constructor triggers an immediate emergency correction. It forcefully closes the first anchor tag right then and there, popping it off the stack of open elements, and then opens the second anchor tag as a separate, sequential sibling node. The same structural ejection occurs if you attempt to place a button inside a button. The parser will split your layout apart to keep the interactive nodes separated in memory. If you are unaware of this architectural defense mechanism, your visual layout will shatter completely on the screen, as the browser actively breaks your nested CSS container chains apart to preserve the legal integrity of the document object model. By deeply understanding these content categories and constraints, you can author clean, compliant structures that work perfectly alongside the engine's internal validation rules, preventing invisible layout failures and building incredibly stable web architectures. Section 10.8. DOM Interfaces and the C++ Binding Layer. Welcome to Chapter 10, Section 8. DOM Interfaces and the C++ Binding Layer. When you open your code editor and write a line of JavaScript to change the text content of a paragraph or read the value of an input field, it feels like you are interacting directly with standard, native JavaScript objects. If you log a DOM element to the console, it prints out like an ordinary object with properties and methods you can manipulate at will. But this seamless experience is a highly engineered illusion. The JavaScript engine running inside the browser, such as Google's V8 or Mozilla's SpiderMonkey, does not actually contain or own the document object model. The DOM tree lives entirely across an architectural boundary, residing inside the browser's native rendering engine, which is written in C++, such as Chromium's Blink or Apple's WebKit. To write highly optimized, institutional-grade web applications, we must unmask this boundary, exploring the C++ binding layer, the deep interface inheritance hierarchies, and the memory mechanics of DOM collections. Let us first peer directly into the JS to Engine bridge to understand how these two completely different software environments communicate. The memory space of the JavaScript runtime is completely isolated from the memory space of the C++ layout engine. When the HTML parser instantiates a node, it creates a native C++ object on the heap. To allow JavaScript to control this node, the browser engine generates a highly specialized intermediary object inside the JavaScript runtime, known as a V8 wrapper or a DOM binding wrapper. When you query an element using JavaScript, the engine does not hand you the real C++ node. Instead, it hands you this lightweight JavaScript wrapper object. The wrapper itself holds almost no data. It contains nothing but an internal, low-level pointer that cuts across the environment boundary, linking directly to the real C++ object on the engine side. Every single property access or method call you execute in JavaScript, whether it is reading a class name or calling a pen child, must physically cross the C++ binding bridge. The wrapper intercepts your JavaScript call, marshals the arguments, translates the data types from JavaScript primitives to native C++ types, and passes execution across the boundary line. Once the C++ engine fulfills the request, the result travels back across the bridge, wrapping native data back into JavaScript objects. Crossing this bridge is not computationally free. It introduces an invisible, systemic processing overhead. If your code crosses this bridge thousands of times inside a tight animation loop, the constant context switching and data translation will quickly saturate the main thread, leading to severe frame drops and lag, even if your JavaScript logic itself is mathematically perfect. To maximize efficiency across this bridge, the browser engine organizes its C++ nodes using a highly structured, strict interface inheritance hierarchy. Every single object residing within the DOM tree sits on a precise rung of a long blueprint chain. Let us trace this inheritance chain from the absolute base layer down to the most specialized elements, analyzing exactly what architectural capabilities are injected at each evolutionary step. At the absolute foundation of the entire architecture sits the master interface known as Event Target. Event Target is the primal root of the DOM blueprint. It holds absolutely no concepts of text, tags, visuals, or styling. Its singular, vital purpose is to inject event routing infrastructure into memory. It provides the low-level C++ mechanisms for three core methods: add event listener, remove event listener, and dispatch event. Because every node inherits from Event Target, every component of your web page gains the native capacity to listen to, propagate, and respond to user and system events. Moving down the chain, the next major interface layer is Node. The Node interface takes the abstract event infrastructure of Event Target and adds the physical concepts of structural placement and tree topology. Node defines the memory slots required to track parent, child, and sibling relationships within a graph. It injects properties such as child nodes, parent node, next sibling, and previous sibling, alongside foundational element manipulation methods like append child, remove child, and replace child. It is at this node layer that the engine differentiates between structural elements, text blocks, and comment objects. Descending further, we encounter the element interface. The element interface narrows the scope specifically to tags, leaving plain text and comments behind. Element introduces the conceptual framework of attributes and tag identities. It provides the data structures needed to store localized identifiers, class lists, and custom attributes via methods like getAttribute and setAttribute. Furthermore, the element layer marks the exact point where visual geometry enters the pipeline. It maps the node directly to the layout engine, exposing real-time dimensional attributes such as client width, scroll height, and the vital bounding coordinate method, getBoundingClientRect. Below the element layer sits the HTML element interface. HTML element introduces the explicit context of the web platform and the HTML specification itself. It decorates the node with global HTML characteristics that apply to all web tags universally. This includes managing keyboard focus rings via tab index, content hidden states, explicit element directionality, the local inline style map object, and the dataset property used to read custom data attributes. Finally, the chain terminates at highly specialized leaf interfaces, known as the concrete HTML tag implementations, such as HTML input element or HTML template element. Each specialized interface structures its internal C++ memory layout to manage the highly unique behaviors of that specific tag. For example, HTML input element allocates specialized internal variables to track form input values, selection states, validation errors, and input types like checkbox or password. Conversely, HTML template element instantiates an entirely different internal architecture. When the parser builds a template element, it deliberately isolates its internal contents inside a completely detached, unrendered data structure called a document fragment. This fragment is structurally quarantined. It does not participate in the main document layout. It completely prevents images or media within it from triggering network resource downloads, and it blocks scripts within it from executing until the template is explicitly cloned and injected into the active DOM tree. This intricate data mapping becomes even more complex when we analyze how the browser engine returns groups of elements, leading to the study of DOM collection behaviors. When you use query selectors or structural properties to retrieve a group of nodes, the bridge does not return a standard JavaScript array. Instead, it wraps the collection inside specialized interfaces, node list, HTML collection, or named node map. Understanding the memory performance implications of these collections requires analyzing the violent division between live and static collections. An HTML collection, which is returned by legacy methods like getElementsByClassName or the native children property of an element, is an absolutely live collection. A live collection does not capture a permanent, static snapshot of the elements in memory at the moment the query is run. Instead, it acts as a permanent, active window pointing directly to the live state of the DOM tree graph. The collection stores almost no hard element arrays within itself. Instead, it holds a set of query rules and filters. Let us look at the severe performance overhead this live architecture inflicts on the engine runtime. Imagine you fetch a live HTML collection of list items, and then you write a standard for loop to iterate through the collection, checking the collection's length property on every single iteration. Because the collection is completely live, it cannot trust its own past data. The moment your loop alters the DOM inside the iteration, even by adding a single class or appending a sibling node, the live collection instantly invalidates its internal structural cache. On the very next loop iteration, when the JavaScript engine reads the length property across the bridge, the C++ engine is forced to pause execution and physically walk the entire DOM subtree from scratch to recalculate exactly how many elements currently match the filter criteria. This creates a catastrophic performance cliff known as synchronous layout thrashing and cache invalidation loops, transforming a simple iteration into an expensive computational nightmare. To bypass this critical vulnerability, modern browser architectures introduced static collections, most notably represented by the node list returned when you use the modern query selector all API. A static collection behaves entirely differently in memory. The moment query selector all is executed, the C++ engine performs a single, definitive walk of the DOM tree, identifies the matching nodes, collects their wrapper pointers, and locks them into a fixed, unchanging internal array inside the collection object. If your JavaScript subsequently appends a million new elements to the page, or deletes the entire layout, the static node list remains completely unaffected. It retains its original pointers, never invalidates its cache, and never forces the engine to rescan the live tree when you query its length or access its indices. By recognizing the hidden costs of the C++ binding bridge, mapping the precise inheritance blueprints of specialized element nodes, and actively choosing static collections over live structures, you can build web architectures that minimize context switching, eliminate layout thrashing, and unlock the true raw processing speed of the modern browser runtime. Section 10.9. From Tree to Screen. Layout, Painting, and Compositing. Welcome to Chapter 10, Section 9. From Tree to Screen. Layout, Painting, and Compositing. We have now reached the final, most computationally intense phase of the browser engine's pipeline. Up to this point, the entire journey has taken place inside abstract, invisible data models. We have watched the conversion of raw network bytes into characters, the processing of characters into tokens, and the weaving of those tokens into the C++ memory trees of the document object model and the cascading style sheets object model. But a user cannot see a memory tree. A user cannot interact with a pointer graph. To display a web page, the browser must convert these data structures into a physical grid of colors painted onto a monitor. This is where the rendering engine transitions from a parsing machine into a high-speed visual compositor, executing three critical operations: layout, painting, and graphics processing unit compositing. The first step in this visual transformation is the construction of the render tree. The document object model tree captures the structural semantics of the HTML, and the cascading style sheets object model tree captures the styling rules, but neither tree alone can drive the display. The browser engine must merge them into a third, highly specialized hierarchy known as the render tree or the layout object tree. It is vital to understand that the render tree is not a one-to-one match with the document object model tree. The engine applies a strict filter during this construction phase. First, it completely strips away every node that has no physical, visual presence on the page. The entire head element, alongside its scripts, styles, and meta tags, is completely excluded from the render tree. Furthermore, if an element has been assigned the styling rule display none, the engine completely bypasses it. The node remains in the document object model tree for script access, but it generates absolutely zero representation in the render tree. Conversely, the engine can create boxes in the render tree that do not exist in your HTML source code at all. For example, when you use CSS pseudo-elements like : before or : after, these elements do not have corresponding nodes inside the document object model tree. Yet, because they generate visual content, the engine instantiates explicit layout objects for them inside the render tree. The engine also generates anonymous layout boxes to resolve structural layout conflicts. Imagine a div tag that contains a long string of bare text followed by a paragraph tag. The layout engine requires structural uniformity. It cannot have a loose text string sitting directly next to a block-level block box. To heal this structural disparity, the engine wraps the bare text string inside an invisible, unnamed container called an anonymous block box. This ensures that every element inside the layout hierarchy behaves predictably under the laws of the box model. Once the render tree locks into place, the engine initiates the layout phase, historically referred to as reflow. The layout phase is the pure geometry engine of the browser. The render tree knows what should be visible and how it should be styled, but it has no idea where things sit or how large they are. The layout engine traverses the render tree using a top-down, recursive calculation loop to determine the exact coordinates and box dimensions of every single node relative to the viewport. The layout computation operates as a negotiation between parent nodes and child nodes. The engine starts at the root node of the render tree, which corresponds to the initial layout viewport. The parent node establishes the available width constraints and hands them down to its immediate children. The child nodes then calculate their own required dimensions based on their internal text, margins, paddings, and borders. If a child box has a fluid width of 50%, it reads its parent's width, divides it by 2, and establishes its own geometric width. This process moves down to the deepest leaves of the tree. Once the widths are locked, the engine performs a bottom-up pass where child heights bubble back up to dictate the final heights of their parent containers, unless those parents have fixed, explicit height constraints. This geometric calculation is incredibly expensive. Every layout box is deeply entangled with its neighbors. If you change the width or height of a single element at the very top of the document object model tree, you disrupt the geometric assumptions of its children, its siblings, and its parent containers. This forces the browser engine to invalidate its layout cache and execute a global reflow, walking thousands of nodes recursively to recalculate coordinates. Synchronous layout thrashing occurs when JavaScript reads a visual property like offset width and immediately writes a styling modification like element style width inside a loop, forcing the layout engine to execute multiple expensive reflow cycles within a single frame, completely crushing the application's performance. With all geometries, boundaries, and coordinates finalized in memory, the engine enters the third phase, which is painting. Painting is the process of translating the geometric boxes of the layout tree into an explicit grid of colored pixels, a process known as rasterization. The engine does not simply draw everything on a single flat surface all at once. If it did, overlapping elements, drop shadows, and absolute positioning would render incorrectly. Instead, the painting engine splits the visual components across multiple display layers and follows a highly disciplined, standardized sequence called the painting order, driven by the CSS stacking context rules. When the engine paints a layer, it executes a sequence of vector drawing commands. First, it draws the background color and background images of the container box. Second, it draws the borders of the element. Third, it paints the internal text content, glyphs, and embedded media assets. Finally, it applies outlines and visual focus rings. The engine captures these vector commands as a highly complex list of recording display items, which are essentially drawing instructions like draw rect or draw text. In early browser architectures, these commands were executed directly on the main thread, painting the pixels straight into the primary window bitmap. However, if a user scrolled the page, the engine had to continuously re-execute these painting commands for the newly revealed areas, creating massive graphical lag. To solve this performance bottleneck, modern browser architectures utilize graphics processing unit compositing and layer promotion. The browser splits its operations across two distinct threads: the main thread, which handles JavaScript, the document object model, layout, and paint command generation, and the compositor thread, which is dedicated purely to coordinating the final display layers. Instead of rasterizing the entire web page into one massive, heavy bitmap, the engine breaks the layout down into multiple isolated compositing layers. The browser can choose to promote specific elements to their own independent compositing layers, completely separate from the main page body. This layer promotion is triggered by explicit CSS properties that indicate an element will move or change independently, such as utilizes 3D transforms like translate Z0, or the explicit application of the will change transform or will change opacity rules. When an element is promoted to a compositor layer, the main thread records its paint instructions just once. It then hands those instructions across to the compositor thread. The compositor thread takes the drawing list and splits the layer into a grid of uniform, manageable squares called tiles. It dispatches these tiles to specialized background helper threads called raster threads. These raster threads convert the vector instructions into raw pixel coordinates, using the system's graphics processing unit to execute the mathematics instantly. The resulting pixel graphics are stored directly in specialized graphics memory as hardware textures. Once the graphics processing unit holds these textures, the compositor thread takes complete control of the screen display. When the user scrolls the page, pinches to zoom, or triggers a hardware-accelerated CSS transform animation, the compositor thread does not wake up the main thread. It does not recalculate layouts, and it does not re-execute paint vector drawings. Instead, it speaks directly to the graphics processing unit, instructing the graphics hardware to move, scale, or fade the pre-rendered textures across the display screen instantly. Because the graphics processing unit can perform matrix modifications on textures in parallel at the hardware level, these animations run at a flawless 60 or 120 frames per second. By understanding this complete path, how the render tree filters data, how the layout engine calculates vector coordinates, how the paint engine generates drawing lists, and how the compositor thread offloads textures to the graphics processing unit, you can engineer applications that bypass the main thread entirely during user interaction, eliminating animation jank and delivering instantaneous, ultra-responsive performance from the very first byte to the final visible pixel. Section 10.10. Serialization and Developer Tool Instrumentation. Welcome to Chapter 10, Section 10. Serialization and developer tool instrumentation. Up to this point in our journey, we have observed the browser rendering engine as a strict, one-way conveyor belt. We watched raw network bytes enter the system, transform into characters, split into tokens, lock into a C++ node tree, and finally compute into geometric boxes painted as pixels on the screen. But inside a live, production web application, this pipeline is rarely a one-way street. As developers and engineers, we constantly need to reverse this process. We write scripts that query the active tree, inject new layout fragments on the fly, and open up advanced developer interfaces to inspect the engine's internal state. To master this runtime environment, we must dissect the deep mechanics of dynamic serialization interfaces, understand the performance and security risks of direct document manipulation, and explore how browser developer tools expose the internal structures of both the primary document object model and its silent sibling, the accessibility tree. Let us first examine the exact technical mechanics of serialization and the dynamic mutation interfaces, specifically focusing on inner HTML, outer HTML, and insert adjacent HTML. Serialization is the mathematical inverse of parsing. When you write a line of JavaScript that reads the inner HTML property of an element, you are forcing the browser engine to perform a real-time data translation. The engine must halt its current operations, step across the C++ binding bridge, and execute a recursive traversal of the chosen element's subtree inside the live memory graph. For every C++ node it encounters, it looks up the tag name, reads the local attribute dictionary, checks the text strings, and reconstructs a clean, human-readable HTML text string on the fly. However, the true engineering complexity, and the massive performance vulnerabilities, manifest when you perform a write operation using inner HTML. When you assign a text string to an element's inner HTML property, the browser engine does not execute a simple text change. Instead, it triggers a mini execution of the entire rendering pipeline right in the middle of the runtime lifecycle. The instant the string crosses the binding bridge, the engine completely destroys every single child node currently living inside that target element, purging them from the C++ heap. It then instantiates an ephemeral, specialized instance of the HTML parser state machine. This runtime parser takes your raw JavaScript string, runs it through tokenization, executes the standard error recovery and tree construction algorithms, and generates a brand new set of C++ nodes. Finally, it graphs this new subtree into the primary document object model graph, forcing a synchronous style recalculation and a visual layout reflow on the page. This destruction and recreation process creates a massive performance cliff. If a developer uses inner HTML to append a single line of text to a massive container element, they are unknowingly forcing the engine to wipe out and rebuild thousands of perfectly healthy nodes. Furthermore, because the old C++ objects are completely obliterated, any JavaScript event listeners or operational references bound to those original nodes are permanently broken, creating invisible memory leaks and broken interfaces. ####. Beyond performance, this runtime parsing mechanism introduces the single most dangerous security vector on the modern web, cross-site scripting, or XSS. Because the inner HTML writer invokes the full HTML parser, if an untrusted string containing malicious user input is passed into the property, the parser will treat it as legitimate structural code. While the engine protects against basic script tag execution inside inner HTML injections by explicitly forcing script tokens into a non-executable state during this specific runtime phase, malicious actors bypass this defense easily using inline event vectors. For example, injecting an image tag with a broken source attribute and an inline honorer attribute allows the attacker to execute malicious JavaScript the exact moment the engine attempts to resolve the image layout, completely compromising the application security. To mutate the document object model safely and efficiently, advanced architectures avoid inner HTML and utilize outer HTML or insert adjacent HTML. The outer HTML property operates under similar parsing rules, but its scope shifts, replacing the target node itself along with its contents. The true surgical strike, however, is achieved using insert adjacent HTML. This interface allows you to pass a text string and a specific placement directive, such as before begin, before end, or after end. When you invoke insert adjacent HTML, the engine does not wipe out the target container. It uses a specialized parsing routine to tokenize the incoming string and injects the resulting nodes directly into the exact target slot specified, completely preserving the surrounding C++ tree architecture, maintaining active event listeners, and saving immense computational energy by avoiding global cache invalidation loops. To monitor, optimize, and debug these dynamic mutations, we must rely on developer tool instrumentation. When you open the browser developer panels and select the Elements tab, it is vital to remember that you are not looking at a static code file. You are viewing a high-level, real-time graphical serialization of the live C++ memory graph. The developer tools act as a constant diagnostic probe inside the engine. By comparing the dynamic visualization inside the Elements panel against the static data blocks inside the Network panel, you can instantly trace exactly how the browser's streaming parser and error recovery systems have altered your source code. If the Network panel shows a broken table layout or unclosed formatting tags, but the Elements panel shows a pristine, beautifully nested structure, you are witnessing the engine's fault tolerance algorithms actively working in the background. The Elements panel also highlights dynamic modifications in real time, flashing colored indicators whenever JavaScript mutations alter an attribute or insert a new node, giving you a direct window into runtime behavior. However, modern developer tool instrumentation extends far deeper than the standard layout tree. Built directly alongside the primary document object model is a hidden, secondary node hierarchy known as the accessibility tree. When the HTML parser constructs an element node, the engine simultaneously evaluates that node's semantic characteristics, local attributes, and structural orientation to generate a corresponding node inside the accessibility tree. This secondary tree is what the browser exposes to the operating system's assistive technologies, enabling screen readers and voice controllers to navigate and interpret the interface for users with disabilities. Through modern developer panels, you can toggle the viewport to completely unmask this accessibility architecture. The accessibility panel strips away all visual layout concerns, it ignores backgrounds, font sizes, and layout grids, and displays the raw, semantic identity of your application. It exposes the calculated name, the functional role, and the interactive state of every node. For instance, if you build a visual button using a generic div tag and style it beautifully with CSS, the primary layout engine will render it perfectly on the screen. But if you inspect the accessibility tree, you will instantly see that the node is identified merely as generic text container, rendering it completely invisible and broken for a screen reader user. By utilizing developer tool instrumentation to verify that your semantic markers match your visual output, you bridge the gap between sight and accessibility, ensuring the engine generates a valid representation in both operational trees. Finally, the instrumentation pipeline routes critical internal diagnostics straight to the console panel. The console is not just a destination for custom console log statements, it is the primary exception reporting channel for the browser engine itself. When the HTML streaming parser hits a non-fatal character encoding crisis, or when the style engine detects an illegal layout rule, or when a script crosses the C++ binding bridge and violates the document's content security policy, the engine flags the event. It halts the local routine, packages the error metadata, and dispatches a hard engine warning or error directly to the console. These platform-level errors tell you exactly where the critical rendering pipeline is stalling. They expose failed network asset connections, blocked cross-origin resources, and synchronous script execution timeouts that are actively freezing the main thread. By mastering this complete instrumentation ecosystem, by tracking dynamic serializations via insert adjacent HTML, analyzing structural changes inside the Elements panel, auditing semantic health via the accessibility tree, and monitoring engine exceptions through the console, you gain the diagnostic insight required to see past the illusion of the text string. You control the living runtime environment of the browser engine, optimizing your applications for maximum speed, impenetrable security, and flawless execution across every single device on the web. Section 10.11. The Living Standard Workflow and Modern Evolution. Welcome to Chapter 10, Section 11. The Living Standard Workflow and Modern Evolution. We have arrived at the final section of our architectural journey through the browser rendering engine. Up to this point, we have treated the browser as a fixed, stable machine executing predictable math, parsing tokens according to unyielding laws, and calculating layout coordinates within rigid C++ frameworks. But the single most remarkable aspect of the web platform is that the engine itself is constantly shifting underneath your application code. Unlike traditional software engineering platforms where compilers and runtimes are locked to discrete, major version numbers, the web operates as a continuous runtime ecosystem. The HTML language is not a dead document locked in an archive, it is a living specification that mutates and expands every single day. To survive as a world-class web engineer, you must master the mechanics of this continuous evolution, understanding the structural workflow of the living standard, the processes governing engine convergence, and the defensive engineering paradigms required to author highly stable applications on top of a fluid runtime. Let us first analyze the historical disruption and modern operation of the WHATWG living standard lifecycle. For the first 2 decades of the web, document specifications were managed by the W3C using a traditional snapshot model. This process yielded fixed specifications like HTML4 or the early drafts of HTML5. Under that legacy model, a committee would spend years debating features in the abstract, compile a massive text document, declare it a finished standard, and then hand it off to browser vendors to implement. This approach failed catastrophically. Browser engineers would encounter massive technical edge cases while writing the actual C++ parser code, leading to divergent custom implementations, broken compatibility, and a fractured web. To resolve this systemic failure, engineers from Apple, Mozilla, and Opera bypassed the committee structure in 2004 and formed the Web Hypertext Application Technology Working Group, known universally as the WHATWG. The foundational thesis of the WHATWG was revolutionary: HTML should never have a version number again. They established the living standard, a single, continuously updated document that maps out the current operational realities and immediate future capabilities of the web platform. The living standard workflow operates as a highly disciplined, multi-stage incubation lifecycle driven by real-world implementation data. The process begins with an initial feature proposal, typically generated by application developers or browser architects who identify a structural limitation in the current platform. This proposal enters an open incubation phase, usually hosted within the Web Incubator Community Group, or WICG. Here, engineers debate the API signatures, write technical explainers, and outline the core use cases. The critical turning point in this lifecycle occurs when the proposal moves from text into actual code. Unlike the legacy model, a feature cannot become part of the official WHATWG living standard purely through abstract agreement. It requires experimental implementation. Engineers across the major browser engines, Chromium's Blink, Apple's WebKit, and Mozilla's Gecko, will actively prototype the new feature directly inside their experimental source code bases. They map out the new state machines in the tokenizer, allocate new C++ node classes in the tree constructor, and expose the new wrappers across the binding bridge to the JavaScript engine. As these implementations take shape, the text of the specification is refined in real time to match the real-world behaviors and engineering constraints uncovered during prototyping. A feature only graduates to a fully standardized state when multiple independent browser engines achieve absolute behavioral convergence, proving that the API is stable, performant, and backwards compatible. The standard follows the code, ensuring that the specification remains a precise engineering blueprint rather than a collection of theoretical ideas. This continuous evolution requires a highly coordinated deployment pipeline across the industry, driving modern engine convergence. Browser vendors ship their software using sequential, multi-tiered release channels that allow new engine features to be aggressively tested before reaching millions of production users. At the absolute front line of this pipeline are the daily experimental builds, including Chromium Canary, Safari Technology Preview, and Firefox Nightly. These bleeding-edge environments contain the raw, unrefined commits straight from the engineering teams. New elements, updated parsing rules, and experimental layout APIs are exposed here first, often hidden behind runtime configuration flags. This allows developers to load their existing applications against the future engine architecture and catch regression bugs before they scale. To ensure that these independent engines actually achieve the visual and structural convergence demanded by the living standard, the industry relies on a massive, shared automated verification suite known as Web Platform Tests, or WPT. Web Platform Tests is a monolithic, open-source testing infrastructure funded and maintained by all major browser vendors. It contains millions of explicit, rigorous compliance tests that run continuously against every single build of every engine. These tests evaluate the engine at every microscopic phase of the pipeline. They check if specific malformed token streams trigger the exact same error recovery algorithms, verify that the C++ wrapper inheritance chains possess the precise prototype properties defined by the spec, and execute automated pixel comparisons to ensure that a layout box calculates identical geometric coordinates across Blink, WebKit, and Gecko. By making test compliance a mandatory metric for browser release pipelines, the industry enforces an unprecedented level of cross-compatibility, turning the theoretical living standard into a uniform, dependable global utility. Yet, despite this massive testing infrastructure, the reality of a living standard means that features will inevitably land in some engines before others, creating a permanent state of functional disparity across the web. To build enterprise-grade software in this environment, you must completely abandon the concept of writing code for specific browser names or version strings, a legacy practice known as user agent sniffing. User agent sniffing is a fragile, anti-pattern engineering flaw. It relies on reading the generic text string exposed by the navigator user agent property in JavaScript and guessing what features that browser supports. This fails because strings can be spoofed, legacy browsers cannot predict future capabilities, and engines frequently update their internal architectures without changing their public identifier tokens. Instead, modern web architecture demands the strict application of defensive authoring driven by programmatic feature detection and progressive enhancement. Feature detection is the engineering practice of directly querying the live runtime environment at execution time to verify if a specific C++ binding wrapper or layout capability exists before attempting to invoke it. Let us look at exactly how this is executed programmatically across both the script and styling layers. In JavaScript, you can safely verify the existence of a modern DOM interface by executing a simple in check against the global window object, or by inspecting the explicit prototype chain of an element interface. For example, before calling a modern method like showModal on a dialog node, your defensive code evaluates whether the showModal property is explicitly present on the native HTML dialog element prototype wrapper. If the runtime check returns true, the application safely executes the optimized, platform-native routine. If the check returns false, the engine gracefully branches into a fallback execution path, running a custom JavaScript polyfill that emulates the behavior using traditional elements and manual coordinate calculations. The exact same defensive strategy is deployed within the styling and layout layers using CSS feature queries. By utilizing the @supports directive directly within your stylesheet rules, you instruct the style engine to evaluate its own internal rendering capabilities before applying a block of rules. You can write a query stating @supports display grid or @supports color mix, and the layout engine will check its own compiled capabilities. If the engine understands the layout rules, it activates the optimized layout block. If it strikes a brand new property it does not recognize, the parsing state machine simply ignores the unknown tokens due to its native fault tolerance rules, allowing the element to fall back gracefully to standard block or inline formatting baseline. This is the true philosophy of progressive enhancement. You deliver a rock-solid, highly accessible baseline experience built entirely on the resilient, core foundations of the HTML parsing pipeline. Then, using programmatic feature queries, you surgically layer on advanced visual layouts, optimized interactive workflows, and hardware-accelerated compositor animations for modern engines that possess the required capabilities. To architect these systems, you treat capability databases like MDN WebDocs and CanIUse not as passive reference websites, but as essential architectural inputs. You monitor engine release pipelines, analyze capability support graphs, and proactively map out your application's structural fallback layers. By mastering this final evolutionary tier, by understanding the incubation lifecycle of the WHATWG living standard, auditing engine convergence via web platform tests, and executing absolute defensive authoring through live feature detection, you elevate your craft from simple coding to high-level systems engineering. You are no longer just writing text files for a static program to read. You are orchestrating a living, breathing, real-time multi-threaded computing environment. You possess the complete diagnostic map of a critical rendering path. From the initial ingestion of volatile binary network bytes, through the state transitions of tokenization, down into the C++ architecture of the document object model, and finally out to the hardware-accelerated tiles of the graphics processing unit compositor, you know exactly how the browser converts thought into layout, logic into interface, and bytes into pixels. Section 11.1. The Accessibility Tree and Implicit ARIA Roles. Welcome to Chapter 11, Section 1. The Accessibility Tree and Implicit ARIA Roles. When we spend hours crafting an HTML document, we naturally judge our work by opening a browser window and looking at the visual viewport. We look at the headers, the form fields, the tables, and the layout structure as they display on the screen. But as an elite web engineer, you must realize that the visual viewport represents only half of the rendering engine's output. Behind the scenes, completely hidden from sight, the browser engine is continuously running a second, equally critical compilation pipeline. It takes the primary document object model tree and translates it into a secondary, parallel data graph known as the accessibility tree. This section is a deep dive into this silent architecture. We will unmask how the accessibility tree is constructed inside system memory, analyze the exact engineering mechanics of implicit ARIA roles, and master advanced ARIA attributes to build web applications that achieve absolute semantic clarity for assistive software devices. Let us first analyze the structural reality of the accessibility tree. The document object model tree captures the technical reality of your markup. It tracks every element tag, every C++ binding wrapper, every class string, and every hidden comment node. But assistive software, such as screen readers, refreshable braille displays, and voice control systems, cannot easily interpret a raw DOM tree. A screen reader does not care if an element is a div styled with specific colors, nor does it care about text formatting nodes that do not add semantic value. To bridge this gap, the browser engine performs a continuous transformation pass on the DOM tree to compute the accessibility tree. During this pass, the engine strips away everything that lacks semantic substance. It purges non-visual configuration nodes like head tags, filters out elements hidden via hidden attributes or the display none property, and collapses plain presentational wrappers. For the nodes that remain, the engine generates an accessibility object. This object does not store visual styling properties like fonts, margins, or grid placement coordinates. Instead, it exposes 4 critical parameters to the operating system's assistive API layer: the node's role, its name, its state, and its value. The role defines what the element actually is, such as a checkbox, a button, a heading, or a main landmark region. The name is the textual label computed by the engine to identify that specific control, such as the text inside a link or the label assigned to an input. The state tracks the live operational status of the element, whether it is currently focused, expanded, checked, or disabled. The value holds the current numerical or textual data payload of the node, such as the volume level of a range tracking input. This tree forms a parallel structural graph. If your DOM tree contains semantic layout failures, the accessibility tree will break down, rendering your application completely unnavigable for users who rely on assistive hardware to consume the web. This brings us to the core engineering mechanism that governs this tree mapping: native semantic element role assignments versus duplicate ARIA configuration overrides. ARIA stands for Accessible Rich Internet Applications. It is a specification that allows developers to manually inject roles and states into the accessibility tree using attributes like role equals button or role equals navigation. However, the absolute first rule of ARIA architecture is clear: don't use ARIA if you can use native HTML semantics instead. Every valid HTML5 element possesses a hard-coded, built-in semantic assignment known as an implicit ARIA role. Let us look at how the engine treats these native mappings. When the parser encounters a NAV tag, the engine automatically assigns it the implicit role of navigation inside the accessibility tree. A main tag automatically becomes the main landmark region. An H1 through H6 tag triggers an implicit heading role coupled with a specific hierarchy level attribute. A button tag maps natively to the button role, and an input type equals checkbox becomes a checkbox control. Because these roles are natively bound within the C++ rendering engine, they work flawlessly across every operating system and assistive device without a single extra byte of code. The widespread engineering failure occurs when developers execute duplicate ARIA overrides, writing code like NAV role equals navigation or button role equals button. This is not only completely redundant, but it also increases the character weight of the document and exposes the pipeline to manual coding errors. Worse yet are destructive overrides, where a developer places a generic tag like a div, styles it to look like an interactive button, and manually slaps role equals button onto it. While this manual override successfully updates the role parameter inside the accessibility tree, it forces a massive architectural debt onto the system. A native button element automatically handles keyboard focus tracks, participates in standard tab indexing, and dispatches native click triggers when a user presses the spacebar or the enter key. A generic div with a manual button role does absolutely none of these things. It remains a broken text box that cannot be focused via the keyboard and completely ignores spacebar interactions, shattering the accessibility profile of the application. The engine's implicit roles must be respected as the foundation of your document graph, using manual ARIA roles strictly as a last resort to enhance custom interfaces that native HTML cannot describe. When you do encounter complex, custom UI paradigms that native semantics cannot fully support, you must deploy advanced ARIA attributes to bridge the communication gap. 3 core tracking domains allow you to precisely manage labels, relationships, and dynamic state changes across the binding layer: ARIA label, ARIA described B, and the dynamic ARIA live region. Let us first examine how the engine resolves names using ARIA label. Under normal conditions, the accessibility engine computes an element's name from its internal text content. If you create an anchor link containing the word home, the calculated accessible name is home. But imagine an interactive interface where a button features nothing but a graphic symbol, like a magnifying glass vector image. The button contains 0 text characters. Left unconfigured, the engine's text computation returns an empty string, leaving a screen reader user with a completely anonymous control. By applying the ARIA label attribute, written as ARIA label equals search site, you bypass the standard text node collection routines. The engine reads your custom string and forces it directly into the button object's accessible name slot. When an assistive device interacts with that button, it skips the blank visual layer and reads your precise descriptive label aloud, restoring clarity to the control. To manage complex structural relationships, we utilize ARIA-describedB. While a label provides a short identifier, elements often require extended contextual descriptions. The ARIA-describedB attribute creates a formal metadata link between an interactive control and a separate text element elsewhere on the page. For example, when validating a form, you might have a password input box, and several lines below it, a paragraph detailing the specific password complexity rules. By passing the ID of that complexity paragraph into the input field's ARIA-describedB attribute, you establish an explicit relationship link inside the accessibility tree. The moment a screen reader focuses the input field, the engine reads the primary input label, pauses, crosses the relationship link, and reads the entire complexity description paragraph, ensuring the user has full situational context before typing a single character. Finally, we must manage the highly volatile domain of dynamic web content using ARIA-Live and ARIA-Atomic. The document object model is constantly changing, errors flash onto the screen, notifications pop up, and text counters increment. To a sighted user, these visual updates are instantly noticeable. But to a screen reader user whose focus is locked inside a specific text input, an update happening elsewhere on the page is completely invisible. To force the engine to track and announce these updates, we configure an element container as an ARIA-Live region using the ARIA-Live attribute. The ARIA-Live property accepts two main configuration values, polite and assertive. When a live region is set to ARIA-Live equals polite, the browser engine watches the container subtree for changes. When a new text token or node is injected, the engine queues the announcement text safely. It waits until the user has stopped typing or reading, and then announces the update smoothly without interrupting the user's active workflow. However, if you set the container to ARIA-Live equals assertive, the engine elevates the update to an emergency priority status. The instant a mutation registers, the browser bypasses the speech queue, aggressively interrupts whatever the screen reader is currently saying, and forces the immediate announcement of the new text payload. This assertive override must be used with extreme discipline, reserved exclusively for critical system alerts, timeout warnings, or catastrophic application errors. To control exactly how much data is announced during these live updates, you couple the region with the ARIA-Atomic attribute. The ARIA-Atomic property accepts a simple Boolean token, true or false. Imagine a layout section displaying a live tracking notification, like shopping cart, 3 items. If JavaScript updates the text node from 3 to 4 items, and ARIA-Atomic is set to false, the accessibility engine looks only at the mutated character block. It will aggressively announce nothing but the single changed number, 4. Without context, this announcement is completely meaningless to a user. By explicitly setting ARIA-Atomic equals true, you instruct the tree monitor to intercept the update, read the boundaries of the entire live container, and announce the complete, unified text string, shopping cart, for items. The engine packages the entire context, ensuring the dynamic announcement makes absolute sense. Now, to ensure your source strings compile flawlessly into these memory networks without trailing syntax errors or orphan tags, we will execute a complete spoken code walkthrough. We are going to write a highly secure, semantically accessible form container. To do this cleanly, we will use the strict tag pairing technique, meaning we will write the complete opening tag and the complete closing tag first, to close the element loop in memory before we ever step backward to put any configuration attributes. Listen to the workflow instructions and visualize the cursor movements step by step. First, initialize the primary landmark scope using the tag pairing technique. Type less than, main, greater than. Then, immediately type the closing pair, less than, / main, greater than. The structural boundary is locked. Drop your cursor back inside the main tag block, create a new line, and initialize a generic block flow box. Type less than, div, greater than, followed instantly by less than, / div, greater than. Now, move your cursor backward, stepping directly into the div tag's opening boundary before putting any attributes. Hit the spacebar and type class equals, open quote, console field, close quote. Move your cursor back down between the div elements to insert the control details. Next, instantiate the form label using the tag pairing workflow. Type less than, label, greater than, then immediately close it with less than, / label, greater than. Move your cursor backward into the opening label tag before putting the attributes. Hit space and type for equals, open quote, secure passcode, close quote. Move your cursor forward between the completed label elements and type the text payload, security passcode. Below the label, we must drop in our input field. Because an input is a structural void element, it does not accept internal child text blocks, meaning the tag pairing technique operates inside a single self-closing instruction. Type less than, input, space, / greater than. The void element loop is fully closed. Now, step your cursor backward, moving inside the tag before putting the attributes. We will layer on 4 distinct configuration properties sequentially. First, hit space and declare the engine interface mode by typing type equals, open quote, password, close quote. Second, hit space and map the network identification link by typing ID equals, open quote, secure passcode, close quote. Third, hit space and trigger the native client-side validation constraint by typing the standalone attribute token, required. Fourth, we must forge the advanced accessibility tree link. Hit space and type aria described b equals, open quote, passcode requirements, close quote. The input node is completely configured. Directly below the input, we must write the contextual description paragraph that our aria property points to. Execute the tag pairing sequence, type less than, p, greater than, followed immediately by less than, / p, greater than. Step your cursor backward into the opening p tag before putting the attribute. Hit space and type ID equals, open quote, passcode requirements, close quote. Move your cursor forward between the paragraph boundaries and type the string payload. Passcode must contain at least 8 characters. Finally, we will append our live monitoring section at the bottom of the main frame. Execute the tag pairing sequence, type less than, section, greater than, followed immediately by less than, / section, greater than. Move your cursor backward, stepping inside the opening section tag before putting the attributes. We will apply 2 advanced accessibility triggers to manage the runtime memory state. Hit space and type aria live equals, open quote, polite, close quote. Then, hit space and type aria atomic equals, open quote, true, close quote. Move your cursor forward between the section containers to drop in the final text tracking node. Run the tag pairing technique one last time, type less than, p, greater than, less than, / p, greater than. Move your cursor inside the text nodes and type the live dynamic layout text, current cart payload, for items. By executing this exact structural developer workflow, pairing your tags securely and closing the loops before putting attributes, you eliminate syntactical drift and guarantee that your markup translates cleanly into both live memory structures. You deliver a high-speed, perfectly normalized, and absolutely accessible interface for every single user across the web. Section 11.2. SEO Mappings. Welcome to Chapter 11, Section 2. SEO Mappings. When we discuss optimizing a website for search engines, the conversation is frequently dominated by marketing terminology, keyword densities, and external backlink profiles. But as a systems engineer, you must look past the marketing layer and understand search engine optimization as a strict data mapping problem. Search engine crawlers, such as Googlebot or Bingbot, are automated, headless software programs designed to ingest the global web data stream, map information architectures, and build a massive, searchable index of human knowledge. When a crawler hits your server, it executes the exact same critical rendering pipeline we have traced throughout this course, converting bytes to characters, characters to tokens, and tokens to a live document object model tree. However, the crawler does not look at visual layouts, it does not calculate GPU compositing tiles, and it does not care about visual pixel presentation. Instead, it parses the document object model tree to construct an internal semantic outline, evaluating structural hierarchy to calculate content weight and determine search categorization indexing. This section is a deep dive into the engineering mechanics of SEO mappings. We will explore how automated indexing bots analyze document layouts, examine how structural element distribution controls semantic weight, and master the exact document architecture required to optimize your pages for search categorization algorithms. Let us first analyze the crawler's indexation workflow and the reality of the two-pass rendering architecture. Modern search crawlers utilize a highly optimized, dual-stage ingestion pipeline. When a crawler discovers your URL, it immediately executes Pass 1, downloading the raw HTML byte stream, executing instant tokenization, and parsing the primary structural node graph. The crawler instantly evaluates this raw HTML tree to establish the baseline identity, language, and core outline of your page, committing this data to the search index immediately. Pass 2 involves running the page through a full automated browser rendering engine to execute client-side scripts and parse dynamic layouts. However, because rendering layouts and executing JavaScript consumes massive amounts of computational energy and cloud hardware cycles, Pass 2 is frequently deferred. The crawler may wait days or even weeks before it allocates the computing resources to execute your scripts and render your dynamic views. Because our architectural paradigm in this course is built entirely on pure HTML excellence, our documents possess a massive competitive advantage. By delivering 100% of your content, metadata, and structural weight directly inside the initial raw HTML byte stream, you ensure that the crawler's first pass captures a completely optimized, highly detailed, and perfectly indexable map of your data instantly, completely bypassing the scheduling delays of the secondary rendering layer. To optimize this initial pass, the browser engine and the crawler rely on a strict computational outline constructed via logical heading distribution rules. Headings, from H1 through H6, represent the primary skeletal scaffolding of your information architecture. In early web development, amateurs used heading tags as visual sizing shortcuts, making text in H1 simply because they wanted it to look large on the screen. To a search crawler, this is a catastrophic optimization failure. The crawler reads heading levels strictly as mathematical node weights that define the parent-child nesting relationships of your content topics. The H1 element acts as the absolute semantic root of the document scope, declaring the singular, primary topic of the entire page layout. The engine expects exactly one H1 per document tree. When the crawler walks the tree and encounters an H2, it programmatically subcategorizes the subsequent text nodes as an explicit subtopic branching directly off that main H1 route. An H3 token creates a nested subtopic underneath that specific H2, and this hierarchical inheritance chain continues down to H6. If your document skips heading ranks, for example, dropping an H4 immediately after an H1, or jumping randomly from an H2 to an H5, the crawler's outline algorithm detects a structural discontinuity. The semantic chain fractures, the automated indexing bot struggles to determine the relationship boundaries of your information, and the page suffers a structural categorization penalty in the global index. Headings must be authored as a continuous, mathematically strict logical ladder, completely decoupled from any visual display intents. Alongside heading hierarchies, crawlers utilize modern HTML5 landmark elements to divide your layout into explicit priority zones, executing semantic element prioritization. Before these semantic elements were standardized, web layouts were built entirely out of generic div wrappers. To a search bot, a div holds absolutely zero semantic meaning. It is an invisible, anonymous structural box. A crawler forced to parse a page built exclusively of divs had to guess which text nodes represented the actual core article, and which blocks were nothing but repetitive navigational headers or sidebar advertisements. Modern semantic landmarks completely eliminate this ambiguity, allowing you to explicitly dictate which zones of your document graph receive maximum indexing weight. When the crawler encounters the main element, it notes the absolute core focus of the layout document. The engine focuses its primary keyword extraction and data mining algorithms directly inside this node, giving the text within it maximum structural priority. Conversely, when the crawler encounters a NAV tag or a footer tag, it recognizes these zones as document boilerplate, repetitive navigation loops, and copyright legal text that appear identically across thousands of pages on your domain. The indexer intentionally downweights the data payloads inside these boilerplate zones, preventing repetitive menus from diluting the unique keyword focus of the main content. If you place your primary, high-value text nodes inside an incorrectly assigned landmark, or leave your layout buried inside generic div text blocks, the automated indexing bot will struggle to categorize the page accurately. By wrapping your content inside pristine semantic elements like main, article, and section, you explicitly guide the crawler's mathematical focus, ensuring your unique data is indexed with maximum fidelity. Now, to synthesize these search engine optimization mappings into a real-world document structure, we will execute a complete spoken code walkthrough. We are going to write a perfectly search-optimized blog article landmark structure. To guarantee flawless syntax, we will strictly deploy the tag pairing technique. We will write the complete opening tag and the complete closing tag first, establishing the closed loop in memory, before we ever step backward to put any configuration attributes. Listen to the workflow instructions and visualize the cursor movements step by step. First, initialize the primary semantic landmark zone for the entire page using the tag pairing workflow. Type less than, main, greater than, then immediately close the loop by typing less than, / main, greater than. Drop your cursor back between the main tags, create a new line, and instantiate an independent content block optimized for distribution. Type less than, article, greater than, followed instantly by less than, / article, greater than. The article boundary is locked. Now, move your cursor backward, stepping directly inside the article tag's opening boundary before putting any attributes. Hit the spacebar and type item it equals, open quote, https:// domain.com, / post, close quote. This injects a unique, globally distinct machine identifier directly into the crawler's index graph. Move your cursor back down between the article containers to insert the heading hierarchy. Instantiate the absolute semantic root heading for the article using the tag pairing technique. Type less than, h1, greater than, then immediately close it with less than, / h1, greater than. Move your cursor forward between the h1 elements and type the exact primary topic string, architectural analysis of modern browsers. The main topic index is secured. Below the h1, we must create a dedicated section for a specific subtopic. Execute the tag pairing sequence, type less than, section, greater than, followed immediately by less than, / section, greater than. Move your cursor back down between the section elements to anchor it with a proper nested heading. Run the tag pairing technique to instantiate the secondary subtopic heading. Type less than, h2, greater than, then close it with less than, / h2, greater than. Move your cursor between the h2 boundaries and type the subtopic text, the ingestion pipeline. The crawler now reads this explicitly as a subtopic nested under our main h1 header. Directly below the h2, drop in the primary textual data block. Execute the tag pairing technique, type less than, p, greater than, followed instantly by less than, / p, greater than. Move your cursor inside the paragraph elements and type the data payload string. The rendering engine parses raw network binary blocks directly inside the stream buffer. Finally, we will add a tangential landmark block at the bottom of the article frame to hold secondary references. Execute the tag pairing sequence, type less than, aside, greater than, followed immediately by less than, / aside, greater than. Move your cursor back between the aside elements to provide its local heading anchor. Run the tag pairing workflow, type less than, h3, greater than, then close it with less than, / h3, greater than. Move your cursor between the h3 elements and type the string, related ingestion standards. By executing this highly disciplined developer workflow, pairing your tags securely to lock your structural loops before putting attributes, you build a flawless document map for automated search categorization indexing. You bypass the vulnerabilities of deferred script rendering, eliminate outline discontinuities, and ensure your web applications are interpreted with absolute clarity and maximum priority by every search engine crawler on the global web. Section 11.3. Performance and Security Integration Recaps. Welcome to Chapter 11, Section 3. Performance and Security Integration Recaps. When developers deploy production web applications, they often treat performance optimizations and security configurations as secondary concerns to be handled entirely by server network administrators or heavy JavaScript frameworks. But as a systems engineer, you must realize that the HTML document graph is the absolute front line of defense for your application's security posture and the primary engine driving resource loading efficiency. The browser's networking stack and parsing engine read your document markup to determine asset loading schedules, security containment boundaries, and cryptographic verification loops. This section is a deep dive into the engineering mechanics of security and performance optimization embedded straight into the document syntax. We will explore how browser engines execute cross-origin resource configurations, map the implementation of cryptographic asset validation pipelines, and analyze the optimization strategies behind speculative network hint infrastructures. Let us first examine the security mechanics behind cross-referencing media asset validation checks via subresource integrity, known universally as SRI, utilizing the integrity property. In the modern web ecosystem, applications frequently load external assets, such as frameworks, libraries, or styles, from third-party content delivery networks. This introduces a critical security vulnerability. If a malicious actor compromises that third-party server, they can silently inject malicious code into the target asset file. Because the browser engine blindly executes the downloaded code on your main thread, your user data becomes entirely exposed. To eliminate this supply chain threat, HTML provides the integrity attribute. The integrity attribute requires you to supply a strict cryptographic hash of the expected file content, typically calculated using SHA-256. Let us look at how the browser engine processes this validation check on a microscopic level. When the parser encounters an asset tag featuring an integrity property, it dispatches the network request as usual. However, when the raw bytes drop into the socket buffer, the browser engine does not pass them immediately into the conversion or tokenization pipelines. Instead, it pauses the execution stream, intercepts the raw byte payload, and runs the entire file through its internal cryptographic engine to compute a real-time signature hash. The engine then executes a strict bitwise comparison between the computed hash and the cryptographic string declared inside your integrity attribute. If the two hashes match perfectly, the engine confirms the file's absolute authenticity and safely passes the characters down to the rendering pipeline. But if even a single character or byte inside the remote file has been altered, the computed hash fails the validation check completely. The browser engine instantly flags the mismatch as a catastrophic security violation, throws a hard error to the diagnostic console, and permanently blocks the asset from executing or impacting your layout tree, neutralizing the attack completely. Alongside cryptographic file validation, your document syntax must actively coordinate cross-origin security rules using the cross-origin attribute. When a web page requests a resource from a completely different domain, port, or protocol, it triggers a cross-origin resource sharing boundary, known as CORS. By default, the browser engine wraps these cross-domain asset requests inside anonymous, low-privilege network wrappers, completely stripping out user credentials, session cookies, and authorization headers to protect user privacy. The cross-origin attribute allows you to explicitly configure secure media and script contexts by telling the engine exactly how to manage these cross-origin privacy constraints. The cross-origin attribute accepts two primary operational modes, anonymous and use credentials. When you set cross-origin equals anonymous, you instruct the engine to dispatch the network request without passing any local user cookies or authentication tokens, but you explicitly mandate that the remote server must return valid CORS response headers. If the remote server fails to return these valid security headers, the engine blocks the resource from loading. This configuration is absolutely mandatory when using advanced features like rendering third-party images inside an HTML canvas element. If you attempt to draw a cross-origin image that was loaded without explicit anonymous CORS clearance, the browser engine immediately triggers a defensive security state known as tainting the canvas. Once a canvas is tainted, its pixel memory grid becomes permanently locked, preventing JavaScript from reading or exporting its data to prevent cross-site information leaks. By explicitly configuring cross-origin equals anonymous, you clear the security validation loop, preventing canvas tainting and keeping the pixel pipeline completely open and secure. If the application requires session tracking across third-party endpoints, you switch the property to cross-origin equals use credentials, forcing the engine to transmit session cookies while maintaining a strict cryptographic validation check on the incoming server headers. While these security layers protect your data, you must simultaneously accelerate your application's loading pipeline by resolving asset loading restrictions cleanly using network hint configurations. As we traced throughout our study of browser internals, the main thread is continuously threatened by blocking resources that freeze parsing and delay rendering. Network hints act as proactive, speculative processing instructions embedded straight inside link elements, allowing you to bypass standard parser scheduling and execute network operations long before the primary layout engine discovers an asset resource. The pipeline utilizes four primary network hints sequentially: DNS prefetch, preconnect, prefetch, and preload. Let us break down the exact performance engineering driven by each hint mode. The first is DNS prefetch. When the browser engine encounters a standard external URL, it must resolve the domain name into a physical IP address by performing a domain name system lookup. This lookup introduces a critical latency block, often taking hundreds of milliseconds. By writing a link tag with rel equals DNS prefetch, you instruct the browser's background network thread to instantly perform the domain lookup in the background while the main thread is still tokenizing the early body tags, eliminating that latency completely before the asset is ever requested. To accelerate the connection even further, you upgrade the instruction to rel equals preconnect. Preconnect goes far beyond a basic DNS lookup. When the engine processes a preconnect hint, it forces the network thread to speculatively execute three distinct network phases ahead of time: the DNS lookup, the TCP three-way handshake, and the complete secure TLS cryptographic negotiation wrapper. By forging this live connection socket in advance, you eliminate the entire round-trip time overhead. The moment the main parser finally encounters the real asset resource later in the file, the connection is already open and waiting, allowing the data packets to stream down the wire instantly. When you need to optimize future user navigations, you deploy rel equals prefetch. Prefetch is a low-priority predictive optimization hint. It tells the engine that the user is highly likely to navigate to a specific subpage or require a specific heavy asset during their next session task. The browser waits until the current primary layout is completely painted and the main thread enters a completely idle state. It then speculatively downloads the prefetched asset in the background and commits it directly to the browser's persistent disk cache, ensuring the subsequent page transition feels completely instantaneous. The absolute highest priority hint in the performance ecosystem is rel equals preload. Preload is a mandatory, high-velocity override command. You apply a preload hint when you know with absolute certainty that the current page cannot complete its initial visual paint without a specific high-priority sub-resource that is buried deep inside the layout hierarchy, such as a primary web font or a critical hero image. When the engine reads a preload token, it completely ignores its standard scheduling cues. It elevates the preloaded asset to an immediate, top-priority network status, downloading the data in parallel with the main document parsing phase. This ensures the vital resource is resident in memory the absolute millisecond the layout engine executes its box generation pass, cleanly eliminating layout drops and radically accelerating the time to first paint. Now, to synthesize these performance and security optimization recaps into a production-grade document graph, we will execute a complete spoken code walkthrough. We are going to write a highly secure, pre-connected script layout structure. To guarantee absolute syntactical precision, we will strictly deploy the tag pairing technique. We will write the complete opening tag and the complete closing tag first, establishing the closed loop in memory, before we ever step backward to put any configuration attributes. Listen to the workflow instructions and visualize the cursor movements step by step. First, initialize the primary non-visual metadata block using the tag pairing workflow. Type less than, head, greater than, then immediately close the loop by typing less than, / head, greater than. The structural boundary is locked. Drop your cursor back between the head tags, create a new line, and initialize a speculative connection hint. Because a link tag is a structural void element, the tag pairing technique operates inside a single self-closing instruction. Type less than, link, space, / greater than. The void element loop is fully closed. Now, step your cursor backward, moving inside the tag before putting the attributes. We will apply two distinct performance configuration properties. Hit space and declare the network hint operation by typing rel equals, open quote, preconnect, close quote. Second, hit space and declare the secure cross-origin asset boundary by typing the standalone property token, cross-origin. Third, hit space and provide the target address path by typing ref equals, open quote, https:// cdn.domain.com, close quote. The preconnect network hint is fully secured. Create a new line directly below the link element to instantiate our high-priority asset preloader. Execute the void tag pairing sequence, type less than, link, space, / greater than. Step your cursor backward inside the tag before putting the attributes. Layer on 4 distinct performance properties sequentially. Hit space and type rel equals, open quote, preload, close quote. Second, hit space and dictate the explicit asset categorization by typing as equals, open quote, script, close quote. Third, hit space and map the target address by typing ref equals, open quote, https:// cdn.domain.com, /secure-validator.js, close quote. Fourth, hit space and lock down the cross-origin sharing mode by typing cross-origin equals, open quote, anonymous, close quote. The preload optimization loop is perfectly configured. Finally, we will append our actual executable asset tag at the bottom of the metadata stack. Execute the standard non-void tag pairing sequence, type less than, script, greater than, followed immediately by less than, / script, greater than. Step your cursor backward, moving directly inside the opening script tag's boundary before putting any configuration properties. We will layer on 4 distinct security and parsing attributes. First, hit space and type src equals, open quote, https:// cdn.domain.com, /secure-validator.js, close quote. Second, hit space and type cross-origin equals, open quote, anonymous, close quote. Third, hit space and trigger the non-blocking parsing execution mode by typing the standalone token, defer. Fourth, we will forge the cryptographic asset validation check. Hit space and type integrity equals, open quote, SHA-384-, followed by the explicit cryptographic string payload, close quote. By executing this highly disciplined developer workflow, pairing your tags securely to lock your structural loops before putting attributes, you build an impenetrable, ultra-high-speed front-end loading environment. You bypass connection latency blocks, eliminate canvas data leaks, and ensure every single external resource is cryptographically validated by the browser engine before a single pixel is ever painted on the screen. Chapter 12 Capstone Project. Welcome to Chapter 12. Capstone Project, Pure HTML Architecture. This is the absolute final milestone of our technical journey. Throughout this course, we have analyzed the web platform through a strict, purist lens. We have traced how browser engines ingest raw network binary blocks, run them through state-driven tokenizers, and construct complex C++ graphs in system memory. We have deliberately stripped away the layers of presentation and runtime scripts to focus entirely on the raw data model of the web. Now, it is time to synthesize every single semantic landmark, nested table matrix, native interaction layout, and validation constraint we have mastered into a monolithic, production-ready application workspace. But before we type a single angle bracket, we must address how professional, institutional-grade web documents are actually engineered in the real world. Amateurs treat HTML as a messy, temporary scratchpad, a loose pile of generic wrappers thrown together quickly with the expectation that CSS layouts will fix the visual presentation and JavaScript will force the interactive behavior. This approach is a critical engineering flaw that creates brittle, inaccessible code bases that break down the moment a network packet is dropped or an external script fails to compile. An elite systems engineer operates under a completely inverted paradigm. We treat the HTML document graph as the permanent, single source of truth for the entire application. We construct a structural framework so robust, so clean, and so mathematically precise that it stands completely alone as a fully functional, highly accessible utility, while remaining completely prepared to take on massive styling architectures and dynamic script runtimes in the future. To demonstrate this elite asset management workflow, we begin by setting up a future-proof directory matrix. We establish 4 distinct, highly optimized documents within our root workspace: index.html, which handles the primary gateway outline; portfolio.html, which integrates our complex tabular metrics and media frameworks; interact.html, which isolates our scriptless popover and template widgets; and console.html, which drives our comprehensive client-side form validation engine. Crucially, alongside these files, we build a dedicated CSS folder containing an empty styles.css file, and a dedicated JS folder containing an empty app.js file. Right now, these assets remain completely empty. But their presence within our file architecture dictates our entire development strategy. We are deliberately writing our markup with strategic class namespaces, unique identifier keys, and custom data attributes so that we can seamlessly drop in modern utility-style frameworks and asynchronous event observers later, without changing a single line of our core structural tree. In this introductory module, we are going to run a full execution of our master page outline visualizer. We will step back and observe exactly how modern browser engines, automated search crawlers, and assistive operating layers construct computed topological maps of our code trees. We will analyze the gateway overview layout, map the parent-child coordinates of the portfolio data matrix, preview the structural boundaries of our overlay dialog nodes, and trace the algorithmic logic of the system console form controls. You will see exactly how semantic element prioritization guides search bot indexing, how explicit ARIA descriptors secure the accessibility tree, and how native user agent stylesheets provide a pristine layout baseline before a single line of author custom styling is ever applied. Get ready to write code that passes the rigid W3C new HTML checker with a flawless 0-error score. Prepare to build a zero-compromise data graph that delivers perfect layout sanity under plain text conditions, maximizing performance and establishing an impenetrable layer of security. This is where we bridge the gap between simple markup and advanced systems architecture. Let us open up the workspace and visualize the master outlines of our Capstone blueprint. Section 12.1. Welcome to Chapter 12, Section 1. Future-proof directory matrix. Before a single token is ever compiled by a browser engine, the success of an enterprise application is decided by the structural organization of its file architecture on disk. A chaotic, unstructured directory map leads directly to broken asset paths, failed resource prioritization loops, and brittle dependency chains. As systems engineers, we must design our project workspace with the exact same rigor that we apply to our underlying C++ document object model nodes. We must establish a clear blueprint that explicitly isolates our layout definitions from presentation styles and interactive runtimes, while ensuring the entire environment remains perfectly accessible and modular. In this section, we will map out the complete, institutional-grade file structure for our massive Capstone project, analyzing the precise engineering justification for every file, directory, and asset placement within the workspace. Let us first examine the root configuration of our application directory, which we designate as pure HTML Capstone. Sitting directly at the root level of this workspace are our four primary core layout documents: index.html, portfolio.html, interact.html, and console.html. This layout represents a highly optimized, decentralized multi-page document topology. Rather than dumping all code blocks into one massive, unmanageable single-page file that saturates the browser's stream buffer parser, we explicitly partition our application contexts into distinct, isolated structural graphs. The first file, index.html, functions as our primary gateway architecture and semantic outline. It handles our global landmark entry points and baseline document outlines. The second file, portfolio.html, is dedicated exclusively to complex tabular numeric matrices, responsive resolution graphic engines, and multi-codec video ingestion layers. The third file, interact.html, isolates our scriptless interactive disclosure widgets, template objects, and advanced popover top layer configurations. The fourth file, console.html, functions as our comprehensive, industrial-grade data entry form matrix, containing every specialized input token and client-side validation constraint covered in this curriculum. Every single one of these root documents communicates with its neighbors by leveraging strict relative path network traversal keys. We completely avoid absolute URL routing definitions within our internal navigation links. When a user clicks a link to move from the portfolio matrix to the interactive console, the browser engine executes a localized relative path lookup. By mapping our paths relatively, we eliminate reliance on specific server domain routes, keeping the entire document matrix fully functional, portable, and indexable whether it is running on a local offline testing container or deployed to a global content delivery network. This multi-page core is highly specialized, but the true engineering brilliance of this roadmap manifests in how we prepare for the future evolution of our application. Directly alongside our root HTML files, we instantiate two explicit, empty architecture slots, a dedicated CSS directory containing a styles.css file, and a dedicated JS directory containing a app.js file. At this precise point in our development cycle, these files remain entirely blank, containing 0 bytes of custom author code. However, their placement within our production directory matrix is a fundamental requirement of professional progressive enhancement. By defining these dedicated asset pipelines from day one, we establish an explicit separation of concerns baseline. We are deliberately constructing our HTML node tree using a strict, semantic namespacing strategy. Every global layout box, every content section, and every button control is authored with clean, standardized class attributes and unique identifier keys. These classes and IDs act as an immutable application programming interface built straight into the document structure. When the time comes to layer on advanced visual aesthetics, responsive grid alignments, and custom dynamic event observers, you can open up styles.css and app.js to drop in full utility style frameworks and asynchronous script runtimes. Because your HTML core was engineered to be completely extensible, these external assets will attach cleanly to your predefined class and ID hooks instantly, requiring absolute zero refactoring of the underlying semantic document tree. Finally, we isolate our auxiliary operational resources by creating a centralized asset vault, designated as the assets directory. This directory is strictly segregated from our primary layout code to prevent file bloat and optimize server fetch performance. The assets folder houses two vital non-HTML resources required by our media and vector embedding engines, architecturalmap.svg and captionzen.vtt. The first file, architecturalmap.svg, contains our raw, inline Cartesian coordinate vector paths. By storing this graphic structure within the dedicated asset directory rather than hard-coding thousands of loose vector lines directly into our primary gateway document, we keep our index file light, clean, and highly readable for network stream parsers and automated indexing bots. The second file, captionzen.vtt, is a timed web text track file containing explicit chronological subtitle nodes. When our portfolio video engine initializes, it cross-references this VTT asset to stream synchronized text layers directly onto the media frame. Separating the text caption data stream from the heavy raw binary video blocks ensures the browser's background thread can schedule resource delivery with maximum efficiency. By mastering this precise directory matrix, by isolating your content phases across discrete multi-page files, establishing placeholder slots for clean style and script expansion, and anchoring your graphic assets inside an explicit assets vault, you lay out the foundations for a stable, enterprise-ready web application. You eliminate structural drift, protect your document integrity, and guarantee that your application remains perfectly performance-tuned and completely future-proof from the very first byte committed to disk. 12.2 Master Page Outline Visualizer. Welcome to Chapter 12, Section 2. Master Page Outline Visualizer. When an elite software engineer drafts a web architecture, they do not simply type out elements and hope they fall into the right slots. They visualize the precise, mathematical structure that the browser engine constructs in memory long before a single pixel is painted onto a display screen. Every document you author undergoes a rigorous scanning phase where the tree constructor maps tokens straight into a calculated topological layout graph. This visualizer module is designed to pull back the curtain on that invisible graph runtime. We are going to perform a complete verbal audit of the structural outline maps for our first two core application files. By auditing these layouts before dropping in any visual styles or background processing scripts, you can guarantee that your applications possess a pristine, highly accessible data blueprint that is completely prepared to scale. We will observe exactly how the rendering engine categorizes nodes, tracks nested scopes, and establishes clean namespaced hooks that allow modern layout systems and async event frameworks to attach seamlessly later without altering a single branch of your underlying semantic core. 12.2. A primary gateway component, index.html, outline blueprint. Let us first execute a deep structural audit of our primary gateway layout document, index.html. The compilation pass initializes at the absolute root of the document graph, establishing a valid document root running strictly under standards mode instructions. Branching directly off this root index is our metadata containment zone, the document head. The engine processes this zone as a non-visual metadata stage, using it to fire speculative networking links, pre-warm connection sockets, and declare the extensible stylesheet links and application runtime script components that will be layered onto the project later. Once the head metadata locks down, the engine moves directly into the document body, which serves as our active visual viewport stage. To ensure we can attach global theme rule sets and layout geometries smoothly down the line, we decorate this master viewport container with the class name hook set explicitly to site-body. Descending into the active body layer, the first major block the engine processes is our global identity scope, defined natively by the header element. We brand this container with the class hook site-header to prepare it for future visual formatting. Nesting inside this header is a specialized multi-tier heading group, the group element. The group operates as a single, unified semantic anchor for our document outline, holding our primary domain heading inside an H1 element, and our supporting architectural subtitle string cleanly inside an H2 tag. Directly following the global header, the engine encounters our primary document traversal navigation landmark, the NAV tag, mapped explicitly to the unique identifier hook global-nav inside this navigation bar container. The engine parses an unordered list wrapper representing our relative path network traversal matrix. This menu links the browser's tokenization engine directly to the secondary portfolio, interaction, and console pages across the local workspace. Below the navigation bar, the engine instantiates the absolute core of our layout graph, the main element landmark. In strict compliance with browser architecture specifications, exactly one main landmark region is initialized within the entire viewport graph, mapped directly to the tracking ID hook main-content. This landmark acts as the dominant processing arena for the unique data payloads of our gateway page. Stepping inside the main landmark stage, the engine processes a semantic context section block, decorated with the class hook content-section-card. To preserve absolute accessibility health, this section is firmly bound to a mandatory section outline header H2 via an aria labeled by relationship link. Nesting underneath this section is a self-contained content entity, the article tag, branded with the class descriptor dynamic-article. This article container holds our H3 journal entry titles, our textual prose paragraphs, and an algorithmic description list matrix. The description list functions as a native human-machine data bridge, using DL, DT, and DD nodes to cleanly map technical pipeline phases to their explicit definition strings without any formatting code blocks. At the base of the main landmark stage, the engine strikes an explicit landmark scope for query controls, the search element container. This landmark houses our interactive search form control, providing automated indexing bots and script observers a pristine structural anchor to capture user inputs later. Flanking the main framework is our tangential layout context landmark, the aside element, marked with the class identifier sidebar-telemetry. The engine interprets this aside block as auxiliary metadata, using it to hold secondary technical metric items without diluting the keyword weight of the primary main stage. Finally, the master layout grid terminates at the global identity specification block, the footer tag, namespaces cleanly via the class hook site-footer. Nesting safely inside this footer landmark is our contact verification metrics block, the address element. The address node aggregates our author diagnostic cards, telephone links, and email routing addresses, securing a completely valid, highly professional layout graph from the absolute root down to the last child node. 12.2.b Tabular Data and Media Matrix Engine, Portfolio.html, Layout. Now, let us trace the parallel structural architecture of our data engine and media matrix page, Portfolio.html. Just as before, the rendering engine boots up at the document root, verifying standards mode before passing parameters down to the head metadata zone. The head block handles our asset loading pipelines, ensuring that external style sheets and application scripts are properly declared for future injection. The engine then drops down into the main viewport body container, tracking the active visual frame. At the top of the body workspace, the engine maps our synchronized global boilerplate hierarchy. It parses the exact same site header branding block and global navigation menu that we verified in our gateway document, ensuring a perfectly uniform, predictable structural interface across the entire multi-page application matrix. Once the boilerplate components are processed, the engine steps straight into the dominant domain scope of this document, the main element landmark, namespaces uniquely via the class hook portfolio-stage. The first massive structure the engine processes inside this stage is our tabular matrix section, wrapped cleanly in a responsive layout container class named matrix-wrapper. Inside this section lives a deeply structured relational grid, the table element, marked explicitly with the class selector data-table. Let us trace how the engine builds this relational table grid step by step. First, it processes a data table caption node, establishing the official descriptive label for the matrix. Second, it encounters a call group container holding multiple call elements. These column tags act as structural target hooks, allowing the layout engine to map uniform column configurations across the horizontal grid axis. Third, the engine parses the core data header context, the THEOD element, which structures a multi-row matrix of table heading cells mapping component IDs and latency categories. Fourth, it processes the table body context, the body element, which contains our actual data rows built out of cross-referenced header mappings. Fifth, the grid terminates at the table footer context, the TFOOD element, which aggregates our summary calculations and arithmetic means across a unified final row block. Below the complex data grid, the engine enters our media and graphic embedding section. This zone houses three distinct non-textual resource engines. First, it processes a responsive picture element containing multiple source resolution graphs and a core lazy loading image element. This structure allows the layout engine to execute speculative image selections dynamically based on the width metrics of the user's viewport screen. Second, the engine instantiates our multi-codec video ingestion player module, bound explicitly to the unique device identifier system-player. The video player manages external network media files while hosting internal text track elements that stream synchronized subtitle layers onto the display frame. Third, the engine parses a specialized vector and scientific node block, the figure element. Nesting cleanly inside this figure block are two advanced declarative graphic languages, an inline SVG element mapping raw Cartesian line paths, and an inline math element rendering complex performance energy formulas via structured math-ML tokens. The figure block is locked securely in space by a final fig caption anchor element, which attaches a permanent, semantic caption description to the graphic components. Finally, the document path passes cleanly out of the main portfolio stage and settles at the application footer block, completing the structural pipeline pass and locking down a pristine, future-proof media tree ready to convert text streams into layout realities. 12.3 Granular Structural Outline. Welcome to Chapter 12, Section 3. Granular Structural Outline. When executing an enterprise-grade front-end architecture, a professional engineer does not simply throw elements at the page. Every element, attribute, namespace, and configuration pattern must be mapped with geometric precision. The document graph must stand alone as a flawless structural and semantic masterpiece before any style layers or script conditions are introduced. In this module, we will execute a complete deep dive script analysis of the underlying architectural blueprints driving our Capstone project. We will break down our execution matrix into four distinct core domains: future-proof extensibility hooks, pure HTML interaction layouts, tabular metrics and relational grids, and the interactive form matrix with native client-side constraints. We will explore exactly how to establish a bulletproof progressive enhancement baseline, preparing our documents to seamlessly ingest heavy CSS frameworks and complex JavaScript runtimes later without ever compromising the baseline data integrity of the system. 12.3. A future-proof extensibility hooks. Let us first address the absolute baseline of professional document design, engineering for future expansion. Amateurs author HTML as an isolated dead end, leaving their node layouts completely unindexed and unprepared for future styling or behavioral additions. An elite systems engineer treats the HTML tree as an extensible application programming interface, embedding structured namespaces straight into the markup token strings. The first critical layer of this strategy is semantic class namespacing. Throughout our Capstone documents, every primary structural box and layout element is explicitly stamped with clean, structured class attributes like class equals open quote site header close quote, class equals open quote navigation bar close quote, or class equals open quote content section card close quote. These classes do not apply styles natively. Instead, they establish a highly disciplined architectural blueprint. By using explicit namespaces uniformly across all pages, you create a standardized hooks layout. Later, when you drop a production-grade CSS architecture or utility style library into your compiled stylesheets folder, the CSS selectors will attach to these exact predefined hooks instantly. You can rewrite the entire visual layout, change flexbox boundaries, or implement grids across the site from a single global stylesheet, completely eliminating the need to modify a single line of your underlying markup files. The second core layer is our JavaScript DOM hooking strategy. To prepare our semantic document tree for complex runtime interactions down the road, we surgically inject unique identifier keys and custom data parameters into strategic nodes. We utilize distinct ID attributes like ID equals open quote system player close quote or ID equals open quote gateway search phone close quote, coupled with custom metadata tracking chips like data action or data telemetry node. These selectors act as clear, dedicated entry paths for the browser's JavaScript engine wrapper layers. When a developer drops an external application bundle into the scripts directory later, the background execution scripts can instantly locate target nodes using high-speed query selectors, anchoring event listeners and data observers directly to the preconfigured hooks. The data properties allow scripts to track state mutations cleanly, completely bypassing the messy, fragile practice of searching through untagged text boxes or generic layout wrappers. Finally, we secure this entire extensibility architecture using progressive enhancement anchors. By leveraging native HTML5 interactive components, such as the built-in dialog element, the global popover API, and native form validation parameters, we guarantee that the application's core logic remains 100% operational out of the box. If a user opens your page on a highly restrictive network environment where external stylesheets are blocked or large JavaScript bundles drop completely over the wire, the application does not crash. The native user agent layout defaults step in, executing form checks, handling overlay toggles, and maintaining absolute document sanity under plain text conditions. You achieve a resilient, bulletproof baseline that remains fully functional for all users, while standing perfectly primed to scale into a heavy rich media interface the moment styles and scripts initialize. 12.3. Pure HTML interaction layouts. Now, let us examine the engineering behind our scriptless interactive layouts. A primary goal of the modern HTML standard is to offload common interface routines from the JavaScript runtime thread and embed them natively into the browser engine's C++ processing loops. This maximizes rendering efficiency and prevents main thread jank during user interactions. The first interface system we deploy is the native state-driven disclosure accordion, constructed via the details and summary tags. When the tree constructor processes a details node, it instantiates an interactive visibility container managed directly by the user agent stylesheet defaults. The summary tag acts as the permanent, semantic toggle header. When a user interacts with this header, the browser engine internally toggles the Boolean open attribute on the parent details element. The layout engine immediately updates its vector calculations, expanding or collapsing the child content panel instantly. Because this operation runs natively at the platform layer, it requires zero custom script listeners and executes with absolute zero processing lag, providing a perfectly fluid text accordion tree completely free of code overhead. The second system is our advanced modal orchestration layer. To construct complex top-layer overlays without the security and layout bugs of old scripting hacks, we deploy the native HTML dialog element alongside the non-scripted global popover API triggers. The popover API acts as a pure declarative overlay system. By simply adding the popover target attribute to a standard button and mapping it to the ID string of a target container, you establish a direct linkage bridge inside the engine memory. When clicked, the engine intercepts the command and automatically promotes the target popover container straight to the browser's internal top-layer rendering stack. This top-layer promotion is an architectural marvel, It completely rips the container box out of its normal document flow and projects it above all other elements on the screen, completely bypassing any parent container z-index constraints or overflow clipping rules. When you require a strict modal boundary that freezes background document interactions, you deploy the native dialog tag. When initialized, the dialog element spins up an isolated operational scope that handles keyboard focus containment natively, trapping the user's tab index within the modal frame and executing an automatic light dismiss event loop the millisecond the user strikes the physical escape key on their device. The final layer of our interactive structure is web components isolation via template and slot parameters. The template element is a highly unique asset within browser architecture. The tree constructor parses its internal markup tokens but forces them into a completely inert state inside memory. The elements within a template do not generate layout boxes, they do not render visually, and any media or scripts inside them are completely blocked from executing or triggering network downloads. This template acts as a pristine, reusable structural blueprint. By integrating slot tags within this blueprint, you define explicit element projection vectors. When the browser initializes a shadow DOM boundary later, these slots act as predefined drop zones, allowing external data nodes to slide cleanly into specialized positions within the component layout. This guarantees absolute structural isolation, preventing downstream styles or script errors from corrupting the core semantic integrity of your master widget's layout. 12.3.c Tabular metrics and relational grids. Our third architectural domain shifts from interactive layouts to data processing systems, focusing on deeply structured relational grids and tabular numeric matrices. A technical data grid should never be constructed out of loose paragraph blocks or generic div structures. To a rendering engine and an automated accessibility crawler, text tables must be mapped as explicit, multidimensional coordinate arrays where every numbers node is structurally linked to its corresponding data descriptors. We enforce this structural discipline by dividing our table element grids into three explicit functional boundaries: thiad, tbody, and tfoot. The thiad element locks down the core data header matrix, isolating the master title cells that define the columns. The tbody element holds the main computational datasets, containing the sequential rows of data numbers. The tfoot element aggregates summary metrics and arithmetic means across a definitive final row. This rigorous segmentation provides vital optimization metrics to the rendering pipeline. When the browser's layout engine executes its box alignment pass, it reads these explicit section boundaries to manage memory caching efficiently. If a massive data matrix stretches across multiple screen heights, advanced user agent layouts can reference the thiad block to repeat the column headers automatically at the top of every visual viewport window, keeping the data completely readable during scrolling tasks. To ensure this data matrix remains perfectly navigable inside accessibility tree maps, we execute a comprehensive relational cell mapping routine using scope, ID, and headers attribute tokens. Every header cell inside the thiad is stamped with a unique identifying key, alongside an explicit scope attribute set strictly to row or kernel. The scope attribute tells the engine's data parser exactly which direction the header's semantic authority travels across the grid axis. For highly complex grids featuring multi-tiered stacked headers, we use the advanced headers attribute straight inside the individual body data cells. Every single data cell is configured with a headers attribute containing a space-separated array of the exact ID strings matching every header cell above it. This creates a rigid, multi-point coordinate link inside system memory. When an assistive software system walks through a dense grid of performance numbers, it does not just read a blind string like 1.2 milliseconds. The accessibility engine crosses the relationship links instantly, aggregates the corresponding header tokens, and announces the complete contextual payload, target component incremental parser, network latency initial window, 1.2 milliseconds. The data transforms from an unindexed text block into a perfectly mapped relational database layout, preserving complete informational transparency across all software layers. 12.3.d Interactive form matrix and native constraints. Our final architectural milestone focuses on the interactive form matrix, the primary engine driving user data entry and server transmission, engineered completely via pure HTML native constraints. A form should never rely on heavy external script libraries to check strings or block submissions. The document syntax itself possesses all the necessary computational tools to validate data payloads right at the entry boundary. The pipeline initializes at the form element core, configured with absolute parameter precision. We declare the precise action target URI determining where the data travels, bind the secure transport protocol via the method attribute set to post, and lock down the data format using the type attribute set explicitly to multipart/form data. This encoding type is critical. It tells the browser's network stack to skip basic URL text streaming and package the input nodes as a highly secure, multi-segmented binary payload block, preparing the form to safely transport complex files and extended data manifests across the wire. To manage the massive array of inputs required by our control console, we execute strict structural segmenting using fieldset containers coupled with legend captions. The fieldset element is not a decorative border box, it is a vital functional manager. By grouping related inputs, such as operator identity metrics or technical hardware parameters, inside a fieldset container, you isolate that block within the document graph. The fieldset possess a powerful native capability. If you apply the standalone disabled attribute token to a parent fieldset, the browser engine instantly intercepts the command and programmatically disables every single child input control nesting inside it, blocking focus tracks and preventing data transmission across that entire subtier instantly. The legend element acts as the mandatory structural caption, providing an absolute semantic identifier for the grouped controls inside the accessibility tree. Nesting inside these fieldsets is our core input matrix, utilizing modern analytical input types and mobile layout hardware hints. We completely move past generic text fields and deploy specialized types including email, URL, tel, date, and color. When a mobile device rendering engine processes these specialized input tokens, it reads them as hardware layout instructions. Instead of showing a standard alphabetic keyboard that forces the user to manually switch layouts to type symbols, the input type forces the mobile operating system to instantly adjust its visual keyboard interface. An input type equals email automatically exposes the @ sign and .com buttons, type equals tel displays a clean numeric dial pad, and type equals URL injects a / and .local shortcut key. We optimize this user interaction further by layering on advanced keyboard behaviors using input mode, enter key hint, and autocomplete parameters, alongside the data list component which injects a native, scriptless autocomplete suggestion box straight into the viewport focus stream. Finally, we enforce strict client-side validation logic by embedding native constraints directly into the input syntax. We deploy an unyielding array of structural validation checks using required tokens, min-length and max-length boundary limits, and explicit regular expression checking via the pattern attribute. When a user triggers a form submission button, the browser engine pauses the execution loop and runs a complete native validation scan across all input nodes. If an operator types an invalid signature string that breaks the pattern constraints, the user agent layout engine automatically aborts the transmission sequence. It blocks the form submission, targets the broken node, fires a native localized warning overlay straight into the active viewport, and shifts the system focus directly to the invalid element so the user can fix the string immediately. We track the results of these data interactions by connecting the inputs to native progress bars, measurement gauges, and declarative output arithmetic displays. By setting an output tag with an explicit for attribute referencing the ID strings of your range and selector inputs, the document establishes a live value tracking relationship. The output element stands completely prepared to receive and display real-time arithmetic calculations, providing a highly responsive, structurally sound data dashboard. By organizing your entire form workspace around these native validation networks, you completely eliminate script vulnerabilities, optimize processing speed, and deliver a rock-solid data transmission matrix engineered for complete reliability across the global web. Section 12.4. Complete production code files. Welcome to Chapter 12, Section 4. Complete production code files. We have arrived at the final technical execution phase of our curriculum. Up to this point, we have mapped out folder layouts on disk and audited visual outlines in the abstract. Now, it is time to build the actual functional codebase. This section is a massive, step-by-step spoken live coding script divided into 4 distinct production walkthroughs: 12.4. for our gateway architecture, 12.4.b for our media matrix, 12.4.c for our interactive widget templates, and 12.4.d for our comprehensive data validation console. As elite developers, we will not construct this project using reckless formatting choices. We will strictly deploy the tag pairing technique across every single milestone. Because we have already mastered how to form individual elements, we will completely discard instructions like less than or greater than. Instead, we will directly declare our structural boundaries by instantly making the complete opening and closing tag pairs to lock the loop securely inside memory first. Only then will we step our cursor backward to inject namespaces, class hooks, and configurations. This mechanical workflow completely eliminates structural drift, prevents unclosed tag bugs, and ensures our document graph seamlessly ingests heavy styles and modern scripts later without breaking a single semantic boundary. Visualize your editor window, position your fingers on the home row, and let us execute these production graphs. 12.4. A primary gateway architecture script, index.html. Let us boot up our editor workspace and construct our root gateway, index.html. First, initialize the document type declaration string by typing !doctype_html inside an initial declaration bracket. Now, instantly apply the tag pairing technique to lock down the master root document container by creating an HTML tag pair. Step inside the opening HTML tag boundary and declare the language token set to English. Drop down between the master HTML wrappers and initialize the non-visual metadata zone by creating a head tag pair. Step inside this head segment to establish our document properties within the critical 1024-byte buffer zone. Run the self-closing void tag technique to insert a metacharset tag set to UTF-8. Next, instantiate a responsive viewport configuration meta tag, followed by a search description meta tag declaring our production gateway summary. Now, create a title tag pair, move your cursor between the tags, and insert the text string, Architectural Ingestion Platform, Primary Gateway. To establish our future-proof extensibility layouts, create a self-closing link tag pair mapping our future stylesheet asset path to css/styles.css, followed by a script tag pair pointing its source to js/app.js, coupled with a standalone defer token. The metadata zone is locked. Move your cursor below the closing head boundary and initialize our visual viewport stage by creating a body tag pair. Step backward into the opening body tag and decorate it with our extensible global class hooks, site body, container root, and visual viewport stage. Nesting inside the body loop, let us construct the global identity landmark by creating a header tag pair, namespaced with the class site header. Inside the header wrappers, instantiate a clean heading group by creating an group tag pair. Step inside the group block and apply tag pairing for the multi-level headers. Create an H1 tag pair containing the text payload, pure HTML architecture system, and an H2 tag pair containing the subtitle string, curriculum synthesizer, and document graph gateway. Below the group, append our revision auditing controls by creating a paragraph tag pair. Inside it, pair a data element tag set to a value of 2026.1.0, a time element tag pair set to our explicit timestamp string, and a structural insertion ins tag pair carrying the audit status class badge and the display text, approved for public release. Directly underneath the global header block, initialize the structural navigation bar landmark by creating a NAV tag pair. Step backward into the opening NAV tag and secure it with its distinct target hooks, the identifier global NAV, the class navigation bar container, and an ARIA label set to global primary navigation. Move down inside the NAV landmark and create an unordered list all tag pair namespaces as NAV menu list wrapper. Inside the list container, we will place 4 distinct relative path network navigation links. For each menu item, create a list item li tag pair enclosing an anchor tag pair. Move inside the first anchor tag pair and attach the NAV menu link class, mapping the ref link to index.html and setting ARIA current to page. Repeat this exact tag pairing loop for the remaining 3 list items, mapping the relative paths cleanly to portfolio.html, interact.html, and console.html. Below the navigation landmark, initialize the absolute processing core of our document graph by creating a main tag pair. Step backward into the opening main tag and anchor it securely for future styling grids and dynamic scripts by assigning the identifier main content and the class layout main stage. Nesting safely inside the main stage wrapper, let us construct a semantic section block by creating a section tag pair, namespaced with the class content section card and bound to its heading anchor via ARIA labeled by. Inside the section block, drop in the secondary layout heading anchor by creating an H2 tag pair hooked to the identifier curriculum core heading, containing the text string, core architectural foundations. Directly below the H2 heading, initialize a self-contained content entity by creating an article tag pair, decorated with the class journal entry container and custom data telemetry properties. Move inside the article block and instantiate the journal title heading by creating an H3 tag pair hooked to the identifier article ingestion mechanics, containing the text, ingestion mechanics, from bytes to pixels. Below the title, drop in the primary textual data block by creating a paragraph tag pair. Inside the paragraph, wrap a definition anchor by creating a DFN tag pair namespaces as technical glossary term, containing the text, deterministic multi-phase rendering pipeline. Complete the prose paragraph string, integrating an abbreviation ABBR tag pair carrying a title attribute set to Web Hypertext Application Technology Working Group and the internal text, WHATWG. Create a second paragraph block underneath using strict tag pairing to verify internationalization processing controls, decorating it with the textual alert callout class. Inside the paragraph, create a bidirectional isolation D tag pair containing the term HTML5 engine, followed by a bidirectional text direction override BDO tag pair configured with a strict right to left layout direction and the text string, document matrix terminal. Below the callout text, establish our native data definition array by creating a description list DL tag pair namespaced as pipeline definition list. Inside the list, systematically create 3 data term DT tag pairs styled as pipeline term node, and 3 data definition DD tag pairs styled as pipeline description node. Populate these clean structural tags with the explicit text descriptions for the conversion, tokenization, and tree construction phases. At the base of the main landmark framework, create a second section to handle our local index traversal controls by creating a section tag pair namespaced as search landmark block. Inside, pair an H2 heading element anchored with the identifier search landmark heading, containing the string, local index traversal. Directly below the heading, instantiate a dedicated query landmark by creating a search tag pair styled as search landmark wrapper. Move down inside the search landmark and create a form tag pair, configured with the class search form element, an action pointing to index.html, a get transmission method, and a unique form identifier hook. Inside the form block, create a control label tag pair styled as form input field label, linked cleanly via a for attribute to the identifier gateway search query. Below the label, insert a search input element using the self-closing void tag technique, applying the input field search class, a type attribute set to search, and specialized mobile keyboard parameters including enter key hint set to search and input mode set to search. Beside the input field, create a submission button control by making a button tag pair styled as action btn primary, carrying a type attribute set explicitly to submit and the display text, execute search. Flanking our primary main framework, initialize our tangential layout context landmark by creating an aside tag pair configured with the identifier sidebar telemetry and the class layout sidebar stage. Move inside the aside landmark, create an H2 heading tag anchored to the identifier aside metadata heading, and give it the text, engine statistics. Below the heading, create a wrapping section container tag pair styled as sidebar widget container, nesting a tracking subtitle using a paired H3 element containing the string, structural metrics. Directly below the H3, create an unordered list all tag pair namespaced as sidebar data list. Inside the list, use strict tag pairing to assemble 3 distinct metric items by creating list item li tag pair styled as sidebar data item. Inside the first list item, use a paired span element styled as a success status tag to wrap the text, 100% native. For the second and third items, create span elements styled as neutral status tags to cleanly display the 0-byte style footprint and 0-millisecond script runtime evaluations. Finally, move down to the base of the document body loop and instantiate our global identity specification block by creating a footer tag pair, namespaces cleanly via the class application footer container. Move inside the footer and create a copyright paragraph by making a paragraph tag pair styled as legal copyright notice, populating it with the tracking notice string. Directly below the copyright notice, initialize our verified contact metrics block by creating a paired address element styled as author address card. Move down inside the address card, insert the plaintext diagnostic lines, and use the tag pairing technique to cleanly build your email and telephone anchor links, applying the address link anchor class to ensure both structural nodes can be targeted cleanly by external layouts later. The primary gateway layout document graph is fully assembled and entirely closed inside memory. 12.4.b Tabular data and media matrix script, portfolio.html. Let us move to the second core file in our multi-page directory matrix, portfolio.html, which houses our data engines and responsive media arrays. First, construct the header metadata baseline by typing the standard document declaration string, followed instantly by creating an HTML tag pair configured with the language token set to English. Drop inside the HTML block and create a head tag pair container. Populate the head zone within the critical buffer limit by deploying the standard character encoding, viewport settings, and search description metadata layers using the void tag technique. Directly below the metadata, embed the future-proof link hooks by creating a self-closing link tag pair mapping our future stylesheet asset path to css/styles.css, and a script tag pair pointing its source to js/app.js, coupled with a standalone defer token. Now, move down below the head block and execute the tag pairing workflow for our main active visual viewport body wrapper by creating a body tag pair. Step backward into the opening body tag and apply its global layout class names, site body, container root, and visual viewport stage. Nesting inside the visual body loop, we must instantiate our synchronized global boilerplate components to guarantee structural uniformity across our system endpoints. First, replicate the identical site header block by creating a header tag pair namespaced with the class site header branding block. Inside the header, create a group element nesting an H1 tag containing the data topology's title string, alongside an H2 tag containing the chapter table compendium matrix subtitle. Directly below the header, replicate the global primary navigation bar landmark by creating a NAV tag pair hooked to the identifier global NAV and the class navigation bar container. Inside the NAV landmark, create an unordered list all tag pair containing 4 distinct list items and anchor elements assembled via the strict tag pairing workflow, ensuring the second anchor link is marked explicitly as the active portfolio page by assigning the active class modifier, and ref pointing to portfolio.html, and setting aria current to page. With the global navigation boilerplate secured, initialize the dominant domain scope for our media page by creating a main tag pair, Stepped backward to assign the identifier main content and the portfolio view access class hooks. Nesting inside the main stage wrapper, our first core milestone is the assembly of our relational tabular numeric matrix. First, create a section tag pair namespaces as tabular grid responsive container. Inside the section block, drop in the secondary layout heading anchor by creating an H2 tag pair hooked to the identifier tabular matrix heading, containing the text, complex component performance analysis matrix. Directly below the heading anchor, initialize our multidimensional coordinate relational grid by creating a table tag pair. Step backward into the opening table tag and hook it securely for future border configurations by assigning the class datatable analytical matrix grid, the identifier performance analysis matrix, and a native border property set to 1. Move down inside the table grid block and instantiate the table description descriptor node by creating a caption tag pair styled as datatable caption, containing the data descriptor string, rigid metric correlation array. Below the caption node, establish our horizontal layout target hooks by creating a call group container tag pair namespaces as datatable call group. Inside the call group, deploy 4 distinct column tags using the void tag technique. Step back inside each call element to allocate structural classes and target IDs, style the first column as identifier target, the second as metadata target, the third as a latency target spanning 2 columns, and the final column node as an efficiency target. Now, assemble the core data header matrix context by creating a thiad tag pair namespaced as datatable thiad. Inside the thiad container, we will stack 2 clean table header rows using strict tag pairing, making a TR tag pair for each row styled as datatable header row. Inside the first header row, create 4 distinct TH heading cells using the tag pairing technique. Step back into each TH element to allocate scope, row spanning, and identification coordinates, style the first cell as a sortable node anchored to the identifier TH comp ID with a row span of 2, containing the text target component identifier, style the second cell as a sortable node anchored to TH class cat with a row span of 2, containing structural content category, style the third cell as a grouped node anchored to TH network metrics with a call span of 2, containing network latency benchmarks, and style the final cell in the first row as a sortable node anchored to TH compute rating with a row span of 2, containing GPU efficiency index. Move down and pair the second header row block, inside which you will create 2 subtier TH heading cells using tag pairing, configuring the first subcell as a subnode anchored to the identifier TH lat initial and linked to header string TH network metrics, and the second subcell anchored to TH lat complete linked to the same header network group. The data header matrix context is completely locked in memory. Below the thiad, construct our main computational dataset container by creating a tbody tag pair styled as datatable tbody. Inside the tbody block, we will precisely assemble 3 distinct data rows by creating TR tag pairs namespaced as datatable data row, decorating the second row with an alternate row modifier class to ensure it stands ready for clean visual striping variations later. Inside each row container, the first cell must be a row header anchor to preserve accessibility navigation tracks. Create a TH tag pair styled as cell row header, carrying a row scope attribute, a distinct row identifier like row parser, and linked to header string TH comp ID. Populate it with the data identifier text string. Following the row header, deploy 4 distinct data cells sequentially by creating TD tag pairs using strict tag pairing. Step back into each opening TD tag to declare its styling classes and relational multipoint coordinate header string. Assign the class cellTD text and map headers to row parser and TH class cat for textual values, and assign cellTD numeric mapping headers to the corresponding network benchmarks for numeric cells. Statically decorating high-performance cells with a positive metrics class and low-performance index cells with a warning metrics class to allow easy conditional style targeting. Later, repeat this rigorous cell configuration layout uniformly across the second row for the speculative preload scanner and the third row for the C++ binding bridge wrapper. The table grid terminates at the table summary evaluation container by creating a tfoot tag pair namespaced as data table tfoot. Inside, pair a single row block by creating a tr tag pair styled as data table summary row. Inside this row, create a summary row header cell by making a th tag pair styled as cell summary header, carrying a row scope attribute, the identifier row summary, and a callspan property set to 2, containing the text system arithmetic compound mean. Beside the row header, deploy 3 final numeric summary cells by making td tag pairs styled as celtd numeric, linking them to their respective column tracks using the headers attribute, and populating them with the computed system baseline averages. The data table grid engine is completely closed and finalized. Below the performance grid, drop down and construct our high-velocity media embedding section by creating a section tag pair styled as content section card media integration block, anchored to the identifier media engine heading via aria labeled by. Nest a section header h2 containing the framework title string anchored to the identifier media engine heading. Inside this media zone, we will deploy 3 independent resource engine cards using strict tag pairing by creating article containers styled as media display card, grouping each block under an explicit h3 title heading. Inside the first media card, initialize our responsive picture layout tracker by creating a picture tag pair styled as picture media frame. Inside the picture container, insert the capability source line using the void tag technique, configuring the resolution calculation maps via circset and sizes attributes and setting the image type to image/wep. Directly below the source line, deploy the primary visual fallback node by creating a self-closing img tag pair, stepped backward to apply the performance optimization commands, assign the class media image element interactive hotspot target, the source path assets/architecture default.png, the descriptive alt text, hard-coded width and height dimensions, lazy loading controls, async decoding triggers, a low fetch priority, and link it to the hotspot coordinate tracking map via usemap. Directly below the completed picture frame, construct the localized image hotspot coordinates mapping array by creating a map tag pair assigning the name and identifier to pipeline hotspots. Inside the map, run the void tag loop to plot 2 distinct coordinate spaces by making self-closing area tags, configuring the shape, coordinate pixel sets, and target ref path anchors pointing to our document text sections. Inside the second media display card, instantiate our multi-codec video player subsystem by creating a video tag pair, stepped backward to allocate the future behavioral execution links, the identifier system player, the class HTML5 video player, native control triggers, visual width and height boundaries, a poster frame asset path, metadata preloading controls, and an inline processing directive. Move down inside the video player block and deploy 2 streaming source nodes using the self-closing void tag method, mapping the path vectors to our local MP4 and WEBM assets. Below the source elements, pair 2 tracking nodes to handle localized subtitles and chapters by creating self-closing track tags, configuring the first track tag for kind subtitles pointing to assets/captionsn.vtt, and the second track element for kind chapters pointing to your local milestones track file. Inside the final media integration block, assemble our scientific equations matrix and Cartesian path lines. First, pair an isolated sandbox frame container by creating an iframe tag pair locked down with the class sandbox frame viewport, an inline document source directive, a strict same origin sandbox policy, cross-origin isolated clearances, width and height values, and lazy execution boundaries. Directly below the iframe sandbox, pair a vector figure block container by creating a figure tag pair namespaced as vector figure wrapper. Move inside the figure block and pair the vector graphic canvas element by creating an SVG tag pair, stepped backward to hook it securely for future styling sheets adjustments, assign the class SVG inline canvas, geometric canvas dimensions, a Cartesian viewbox layout grid, the standard XML namespace, and a clear descriptive ARIA label. Inside the SVG container, run the tag pairing workflow to draw the vector lines and circular tracking points. Create a line tag pair styled as SVG line, passing the starting and ending Cartesian coordinates, a solid stroke color, and a pixel stroke width, and create two circle tag pairs styled as SVG node start and end modifiers, plotting the center point coordinates to establish clean visual anchors across the line axis. Directly below the SVG graphic canvas, instantiate the pure declarative scientific calculation formulas block by creating a math tag pair container. Stepped backward to assign the class MathML equation element, the authoritative MathML namespace, and a block display format. Move inside the MathML tree block and run the tag pairing sequence to build the layout rows and exponential powers. Create an row container, inside which you will systematically create your variables, operator indicators, and subscript tokens by making me, mo, and subtag pairs, statically binding the class names MathMLvar, MathMLop, and MathMLNumber to the internal mathematical elements to ensure you can apply advanced visual typography rules later from your central stylesheet file. Lock the base of the figure block by creating a fig caption anchor element containing the scientific figure caption reference text string. The main portfolio stage view is completely built, fully sealed, and perfectly extensible. 12.4.c Reusable components and interactive core script, interact.html. Let us now move to the third core file in our decentralized workspace directory matrix, interact.html, which handles our scriptless interface disclosures and top-layer popover panels. First, construct the header metadata baseline by typing the standard document declaration string, followed instantly by creating an HTML tag pair configured with the language token set to English. Drop inside the HTML block and create a head tag pair container, populating the head zone within the critical buffer limit by deploying the standard character encoding, viewport settings, and search description metadata layers using the void tag technique. Directly below the metadata, embed the future-proof link hooks by creating a self-closing link tag pair mapping our future stylesheet asset path to css/styles.css, and a script tag pair pointing its source to js/app.js, coupled with a standalone defer token. Before you drop down into the main body loop, we must instantiate our reusable component blueprints right at the top of the graph layer by creating an inert template container tag pair, stepped backward to bind it to the tracking device identifier hook telemetry node row. Move down inside the inert template block and pair a structural table data row by creating a tr tag pair styled as custom component row. Inside the row container, we will place two distinct element projection vectors by creating cell td tag pairs styled as custom component cell ID and cell status. Inside the first cell, run the tag pairing technique to establish an extraction hook slot by creating a slot tag pair, stepped backward to assign the reference identifier name set to node ID, and input the default baseline fallback text inside. Repeat this tag pairing step inside the second cell to configure your node status slot hook. The reusable component blueprint is safely compiled in memory in an inert state. Now, move down below the template block and execute the tag pairing workflow for our main active visual viewport body wrapper by creating a body tag pair, stepped backward to apply its global layout class names, site body, container root, and visual viewport stage. Nesting inside the visual body loop, we must instantiate our synchronized global boilerplate components to guarantee structural uniformity across our system endpoints. Replicate the identical site header block by creating a header tag pair namespaced with the class site header branding block. Inside the header, create a group element nesting an h1 tag containing the interactive framework title string, alongside an h2 tag containing the chapter subtitles interaction controls. Directly below the header, replicate the global primary navigation bar landmark by creating a NAV tag pair hooked to the identifier global NAV and the class navigation bar container. Inside the NAV landmark, create an unordered list.ul tag pair containing 4 distinct list items and anchor elements assembled via the strict tag pairing workflow, ensuring the third anchor link is marked explicitly as the active interaction page by assigning the active class modifier, and ref pointing to interact.html, and setting aria current to page. With the global navigation boilerplate secured, initialize the dominant domain scope for our interaction page by creating a main tag pair, stepped backward to assign the identifier main content and the component stage wrapper class hooks. Nesting inside the main stage wrapper, our first core milestone is the assembly of our native disclosure accordion trees. Create a section tag pair namespaces as content section card accordion flow block, bound to its heading anchor via aria labeled by. Inside the section block, drop in the secondary layout heading anchor by creating an H2 tag pair hooked to the identifier disclosure widget's heading, containing the text, advanced native disclosure components. Directly below the heading anchor, initialize our primary state-driven disclosure interface by creating a details tag pair container, stepped backward to apply the user agent visibility toggle command, assign the class accordion disclosure wrapper and the standalone layout token, open, to ensure this block initializes in an expanded state inside the active viewport. Move down inside the details container and pair the summary header toggle node by creating a summary tag pair styled as accordion summary bar, populating it with the header trigger text, system architectural level 1 parameters. Directly below the summary header, pair a structural content wrapper by creating a div tag pair styled as accordion details panel. Move inside this details panel and drop in a descriptive prose paragraph built via tag pairing. Below the paragraph, nest a secondary subtier accordion tree block by creating a nested details element container, styled as an accordion disclosure node with a nested modifier class. Inside the nested container, pair an accordion summary trigger bar containing the subtitle string text, subtier state metrics index. Below the nested summary, pair an internal content block div namespaced as accordion details panel. Inside this panel, use strict tag pairing to deploy an unordered list element class styled as nested data list, hosting multiple list items where status text tags are wrapped cleanly inside a paired span element namespaces as text status tag, protecting baseline document layouts. Create a second, independent accordion disclosure card below the master block to track secondary debugging tracks by making a details tag pair container styled as accordion disclosure wrapper, inside which you will pair a summary trigger bar element containing the level 2 debug vectors text, followed by the content wrapper div panel containing the text lines detailing the locked telemetry paths. Below the accordion section, drop down and construct our declarative modal overlays and top layer configurations by creating a section tag pair styled as content section card overlays flow block, anchored to the identifier overlay controls heading via aria labeled by. Nest a section header H2 containing the overlays title string anchored to the identifier overlay controls heading. Inside this overlay section, we will deploy two independent interactive interface cards using strict tag pairing by creating article containers styled as overlay interface card, grouping each block under an explicit H3 title heading. Inside the first interface card, initialize our top layer popover overlay engine system. Below the descriptive text lines, deploy the popover initialization buttons using the tag pairing technique. Create a button control element styled as a popover trigger button, stepped backward to declare the pure declarative linkage parameters, a button input type, popover target set explicitly to telemetry popover panel, and popover target action set to show, populating it with the trigger text. Initialize telemetry overlay panel. Beside the trigger button, pair a second button control to handle manual dismiss tasks, styled as a popover dismiss button with a popover target action set explicitly to hide, populating it with the dismiss text, force dismiss overlay. Directly below the control buttons, construct the isolated top layer target overlay container box by creating a div tag pair, stepped backward inside the opening tag to allocate the engine popover commands and security observer parameters, assign the identifier telemetry popover panel, the class popover panel root, a popover value set to auto, an explicit tooltip role, a clear accessible aria label, and a custom data telemetry layer attribute set to active node. Move down inside this popover panel wrapper and insert a paired H4 heading tag containing the string diagnostic title, followed by a paired paragraph element containing the technical panel descriptions detailing the automated hardware light dismiss event loops. Inside the second interface card, initialize our native layout modal dialog component. Below the descriptive text lines, deploy the modal invocation trigger button by creating a button tag pair styled as a modal trigger button, carrying a popovertarget set to secure modal dialog and a popovertar detection set to show, populating it with the trigger text, expose structural warning modal. Directly below the trigger button, construct the native structural modal dialog container element by creating a dialog tag pair, stepped backward into the opening tag to apply the secure workflow boundary hooks, assign the identifier secure modal dialog, the class dialog frame application modal container, and link it to the heading anchor via aria labeled by. Move down inside the dialog element loop and pair an internal alignment wrapper div styled as dialog body layout. Inside this alignment box, pair an h4 dialog alert title heading tag by making an h4 tag pair styled as dialog alert title, anchored to the identifier dialog title string, giving it the alert text, terminal security alert constraint. Below the h4 heading, pair a modal prose paragraph container containing the alert details warning developers about runtime changes, and lock the base of the dialog container loop by pairing a manual dismiss button control styled as a modal dismiss button carrying a popovertarget set to secure modal dialog and a popovertar detection set explicitly to hide, providing the button display text, acknowledge and safe reset container. The interactive control framework core document graph is completely built, fully closed, and perfectly optimized. 12.4.d Comprehensive Data Validation Console Script, console.html. Let us now move to the final core layout file in our workspace directory matrix, console.html, which handles our algorithmic form engine and structural client-side validation networks. First, construct the header metadata baseline by typing the standard document declaration string, followed instantly by creating an HTML tag pair configured with the language token set to English. Drop inside the HTML block and create a head tag pair container, populating the head zone within the critical buffer limit by deploying the standard character encoding, viewport settings, and search description metadata layers using the void tag technique. Directly below the metadata, embed the future-proof link hooks by creating a self-closing link tag pair mapping our future stylesheet asset path to css/styles.css, and a script tag pair pointing its source to js/app.js, coupled with a standalone defer token. Now, move down below the head block and execute the tag pairing workflow for our main active visual viewport body wrapper by creating a body tag pair, stepped backward to apply its global layout class names, site body, container root, and visual viewport stage. Nesting inside the visual body loop, we must instantiate our synchronized global boilerplate components to guarantee structural uniformity across our system endpoints. Replicate the identical site header block by creating a header tag pair namespaced with the class site header branding block. Inside the header, create a group element nesting an h1 tag containing the comprehensive console title string, alongside an h2 tag containing the chapter form validation constraints subtitle. Directly below the header, replicate the global primary navigation bar landmark by creating a nav tag pair hooked to the identifier global nav and the class navigation bar container. Inside the nav landmark, create an unordered list_ul tag pair containing 4 distinct list items and anchor elements assembled via the strict tag pairing workflow, ensuring the fourth anchor link is marked explicitly as the active console page by assigning the active class modifier, and ref pointing to console.html, and setting aria current to page. With the global navigation boilerplate secured, initialize the dominant domain scope for our form console page by creating a main tag pair, stepped backward to assign the identifier main content and the console form stage class hooks. Nesting inside the main stage wrapper, our main core milestone is the assembly of our algorithmic input system. Create a section tag pair namespaces as content section card form workspace wrapper, bound to its heading anchor via aria labeled by. Inside the section block, drop in the secondary layout heading anchor by creating an h2 tag pair hooked to the identifier form engine heading, containing the text, system registration, and calculation array engine. Directly below the heading anchor, initialize our data handling configuration network by creating a form tag pair, stepped backward into the opening tag to hook it securely for precise server routing, assign the class form core element, an action target pointing to console.html, a secure post-transmission method, a multi-part form data encoding layout, global autocomplete tracks enabled, and bind it to the unique device identifier core telemetry form. Move inside the form element block and segment your control inputs systematically by creating 3 independent fieldset containers using strict tag pairing, assigning the class form fieldset along with a distinct identification key tracking the operational parameter tier, anchoring the top of every fieldset loop by creating a legend container tag pair styled as form legend to hold the structural matrix captions. Inside the first fieldset identity block, initialize 2 distinct form control rows by creating a div layout element styled as formGroupRow. Inside the first row, construct our alphanumeric verification field by creating a form label control styled as formLabel, linked via a for attribute to the identifier input operator name, populating it with the text operator canonical signature string. Below the label, deploy the text validation box using the self-closing void tag technique. Stepped backward inside the input tag to layer on the strict constraints, assign the form input text class, a text input mode type, the target identifier input operator name, a matching network name field, an explicit required token, minimum and maximum character length safety boundaries, a strict alphanumeric regular expression pattern string, a placeholder example value, a username autocomplete hint, and link it via aria-described to the helper text paragraph below. Create the helper text paragraph directly underneath, anchored explicitly via its target identifier to hold the signature constraint instructions. Replicate this exact label and input tag pairing row layout for the second control row to deploy your secret passphrase token control, configuring the input box type explicitly for a password input format. Inside the second fieldset hardware block, deploy 6 independent form control rows built via strict tag pairing to configure specialized analytical input types and device keyboards hardware hints, replicating the exact label and input tag pairing loops sequentially for every row. Configure the first control row to display an email input box by setting the input type to email, mapping the hardware layout input mode to email, attaching a next enter key hint, and providing a clean local node placeholder string. Configure the second row to display a target URL vector field by setting the type to URL, input mode to URL, and matching the navigation flow hints. Configure the third row to display a telephone dial pad hotwire input by setting the type to tel, input mode to tel, and attaching a strict numerical digit verification pattern matching our structural console codes. Configure the fourth control row to hold your chronological temporal calibration controls by creating 2 separate self-closing input nodes sequentially, setting the input type to date for the first field and time for the second field. Configure the fifth row to display your Visual Workspace tint selector by setting the input type to color and anchoring a default green hexadecimal color value. Configure the final row in this hardware field set block to inject a scriptless autocomplete suggestion box into the viewport focus stream by making a standard input text box, attaching the list autocomplete suggestion tracking bridge pointing to the identifier suggested subsystems, and creating a paired data list container element directly below anchored to that exact matching identifier, inside which you will run the void tag pairing loop to deploy 3 separate option tags containing our predefined core tokenizer, DOM builder, and GPU compositor baseline tokens. Inside the final field set arithmetic status block, deploy 7 highly complex data payload and metric indicators controls assembled via the strict tag pairing technique. First, construct a hierarchical selection list structure by creating a select field container element styled as formSelect, anchored to the identifier select processing tier. Inside the select block, group your options matrices by creating 2 separate opt group elements carrying standard cluster and premium hardware allocation group labels, inside which you will use tag pairing to deploy your choice list option cells using paired option elements containing target compute value tags, marking the standard core tier as selected by default. Second, construct a heavy data text box block layout by creating a multi-line text field container element using a paired text area tag, stepped backward inside the tag to layer on the hard character constraint wrap properties, assign the form text area class, a target identifier, a matching network name, a required token, strict minimum and maximum character payload limits, a hard text wrapping constraint, and a descriptive logging placeholder text string. Third, construct a multi-option checkbox Boolean array grid matrix by creating a list container element styled as form checkbox list, hosting multiple list items where checkbox inputs and labels are assembled via strict tag pairing, setting the input type to checkbox and marking the core safeguard configurations as checked and required by default to secure the cross-origin sharing modes. Fourth, construct a binary radio mutually exclusive selection list by creating a radio group cluster wrapper container div, hosting two choice rows where radio controls are paired via a radio input type and a unified network stream name, marking the incremental buffer stream rendering pipeline mode as checked by default to align with the core rendering engine baselines. Fifth, construct a manual throttle target control element by creating a range volume input node using the void tag technique, assigning the form range class, a range input type, a target load identifier, and custom data attributes mapping the range value to the live output displays below to establish a clear tracking vector for future dynamic script observers. Sixth, construct our native asynchronous progress indicator bar and thermal gauges by creating a progress tracking indicator element styled as a progress bar with a maximum calculation ceiling of 100 and a current value of 75, followed by a measurement gauge indicator element using a paired meter tag, configuring the minimum, maximum, low, high, and optimum scale milestones to cleanly register system thermal indices out of the box. Seventh, construct our pure declarative output arithmetic dashboard display by creating a calculation display panel row wrapper div enclosing a live output calculation element container, stepped backward into the opening output tag to define the relational data connections, assign the UI output monitor class, a distinct output display identifier, a matching calculation network name, and forge the explicit data link tracking bridges via a for attribute containing a space-separated array of the exact identifier keys matching your manual load range inputs and select processing fields, populating the internal node with the initial static baseline calculation token string. Lock the absolute base of the form framework core by creating a final button actions control row div container element styled as form button actions row, inside which you will deploy 3 independent action button controls assembled via the strict tag pairing technique. Configure the first button control for a form reset type styled as a form action reset button to cleanly purge workspace memory nodes. Configure the second button control for a form submit type styled as a form action submit button to transmit data matrices across network wires. Configure the final button control to execute a complete validation bypass override and network reroute by creating a button tag pair styled as a form action validation bypass button, setting the input type explicitly to submit, overriding targets to index.html via a form action attribute, shifting routing protocols via form method set to get, attaching the standalone formNoValidate constraint property token to neutralize local browser engine checks, and anchoring the node securely to the identifier button bypass validation. Our complete, 4-page Capstone Project document graph matrix is entirely written out, perfectly paired, and 100% closed inside memory, standing perfectly primed to run as an ultra-high-speed, secure, and semantic digital ecosystem. Section 12.5. Quality Instrumentation, Extensibility, and Validation. Welcome to Chapter 12, Section 5. Quality Instrumentation, Extensibility, and Validation. We have officially constructed the complete, production-grade source files for our decentralized 4-page application workspace. Every structural tag loop has been securely closed in memory, every form control row has been explicitly isolated, and our asset management vaults stand perfectly aligned. But as an elite systems engineer, your architecture is not finished simply because the markup text files are written. You must subject your document graphs to a strict, multi-tiered quality verification suite to prove their absolute operational integrity before they face real-world environments. This final section is your operational manual for technical testing and long-term capability verification. We will walk through the exact testing tools used to audit structural layout health, interrogate computed engine graphs, and confirm that our namespaced class and identifier selectors act as a perfect, highly extensible application programming interface ready to take on massive visual themes and runtime JavaScript architectures in the future. 12.5. The W3C new HTML checker validation engine. The first tier of our quality instrumentation suite is compiling our markup through the strict W3C new HTML checker platform. Amateurs guess if their code works by loading it into a random browser tab and checking if it looks acceptable on screen. This is a critical engineering error because modern browser parsers are intentionally designed with ultra-lenient error recovery algorithms that silently fix malformed loops and out-of-bounds cells behind the scenes, masking massive syntax bugs. To run a professional audit, you pass the raw byte streams of your gateway, portfolio, interaction, and console pages directly into the strict verification interfaces of the new HTML checker engine. Because we executed our entire codebase using the strict tag pairing technique, closing every element loop securely before stepping back to inject properties, our structural tree graph passes the compliance matrix with a perfect, zero warning and zero error validation score. The validator confirms that your nested content categories conform completely to specification laws, that your interactive slots and templates are structurally isolated, and that your form control attributes are safely bound within valid semantic parameters, ensuring absolute compatibility across every compliant engine on the global web. 12.5. User agent default layout and flow auditing. The second testing phase involves verifying the structural layout integrity of our unstyled documents under the browser's native user agent defaults. When you open your completed pages inside a completely clean browser environment, with all external stylesheets blocked or disabled, you are auditing the absolute baseline performance of your document flow. Because we rejected generic presentational boxes and organized our layouts using pristine HTML5 landmark elements, the user agent stylesheet automatically translates the document tree into a beautifully structured, highly readable typography ladder out of the box. The main landmark element stages your core data with clean spacing priorities. The NAV landmark collects navigation bar anchors into a predictable, logical menu block. The section and article nodes prevent content overlapping, and the complex data tables align their numeric data matrices across precise coordinate grid lines using their native row and column scopes. Furthermore, your scriptless interactive widgets remain fully operational. Clicking the summary triggers expands the details panels natively, and clicking the popover trigger buttons instantly promotes your warning dialog wrapper straight onto the top layer stack layer without a single line of CSS geometry. You have achieved a rock-solid, completely resilient progressive enhancement baseline that remains flawlessly usable for all hardware devices, even under severe network connection failures. 12.5. See accessibility tree graph interrogation. The third tier of instrumentation moves completely past the visual viewport to audit the hidden, parallel data graph running inside system memory, the computed accessibility tree. To verify this layer, you launch your browser's developer diagnostic panels, navigate to the Elements Inspector, and unmask the active accessibility graph view. During this structural audit, you are checking 4 absolute parameters for every node: role, name, state, and value. You will observe that your landmark tags carry perfect implicit ARIA roles without the redundancy of manually written attribute overrides. Step down to your vector icon button controls and verify that the ARIA label properties successfully override blank text nodes, forcing clear accessible name strings directly into the engine's speech slot. Audit your passcode form inputs and observe how the ARIA described B tokens forge explicit relationship links across the tree graph, binding password text validation boxes cleanly to their corresponding complexity description paragraphs. Finally, update the text fields inside your live tracking zones and watch the browser's tree monitor intercept the change, reading the entire container context as a unified atomic string because ARIA-live and ARIA-atomic are locked to true. Your digital ecosystem is completely normalized, delivering absolute semantic clarity to every assistive device across the industry. 12.5.d Future-proof extensibility matrix verification. The final, most vital tier of our quality review is testing our progressive enhancement extensible hooks to guarantee our code is fully prepared to take on CSS layouts and JavaScript engines later without any structural refactoring. To prove this extensibility matrix works, look directly at how your class namespaces and identifier targets are arranged across the node layers. Presentation layer readiness: every global header, structural aside card, navigation link, and form input is explicitly tagged with semantic, highly specific class attributes like site header, navigation bar container, and form input field element. When you create your global stylesheet files inside the /CSS directory later, you can map modern CSS grid and flexbox layouts, visual themes, responsive typography scales, and visual animations directly onto these class hooks. The styles will attach natively to the document tree instantly, completely removing the need to add new visual formatting elements or alter a single branch of your semantic core markup. Behavior layer readiness: every interactive dialog node, video player module, and calculation form container is bound to a distinct, unique ID selector like ID equals system player or ID equals core telemetry form, coupled with custom tracking chips like data output sync and data telemetry layer. When you drop your application event observers into the /JS file bundles later, your scripts can instantly query these exact preconfigured handles. The scripts can easily capture form entries, track live input load modifications, listen for media milestones, and drive custom dynamic interfaces directly through the C++ binding bridge wrappers. 12.5.e The synthesis: systems engineering realized. By successfully executing this complete verification pass, by validating structural compliance with the W3C checker, auditing baseline layout flow sanity, interrogating the computed accessibility trees, and testing future-proof extensibility matrices, you have elevated your craft from basic coding to advanced systems architecture. You have fully conquered the final milestone of this comprehensive HTML course. You are no longer just an amateur developer throwing loose text strings into a browser. You are a master systems engineer who knows exactly how to command the browser rendering engine from the initial binary conversion phase down to the last painted pixel layer on screen. Your document graphs stand as absolute masterpieces of semantic accuracy, rock-solid security, lightning-fast loading speed, and infinite extensibility, fully prepared to anchor the next generation of the global web.